你听得到吗？直播。你把声音给放开，你把声音给放开，你光那个声音，然后现在直播开起来以后。你把声音给放开，可以，我也听得到。然后你听得到吗？你把声音给放开，因为你那个分配是在Zoom上面，并没有在整个电脑上。
Okay, I logged myself as an external user to see what.
Yeah, I also have two laptops. One is controlling the live streaming, and another one is for the Zoom presentation. So I'm also testing actually right now.
Okay, so I'm gonna try my slides now. Huh?
Yeah.
Let's see. Yeah, it's a bit choppy.
Yeah.
Oh no, it's okay. Actually, it's okay. Okay. Yeah, this one is choppy.
Yeah, let me see whether I can.
Let's look at this one. Okay, I have an idea. Let's see.
Let me search whether I can make it more smooth.
Okay, let's see. Yeah, much better. Okay.
Great.
I reduced the resolution. How does it look on your side?
Yeah, actually here it looks very good.
The resolution is also good because I reduced the resolution.
You are the supporting us?
Yeah.
Okay. Okay. Now it's some because I didn't see something like plugin for the audio, and so I guess this one will hear the speaker is speaking from my laptop, and this guy will receive that.
Okay, that's not set up. I'll let them know. I'll get you set up, but you need you're gonna need a DI for that. All right, I'll get that set up. I'll just let the guys know.
Okay.
Yeah,
okay.
so that you can get set up.
Okay. Actually, just now the video looks pretty smooth.
Okay.
Yeah. I'm just trying to talk with the support people and whether they can make the.
What time was your presentation for?
Actually, it's just after 20 minutes.
Huh?
After 20 minutes, 8:30.
10 minutes.
20 minutes. Sorry. 20 minutes. Yeah. Yeah, it's smooth. It's very smooth from what I see right now.
Excellent.
Yeah. Great.
Okay.
Yeah, I also just now tested the live streaming is also very smooth, actually.
Excellent. Okay, so we have time anyway, right? You're starting in 20 minutes, right?
Yeah, we have time. We have time. I'm just asking the support person to come here to see how to make the audio a little bit louder.
Ah, okay. Yeah.
Yeah, but we can right now. I can hear you. I can hear just something like I want to make it really loud, actually.
Yes. Yes. Of course. Of course. Yeah, sounds good. I'm gonna get something to eat.
Yeah,
I'm gonna
sure.
come back in 10 minutes. And by the way, I'm gonna be on site on Tuesday. By the way,
Great. Yeah, probably we can meet in person at that
yes,
time.
exactly. That would be great.
Yeah, wonderful, wonderful. Yeah,
Moment,
yeah. Friedrich, he told me he cannot come here this time, and but probably he will be online maybe sometime today.
Yeah.
But
Yeah,
anyway,
I'm coming because also there is RSS after CVPR, Robotics Science and Systems. It's just a week after, so I'm gonna go there.
Okay. That is actually the two conferences at the same time. That is great.
Yeah, they always done this over the past 5 years. So they've always run one after the other one.
Okay, that is maybe they make it on purpose for this way.
No, I think RSS has adapted because they know that CVPR draws a lot of attention, so they do it afterwards.
So probably there will be more audience if they set up in next to each other.
Yes.
Okay. Yeah, but yeah, feel free to have something to eat.
Yes, I'm gonna get something to eat. Okay, see you in a moment.
Yeah. See you later. Yeah. good.
Oh.
Hello, hello, hello.
It's gonna need charge, so it'll go plug in here and it looks good.
That's fine. That's fine. It's something like I just can move my laptop to the desk. Otherwise,
Oh
I
yeah.
have to stand here for all the time.
Oh, I got you. Do you want to move it down there?
Yeah, probably better later.
Oh, you know what? Actually, you can't do that because you got the microphone here. So.
Several guys will be talk online, and
Okay.
here, for people who give the talk right here,
Yeah.
probably I can just ask him to come here to move my laptop to here.
Okay.
Somehow.
All right, that's fine.
Yeah, because in the morning, almost the whole morning is online talk.
Okay. It's gonna have to power back. Okay, so let's just put that. It should ding when it's ready.
Okay, do you know how long I should I get started? And I need to plug in somewhere here or not? Oh, it's already set.
It should be set in here. It should be good. You might want to mute your microphone on here, since you're going.
Okay, mute my microphone here.
And then you're gonna want to select this as your audio input device.
Can you wait a couple minutes?
Yeah,
Until
it's gonna have to
I
charge
set
a
up?
little bit. It's still charging up. It should ding when it's ready.
So right now, what I should do right now in my computer?
It's probably not gonna show. Maybe it will. If you go into your Zoom meeting, your settings.
Yeah, I'm right now
go back.
in Zoom meeting.
Go into your audio settings. Always on the settings.
Hi guys.
Hi.
Good morning.
Morning, Dr. Alex, Dr. Yanis. Yes, I'm still setting up, and probably it's a couple minutes.
Okay, no problem.
Yeah, what I should do?
Hi Davide.
Go to your settings here. You're gonna want to single microphone. This
Hi,
thing
Yanis.
is not charged up yet.
Hi Davide. Good morning. Good afternoon.
Yeah, good afternoon. Good morning to you.
Well, if that takes too long, I can just use that one.
Okay.
It doesn't matter.
Yeah, that's fine.
So does it work? You think?
You know, this is the first time we just unboxed them. So I've never even used one of these before, to be honest with you.
Okay.
My silver charge. Now, does it show down there? It's called an e-meet. So you want to look for e-meet. No, it doesn't show that.
No.
Let me make a phone call real quick.
Yeah. Otherwise, I just get started, and in the coffee break, I
Yeah,
can
and you get
10:20.
it set
I can talk with somebody to set up. Right?
Yeah, we can come back around. What time is the coffee break?
It's something like around 10:20.
10:20. Okay, sure.
Yeah. Right now, I just discuss.
Okay. So let's do plug there, and then plug this one back into your computer for you.
Oh, I can. Do I need?
That's just going to be for your audio out. So. You need to plug it to the internet?
No. I'm connecting with the wireless.
Okay.
Yeah.
Okay, let me get this right. Do you mind if I just plug this back into the back of your
Sure.
thing so it's charging?
Yeah. So, David, can you see my screen right now? It should be fine, I think.你看得见我的 screen?
Yes, we can see it.
Okay, that's great. Yeah, let's get started. First, thank everyone to come to our workshop, and it's the fifth time for us to organize this workshop on the topic of visual odometry and computer vision applications based on location clues. My name is Guoyu Lu. I'm currently system professor at Rochester Institute of Technology and the University of Georgia. Other guys organizing the workshop, including Friedrich Franthofer, Yan, Niku Sebi, Chandler come to time too. Okay. First, I need to remind myself to record on Zoom. Okay, let's see. Yeah, every time I forgot to record to record. Stop sharing. Okay, now it's recording. So first of all, today and tomorrow marks the Juneteenth holiday in memorial of the end of the slavery in the U.S., which is especially important for in the U.S. South. CVPR and our workshop encourage attendees to learn more about the Juneteenth and its historical context, and join the city of New Orleans in celebrating this holiday. And more information, you can go to the CVPR website to find the Juneteenth holiday. Okay, next. First of all, why we want to do VO, visual odometry, and location-based applications. And everything something like right now, if you use your mobile phone app or your computers, and quite a lot of time you Google your camera, maps, or even your photos want to know your location to give the labels for your images. And so that is why it's very important for us right now to use the location information to facilitate the computer vision applications. Okay, and some other applications, for example, in VO and in robotics applications, you could do odometry. You estimate the trajectory of the vehicles, and the robotics, and the building the maps, and the augmented reality, and those are all something going on using the visual odometry, and we're using the visual odometry for computer vision applications. Okay, and some other extended application, for example, is right now VO and localization has been used in agriculture and energy to build the 3D models for the crop fields. And somehow right now, since COVID-19, online shopping is also using visual odometry and the SLAM and the localization to do to facilitate online shopping. So it's very important for us to know the location information and use the VO to understand how to do better VO and the localization. Okay, and for the program itself, and it starts from 8:30 to 6 p.m. in US Central Time. And in total, there will be 9 keynote talks and 4 oral presentations. And for online audience, and in addition to Zoom, audience can also leave questions on YouTube chat, and the organizers will read the questions. So to facilitate for online audience, and you can go to the handout in the CVPR Zoom, and in the CVPR virtual site to find out the Zoom link. So in total, there will be 9 world-renowned speakers from both universities and the industries. And that is from, for example, University of Maryland, Professor Alomonos is here already. From UPenn, MIT, Zurich David is here as well. And Dr. Song is also here from TMU, and the CMU, Microsoft, Oppo, and the University of Zaragoza. And those are separated into morning and afternoon session. And totally there will be 4 paper presentations, and from Chinese Academy of Science, and CMU, and UC Berkeley, from the industry, Cisco, and from KAIST. And there will be 4 presentations. And the morning session, there will be, in total, there will be morning session and afternoon session. And from right now until 10:20, that will be the first half session. And in the morning, including 2 keynote talks and 1 paper presentation. And in the second half of the morning session, there will be 3 keynote talks. And in the lunchtime, you can go to the poster session and to watch some posters as well. And from 2 to 6, there will be another afternoon session, which include 2 small sessions as well. And from 2 to 3:30, there will be the first session, and including 2 keynote talks and 1 paper presentation. And from 4 to 6, there will be another 2 keynote talks and 2 paper presentations. Okay. So that is the opening remark. First, let's welcome Dr. David Saramuza to give the first talk. And I want to first introduce a little bit about Dr. Saramuza. Dr. Saramuza is currently a professor in both University Zurich and ETH Zurich, where he directs the robotics and perception group. His research lies at the intersection of robotics, computer vision, machine learning, using standard cameras and event cameras, and aims to enable autonomous, agile navigation of micro drones in search and rescue applications. And his team has won IROS 2008 autonomous drone race, and in 2019, it was ranked in the Alpha Pilot Drone Racing with championship, actually ranked the 2nd. And for his research contributions to autonomous vision-based and drone navigation and even cameras, given multiple prestigious awards such as European Research Council Consolidator grants, the IEEE Robotics and Automation Society Early Career Award, and the SNSF ERC Starting Grant and the Google Research Award, as well as the KUKA Innovation Award, and the 2 Qualcomm Innovation Fellowship, European Young Research Award, and the Misha Mohawat Neuromorphics Engineering Award, and several other best paper award. And in general, he is very well known in the visual odometry and drone research, and some of his research in event-based camera-based visual odometry and SVO has been widely used for the visual odometry research community. Now let's welcome Dr. Saramuza to give the talk. Stop sharing.
Thank you very much for the intro. Can you confirm and you can see my slides and you can hear my sound?
Yeah, I think we can now.
Okay, so thanks a lot for inviting me here. So yeah, I've been working a lot on visual odometry and visual SLAM in the past, and today I want to tell you also what we are working on beyond visual odometry. So visual odometry.
Sorry. Can give a little bit second? I want to turn off my slide so that it seems like there's a little bit. Okay, right now it works. Sorry.
Okay, sure. So I've been working a lot on visual odometry and visual SLAM over the past 10 years. But what I would like to talk on today is about the work that I've been very excited about on autonomous, agile, vision-based drones. So basically using only onboard cameras and computation to allow drones to navigate super fast and maybe even better than human pilots. How did it all start? So I started this journey actually 13 years ago. What you see in this video is from September 2009. It was the first vision-based autonomous navigation of a drone in GPS-denied environments. So we were using a single onboard camera to make the drone autonomous, and we participated in a competition where we were supposed to take off from the floor, move 10 meters all autonomously, and then pass through a window and land. At the time, the safety regulations did not allow us to fly the drones freely, so we had to secure the drone with a fishing rod, which you see here. Also, at that time, we didn't have enough computing power to run everything on board, so we used a 20-meter long USB cable to connect the onboard camera to an off-board computer, a laptop. And this was the moment where basically the drone passes through the window. So first we pass the fishing rod, and then the drone passes. So that was 13 years ago. And we were using PTAM at that time for visual odometry, so for state estimation. After that, we developed SVO, that became our flagship visual odometry algorithm. And where do we stand today? So actually, that work inspired the Ingenuity Mars helicopter, which is today on Mars and flies using the same technique that we used 13 years ago. In fact, one of the team members of the previous video, Stefan Weiss, after his PhD, then he flew to California and he was an engineer at JPL, helping them to make the visual navigation system of Ingenuity. But not only we have nowadays drones flying on other planets, but we have a lot of vision-based navigation today, even on Earth. So what you see here is, for example, Skydio drones that do semi-autonomous or autonomous inspection of bridges using 6 cameras all on board with the onboard computation. And here you can see also the depth perception that the Skydio drones provide. So this begs the question then, what's next for research? So are we done in robotics research? No, not really. Look around you, and especially look at the performance of autonomous drones today. If you look at how autonomous drones in the previous videos, they navigate, they look very clumsy. This is to say that basically the performance of autonomous drones is still far from human pilot performance in terms of speed, versatility, and robustness. To see what I mean, look at this video. Here you see a drone pilot that is piloting a drone during an FPV drone race. These are competitions nowadays that have become as popular almost as Formula One, where pilots compete against each other in a speed race. And what is actually quite impressive about these videos is that human pilots are capable of flying super fast at speed that go over 70 kilometers per hour, despite the motion blur generated during these high-speed maneuvers, and also despite the latency of the brain. In case you didn't know, our brain is quite slow. It has a latency of 200 milliseconds. But nevertheless, humans are capable of these impressive maneuvers. Why? Because it turns out that while the human brain is slow, it's actually much better than machines at making better decisions in more complex situations. And this is actually thanks to years of experience. So basically, what I want to answer in the research that I'm doing at the University of Zurich is what does it take to fly as good or even better than human pilots? But you may ask, why? Why do we bother about flying agile? Flying agile is important because if we can make drones faster, we can increase their range. This is because the drone battery at the moment is limited to 20, 30 minutes. If you can make them faster, they can cover longer distances. You can see what I mean in this plot, where you have on the x-axis the flight speed in meters per second and the range in kilometers on the y-axis. Typically, autonomous drones operate in this range. So usually, you know, if they navigate at 2 meters per second, they can only cover like, you know, less than 1.5 kilometers. But if you can make them, for example, triple the flight speed, like at 6 meters per second, they can cover up almost 3.5 kilometers. So 3 times as far. So that's actually a reason why it is important to make drones more agile. But this is also important for other missions where time is important. For example, search and rescue applications, where every minute saved is actually critical to save people's lives. Also delivery applications, exploration, inspection, reconnaissance, also flying cars, and finally also space. So these are all applications where flying faster actually is important. But also another reason why I like agile flight is because it raises fundamental challenges for robotics research in terms of perception, planning, learning, and control. It really allows us, researchers, to push the limits on vision-based navigation because it's really, really, really difficult. But before I go on, let me introduce you Barracuda. Barracuda is the friendly name that we assigned to our vision-based drone. The drone that you see here, it's less than 20 centimeters in diameter. It has an NVIDIA Jetson as the brain. So we run there visual odometry, but also powerful neural networks for perception tasks. And then we have 2 different types of eyes. We have interior sense cameras, depending on the task that we want to do. And as you can see at the bottom right, the weight of the drone is quite low. It's less than 1 kilo. Can generate up to 70 Newton of force, so it's quite strong. It can reach accelerations up to 5 Gs, which is almost as much as the astronauts experience when they are launched to the moon, for example. So how do you typically control a drone? This is the traditional drone control architecture. You have the images and the inertial measurement units that are input to the perception module that does, for example, visual odometry, but also mapping. Then the result of these are sent to the planning module that generates a collision trajectory, a collision-free trajectory. And then this one is executed by the control module. So what are the issues with this architecture? The main issues about the traditional drone control architecture is that it is very fragile. It is very fragile to imperfect perception. What I mean is, for example, motion blur, high dynamic range scenes, because when you navigate fast, you have a lot of motion blur that basically will render state estimation, visual odometry, you know, very fragile. Also, when you fly fast, you will have a very sudden changes of illumination, which again will cause loss of feature tracks. And also when you fly fast, actually there is a lot of non-linear aerodynamic effects, which is very difficult to model. What are other problems with this architecture? Well, actually, it requires a tight coupling of perception and action. This is something that basically normally people ignore, but when you fly a drone is a very unstable system. For a drone to hover, just hover, it needs to actually constantly observe features in the environment. If there are no features, then the drone crashes. So that means, for example, that if a drone needs to pass, for example, through a door, it needs to constantly look at the door in order to pass through it. Unfortunately, though, the problem is that since a drone is an under-actuated system, it's not free to choose any orientation. You need to basically choose an orientation that also favors perception. And this is very difficult. That's why we say in a drone, perception and action are tightly coupled. Another problem is high latency due to the sequential structure of this architecture. So perception, planning, and control, each one has its own latency. And so at the end of the chain, you have a compound latency, which is actually non-negligible. It can be in over hundreds of milliseconds, which basically limits the maximum agility speed of your vehicle. So in order to change this, to make the system more robust to imperfect perception and faster, we need a change of paradigm. Well, what is at the extreme of this change of paradigm? At the extreme of this change of paradigm would be to learn end-to-end a sensory motor policy that maps sensory inputs to control commands. Is this possible? Well, in some tasks, it has been shown to be possible, but the problem is that it's too sample inefficient, especially if you want to train it on a physical drone, because drones are going to crash thousands of times, especially when you want to fly fast. So this is something not feasible on real-world drones. Another problem with this, end-to-end control policies is that they're very difficult to interpret what they're doing. When something goes wrong, you don't know what is going on. So what I've been working on over the past few years is how to augment the traditional robotic architecture with learning-based methods. And that's what I'm going to focus on in the next minutes. But now the key questions are, should we train it with supervision or without supervision? How do we get enough training data? Can we possibly learn in simulation? And if we train in simulation, how do we address the simulation to reality gap? So these are all things I'm going to talk about. But I want to talk about them in the context of 3 tasks that I've been very excited about, that I've been working on over the past 3 years. The first one is autonomous drone acrobatics. So how to teach drones to perform acrobatic maneuvers that are same level as human acrobatic maneuvers. I also want to talk about navigation in the wild. In the wild, in robotics means in unknown, unstructured environments. And finally, I want to talk a very, very recent topic, which is very, very exciting, which is autonomous drone racing. So let's start with the acrobatic maneuvers. And let me start with a video. What you see in this video is an autonomous vision-based drone. This drone is using a single onboard camera, an inertial sensor, and an onboard computer, and is controlled by a neural network that maps images to control commands. And we show that by using a neural network, we achieve unprecedented performance, meaning that we could not fly so agilely using model-based approaches. However, to train this neural network, we did not rely on a single real-world image. Rather, we relied on just 5 hours of simulation. Here you can see our simulation environment. We used the gazebo, which as you know, is non-photorealistic. We simulated hundreds of drones flying for an equivalent of over 50 flight hours each. And we could do this in just 5 hours of training time. On the left, you see the simulation, what is being learned. And on the right, you can see what the drone is doing. And the interesting thing is that we did a one-shot sim-to-real transfer. So the policy was trained only in simulation, and it was deployed to the real drone without any fine-tuning. How did we train this neural network? So we trained this neural network using privileged imitation learning. What does it mean? It means that basically we have a neural network, our student network, that tries to imitate an expert. But this expert is not a human, because we don't want to be as good as a human. We want ideally to be better than a human. So our expert is actually an artificial expert. That means it's a model-based expert. In this case, we actually use a model predictive control. And this artificial expert is privileged. What does it mean that it's privileged? It means that in simulation, he knows perfectly the state of the robot, so position, velocity, and orientation, as well as perfect knowledge of the environment. So exact knowledge of the environment. That's why it's called privileged expert. And what we do is that we ask this neural network to imitate the control commands output by the expert. So basically, we want that the control commands predicted by the neural network match the control commands output by the artificial expert. Now, the key question, though, is how to make sure that the network trained in simulation transfers to the real world without any fine-tuning. So as you can see, our simulated environment is really non-photorealistic. We use gazebo. We put some random pictures on the floor and on the walls. But as you can see, this is significantly different from what the real-world drone actually sees. So how did we manage to train in such an environment and deploy it to the real world without fine-tuning? Our trick actually consists of using appropriate sensory abstractions. The trick is not to train on raw pixel information, but rather to train on an intermediate representation that is similar both in simulation and in the real world. These intermediate representations we found to be appropriate in terms of feature tracks. So we actually train our policy on feature tracks, on optical flow vectors over the last 10 frames. And you can understand now why it works without any fine-tuning, because feature tracks look similar both in the simulated environment and in the real world. And we also prove that actually these sensory abstractions reduce the fastest time distance between the observation models in simulation and in the real world. Now, let me go on. Let me focus on another task that we are working on, which is navigation in the wild. What you see in this video is, again, the same drone that is now navigating in forest environments, so unknown, unstructured environments. This is the onboard view of the drone. This is the same drone navigating in a structured, unknown outdoor environment. This one is a commercial drone that bumps into an obstacle. This one is instead, again, our drone navigating outdoors in another forest. And the nice thing about this is that it's doing its navigation very fast, at speeds that reach 40 kilometers per hour, so 10 meters per second. And the code of this was also released open source, together with all the data sets. Again, we trained only in simulation. Why? Because simulation is fast, is cheap, and especially when you work on drones, it's very, very safe. You cannot train such a policy in the real world. It would require hundreds of flight hours, which means months of work, and it would be impossible because the drones would be crashing thousands of times. You would have to change the batteries every couple of minutes. You would have to spend a lot of money, probably, more than, $20,000 just to do this. So we trained only in simulation, but now we used a more advanced simulator, Flightmare, that we also released, which basically allows you to interface directly with the Unreal Engine. So as you know, there are beautiful scenarios, 3D scenarios that you can download from Unreal Engine. For example, forest environments. And that's what we did here. We downloaded a few forest environments, and then we imported it into our simulator. And then again, we used privileged imitation learning. In this case, who was our artificial expert? Our artificial expert in this case was a Monte Carlo sampling method that tries to generate collision-free trajectories towards the goal in the direction of a global collision-free trajectory. So let me rewind the video. So since the expert here is privileged, we can basically generate a global trajectory from the start to the finish that avoids all the trees. But now we don't want to imitate this trajectory because we want to be able to cope with ambiguities in the real world. If we try to imitate just a single global trajectory, it wouldn't work. So what we actually did is that we just use this global trajectory as a reference. But then what the network is trying to imitate is a multimodal distribution a multimodal distribution of collision-free trajectories generated by Monte Carlo approaches. These Monte Carlo trajectories are a few thousands, and they are all generated in the direction of the global trajectory. However, again, we face the same problem. Since we are training in simulation, we want to be sure that then it transfers to the real world without any fine-tuning. One shot scene to real transfer. How do we make this possible? Again, as you can see in this slide, the problem is that the image of the simulated forest is very different from the image of the real world camera captured by the real drone. The trick, again, is not to train on raw image pixels, but rather to train on a sensory abstraction, so on an intermediate representation that looks similar in simulation and in the real world. We also proved here that if you train on depth maps, you reduce the Wasserstein distance. So we actually train on depth maps. And you understand why it works, because depth maps are similar in the simulation and in the real world, no matter what the texture looks like. It doesn't matter if the texture is cartoonish or whether the color of the tree, changes over the seasons. The depth is always the same, no matter what. Now, when you train on depth, there is a key question you need to answer. Do you want to train on noisy observations or non-noisy observations? Because since we have access to the ground truth in simulation, in principle, you could actually train on ground truth depth maps. Well, we did it, but the performance was 20% inferior to training on noisy depth maps. So the depth maps that we generate are actually actual depth maps generated from left and right stereo images. We apply semi-global matching and we generate depth maps, and we train directly on these depth maps. And now let's go back to the initial question. Remember what I told you? We are using deep networks in combination with model-based approaches to fly faster and more robustly than ever done before. Is this true or not? Let's try to verify with quantitative data. So what we did is that we compared against baselines that do not use neural networks, but these are basically instead the best baselines of model-based approaches. And the two we used are Fast Planner and Reactive, one from MIT and one from Hong Kong. As you can see, the Fast Planner takes 65 milliseconds to actually output control commands, while the reactive baseline takes about 20 milliseconds. Instead, our neural network policy that maps basically these depth images to control commands only takes 10 milliseconds. So it's twice as fast as the model-based reactive planner and 6 times as fast as the model-based fast planner. So we proved our point, and by combining model-based approaches with neural networks, you can actually shrink by a lot the latency. And this is important. Why? Because if you can reduce the latency, you can actually fly much faster. Let's see. What you see here on this plot is the success rate versus the navigation speed in meters per second. So we range navigation speed from 4 to 10 meters per second. Our neural network controller is the one in green. And as you can see, at the beginning is 100% success rate. Then the success rate drops to 90% at 7 meters per second, and it drops to 60% at 10 meters per second, which is actually not bad if you think about. In fact, we can fly twice as fast as the baseline, because as you can see, for example, the fast planner, basically, which is quite slow, actually the success rate drops to 60% already at 3 meters per second, while the reactive policy drops to 60% already at 5 meters per second. So again, this proves our point that by using neural networks, not only you can navigate much faster, but you're also more robust against imperfect perception, like motion blur, illumination changes, and so on, and especially missing data, which happens a lot when you navigate very, very, very fast. Another thing that we are working on is autonomous drone racing. In autonomous drone racing, what you want to do is to have a drone navigate through a sequence of gates as fast as possible. The participant that reaches the finish line in the smallest possible time is the winner. What you see in this video is a vision-based autonomous drone. It's using a single camera and an onboard computer, and it can already navigate as good as a human pilot. In fact, actually, we are already superhuman because we invited to Zurich last week the best human pilots in the world, and we have outraced all of them in speed. So this is something possible. This is still unpublished, but I'm going to anticipate the results. On the left, you can see what the autonomous drone sees. Basically, we have gate observations by neural networks, and then we have a reinforcement learning controller that takes as input these observations, and it outputs control commands. And here you can see, for example, a head-to-head race against Marvin, who is a world-class drone racing pilot, who is only 15 years old, and we are much faster than him. And now, another thing that I want to talk about for the remaining 2 minutes is what's next. So when we will have achieved the same robustness and performance of our human pilots, the next step is to outperform human pilots in many different tasks. Who is better today than human pilots? Well, birds are better than human pilots. Here you see, for example, a sparrowhawk. They move very agilely through obstacles. And the reason why birds are so agile is because they don't use standard cameras. In fact, the key problem to flying even faster is actually the fact that still, robots are limited by the frame rate of their camera system. Why? Because, for example, if you want to estimate position and velocity, you typically need 2 consecutive frames. That means that given a frame, you need to wait of, a sensing latency, which is given by the frame rate of your camera until the next frame arrives. And this usually is in the order of 30 Hertz, 100 Hertz. So we're talking about 10 to 30 milliseconds latency, sensing latency. In addition to that, there is the processing latency, which is the latency that it takes to process the last frame. And this one varies significantly. It varies between a millisecond or even more than 100 milliseconds, depending on the exposure time of your camera, which is actually limited by the speed and especially by the illumination in the environment. So if you want to fly more agile, then you have to move away from standard cameras. You need to create a low latency, low discretization perception pipeline. And this is only possible if you use event cameras, because their output is not at regular intervals, but it's rather continuous in time. What is an event camera? An event camera is a camera that measures only motion in the scene. And to see what I mean, look at this video where I'm moving my hand up and down. As you can see, an event camera only reacts to motion pixels. So pixels that do not detect any motion do not trigger any information. The beauty about an event camera is that the pixels are all independent of each other. And every time a single pixel detects a change of intensity caused by motion or caused by a blinking pattern, then that pixel triggers an event. But this generation of events is continuous in time. To see what I mean, look at this animation where I'm going to rotate this disk with a black dot. So see what happens. As you can see on top, the output of a standard camera is a stream of frames at constant time intervals. On the other side, the output on event camera is a spiral of events in space and time, because only pixels that detected motion triggered events. And if nothing moves, there is no generation of events. So you have a drastic reduction of bandwidth. But the key beauty of event cameras is that no matter how fast the camera moves, there will never be motion blur. So an event camera has 2 key advantages compared to standard cameras. It has a microsecond latency, which is even more than you actually need in most robotic tasks, and it has no motion blur. Just to reinforce what I'm saying, on top you see what the output of a standard frame-based camera is, so you get frames at constant time intervals, and at the bottom you see the output of an event camera, which is continuous in time. And it's only dependent on the dynamics of the scene. Now what I'm going to show you is two applications of event cameras into drones. One application is to keep drones flying when a rotor fails. What happens when a rotor fails? Let me show you with a drone. So I don't know if you can see me, but I'm holding a drone here. And if one motor fails, typically the drone starts spinning on itself like a ballerina. And then if you have no position information, the drone will drift and eventually crash. And this is unfortunately happening. In Zurich, we had 2 crashes caused by a motor failure. And one of these crashes was next to a kindergarten with kids playing around. So you can, however, control the drone to remain unstably hovering. So that means it will continue to spin on itself, but at least it will not drift and will not crash, provided you have a position reference. The problem is, with standard cameras, you cannot provide position references because standard cameras, during this high-speed spinning motion, would be affected by motion blur. It turns out, though, that this is not a problem for event cameras. Let me show you what I mean. So here you see that we induced now the failure of one motor. So the drone is spinning on itself, but now the drone is not crashing thanks to the event camera. The output of the event camera is different, but there is no motion blur. There is no motion blur at all. So you can constantly detect and track features over time. Not only could we actually stabilize the drone, but we could even do trajectory tracking. We could follow a given trajectory back and forth. Here again, you see on bottom right the output of the event camera, which is different, but it's not motion blur. Another application of event cameras to robotics is, for example, for dodging dynamic objects. For example, when you throw an object and you want to avoid it. If you used a standard camera, you would actually not be able to do it at this speed. You will need to lower the ball speed and the drone speed by at least a factor of 10. Because in order to avoid an object, you need to estimate its position, but also its relative velocity with respect to you. And for doing this, you need 2 frames to measure the velocity. With the standard camera, you need at least 30 milliseconds, at best 10 milliseconds distance. But this will not give you enough response time. We showed instead in this research work that using an event camera, we could do this with a latency of just 3.5 milliseconds. And so we could actually work with relative speeds up to 10 meters per second. And with this, I would like to conclude my talk. So basically, to recap, I talked about a research topic that I call agile vision-based flight. I think to make drones that will be able to navigate autonomously as good or even better than human pilots will take almost 10 years. But this is actually a research topic that will really push the limits on vision-based navigation, not just visual odometry, or perception, control, everything. I've talked a lot about learning-based methods. And what I want to convey is basically that the takeaway message is that learning-based methods are more robust to imperfect perception, and they also exhibit lower latency than traditional methods. I also talked about the fact that we are able to train our control policies directly in simulation without real-world images, and transfer to the real world was done one shot without any fine-tuning, thanks to the use of appropriate input, but also output abstractions. And finally, I talked a little bit about event cameras that have a very low latency and no motion blur. And I think they will also, open up possibilities for high-speed robotics applications in the future. And with this, I would like to thank you for your attention. Thanks.
Thank you, David. Any questions from the audience? Yes, please. Claudia, I want to give you the microphone.
Hi, so I have a question about when you sim to real experiments. So motion blur happen quite frequently in real life cameras. So, but I'm not sure if that happens also for simulators. So when that happens, does the feature tracking still work well for the trained neural network model? And the second question is that, so depth quality is also not very good in real life for depth sensors. And so when you train on depth input, so how will the quality of depth will affect the trained model's performance?
I didn't understand the second question, honestly. I only heard the first question because there is a lot of echo in the background. So the first question was about motion blur. So in simulation, we do not simulate motion blur, but nevertheless, it was able to perform in the real world. What we did is that we added noise in simulation at test time. So we also did the tests in simulation in addition to the real world, in a different type of simulated forest, of course. And what we simulated was, for example, adding noise. And what we observe is that actually, if you add the noise, that is realistic noise values on the depth, like you will get from a real depth camera, the performance drops only by 5%, while it would drop by 100% in the model-based approaches. At speeds, or model-based approaches already at speeds of 5 meters per second. So it really pays off to use neural networks. Of course, if you increase then the noise much further, then it will start to degrade. But the degradation will be smooth. It will not be abrupt like it's happening with model-based approaches. The details are given in the paper. But to answer your first question, no, we didn't simulate motion blur. It just happens to work in the real world as is.
So can you repeat your second question? We didn't actually hear your second question very well.
Yeah, you can maybe you can repeat the second question if you can.
Yeah, sure. Thank you. So the second question about the quality of depth input. So still, you mentioned that you're training on the depth images, and then but my question is that so the real life the depth images from depth cameras are very noisy, especially in outdoor situations. So how does your how does your model get like how does your model work in real life data when the input is depth images?
It does work. So as I mentioned, we do tests also noisy depth maps in simulation to show up to which level basically of depth map noise is able to handle, and up to levels that are 10% of the depth actually works very well. And in the real work, it works. Let me show you. Just a second. Oh yeah, I found it. So I'm gonna project the slides again. Okay, here you can see what I mean. Basically, here on the left, you see the best state of the art, which is model-based, fast planner from Hong Kong University of Science and Technology. In green is without noise, and in blue is with noise. You can see that at the forward speed of 5 meters per second, when you add noise, the performance drops by 100%. We add the noise levels of 10% of the depth estimated by the inter-real sense. While you can see that with the neural network learned end-to-end control policy, not only we are able to sustain flight reliably up to 10 meters per second, but the performance drop before, without noise and with noise only drops by 5%. So I think the results are quite impressive in my opinion. So that's again, the message that neural networks are really robust with to noise. But here, the key to success was to train in simulation on realistically noisy depth maps. What do I mean? We are not training on ground truth depth maps. We are training on depth maps that were obtained by stereo matching of the left and right simulated images. Okay, that was the key.
Cool. Thank you for technical answering. Thank you.
You see this also from the edges of the trees. You see these white edges around the trees? These are occlusion artifacts. These are the proof, the evidence that basically we are using realistic stereo matched left and right images, because these are occlusion artifacts. And these are very important to be provided.
Any other question? Just a brief question, David. Right now I want to hear about your insight. And currently, there are still some people argue that event camera has too low resolution to contain the necessary information. And you mentioned event camera doesn't have any blur, and in comparison, RGB cameras, normal other RGB camera may have blur, but in the VO, similar idea. Actually, event camera is extracting the key points in reality, and similar idea in RGB camera is actually using the keyframe. And whether you think those two principles, using keyframe and key points in event camera, can compensate each other, or you think event camera is actually absolutely much better, or the keyframes in RGB camera is actually redundant, not necessary? What do you think?
Okay, I answered the second question about combining them, and then I go back to your first question, which is about the resolution. It's better to combine an event camera with a standard camera, always. Why? Because an event camera is a high-pass filter, so it does not sense the absolute intensity. There is no way. It's impossible. Okay, it's like asking a single neural network to predict depth from a single image. It's an ill-posed problem. Okay. Is the same with an event camera. You cannot recover the absolute intensity. So already this is a reason to always combine it. Because, for example, if you want to detect something when a car is still at the traffic light, you want to use a standard camera. So I will never remove an event camera. Actually, what we showed in previous work is that if you combine an event camera with a standard camera, you can then also remove the motion blur, for example, from the standard camera. So the standard camera can provide absolute intensity and color information, and the event camera can help you to remove the motion blur. So you will get always sharp images, and that's very good, not the news. About the resolution. So if you check this slide, actually the resolution is not low at all. Depends what you call low resolution. So today already we have over 1.2 megapixel event cameras. For example, the company Prophecy, which is a CVPR today, is actually, selling event cameras that have 1.2 megapixel resolutions. And this is happening now, and the resolution is going to increase further and further, thanks to the fact that the three main event camera companies have partnered with Samsung, Sony, and OmniVision. The cost is a bit high. The range is between $1,000 and $5,000, but it's shrinking. And there is already a product using an event camera from Samsung that costs $180. It's for detecting people falling at home. So it is happening. The cost is already shrinking, and it will shrink further as there will be more killer applications. I think that the situation is very similar to what happened with depth cameras. The first time of flight camera was, in the 90s. It would cost more than $10,000. And 20 years later, the cost dropped to below $5. Okay, so that's what we are witnessing now with event cameras. The event camera resolution was actually, for the first time, VGA only 2 years ago. And last year, the first 1 megapixel resolution event camera was out. And now it's just increasing over time. So I think it's very good news for the field.
Okay, thank you. Thank you, David. Let's thank you, David, again, and for his very interesting talk. Now let's move to the second speaker, Dr. Yanis Aloimonos. He's here. I can see him. Yeah. Dr. Yanis Aloimonos is a professor in computer vision and intelligence at the Department of Computer Science in University of Maryland, College Park. And he's also the director of the Computer Vision Lab at the Institute for Advanced Computer Studies. And he's also affiliated with the Institute of System Research, the Neuro and Cognitive Science program at Maryland Robotics Center. He obtained his PhD from University of Rochester in 1990, and he's also interested in active perception and modeling of the vision as an active dynamic process for real-time robot system. And for the past 5 years, he has been working on bridging signals and symbols, especially on the relationship of vision to control and the relationship of actions and language using hyperdimension computing. And actually, Dr. Aloimonos has been very well known for his research on active vision. And I have also read some news that from his lab, he has developed some very small robot that functions like bees. And I'm not sure whether he's introduced some of the related research in his today's talk, but that would be interesting, and I would encourage everybody to look at his work, and developing very small robots to function as bees for agriculture applications and many other applications. Let's welcome Dr. Aloimonos for his talk, and his topic is hyperdimension active perception towards minimum cognition.
Great. Thank you very much. It's a real pleasure joining your beautiful workshop. I have so many friends in this community, even among the speakers. And as you know, navigation is at the seat of intelligence. Creatures started navigating, and that's how they developed intelligence, as the neuroscientists have been telling us in the past 20 or 30 years. So today I will talk to you about a new approach that we are following, and we named it hyperdimensional active perception. This is joint work with Cornelia Vermeulen, with my student Nitin Sanket, who will be joining Worcester Polytechnic Institute as an assistant professor next month, and my students Chahat Singh, Dehao Yuan, and Peter Shuto. There are two basic themes in our work with regard to this lecture. The first theme is the one of minimalism. Minimalism is a very powerful idea. It has been used very successfully in computational linguistics by Chomsky and his colleagues. The idea here is to solve a vision problem using the minimal amount of visual information. So you can imagine the maximal amount of visual information where you basically have the depth of the scene, like the SLAM approaches that are doing very interesting solutions to a variety of problems. But that's the maximum. There is some kind of a minimum, the minimum thing that you have to do in order to solve a problem. And naturally now there are many things in between. So this introduces a hierarchy in complexity of visual computations. So the second theme, which is the main theme of this lecture, is about the fusion of control and perception, which is something that basically amounts to sensory motor intelligence. This is the intelligence that we had before we developed language. And in our opinion, it's very important to understand that step because, you know, many solutions involve language very early, and then it becomes very murky to understand the principles involved. So sensory motor intelligence is like the intelligence without language. And it amounts to what, again, the neuroscientists have been telling us for the past 30 years, to the problem of prediction. Okay, and the field is not there yet, but it's getting closer and closer by the day. Especially if you look at the natural language models, the large language models that predict the next thing. So what I'm going to do is I'm going to speak very little about minimalism with an example, and then I will concentrate on the second issue. So let's look at three problems. Finding independently moving objects while the observer is moving, navigating in cluttered environments, and going through gaps. Okay, and we will solve all three problems by computing just the uncertainty in the optical flow, not the optical flow values themselves, but the uncertainty. And no depth of the scene is going to be needed here. So this uncertainty provides a retinotopic map that is used by the control module to do the navigation. Okay, so here's an example. Here's Chahat, and he's going to throw a ball. Okay, and it's moving fast. It has motion blur. And you can see here systems, other systems like Midas that are trying to find the object. And here, by computing the uncertainty in the optical flow, just the uncertainty, it will give you the moving object. So here's another example. Again, here you see on the left, there's a drone and there are objects that are thrown at it. And again, you see the results of a depth camera, of the Midas system, of occlusion masks, and of the uncertainty. Again, in the second example. Here you have a drone and then objects will be thrown at it, detected, and sort of dodged with this technique. Dodging is a problem that we worked together with Davide on a paper. By the way, Davide, that was such an amazing talk. So here is a drone navigating in like some simulated forest in the lab. And you can see what, again, the depth camera will provide, or Midas, or occlusions, or the uncertainty. So, using an anisotropic diffusion, we can take the uncertainty values and build the hazard maps that will allow the navigation. And here's going through the gap. Again, you can see cases where these other systems are failing. So basically, uncertainty in the optical flow will first of all give you the occlusions, because these are places where you cannot compute the optical flow. But not only because when you have blur, again, you have uncertainty. And if you have darkness and homogeneous regions, again, you have uncertainty, and so on. Okay, so minimalism is really a part of the future, not only because of the swap constraints, that is, especially if you are interested in building very small drones, very small mechanisms, like we do when we're trying to make functional bees, then they don't have a lot of luxury to put whatever sensors you want on this agent. And so it is natural that you are going to seek minimalistic solutions. However, the future of AI is a frugal and parsimonious AI, Because think about it, let's say, take a self-driving car industry. When we have built successful self-driving cars, we don't want them to cost $1 million. We want them to cost as little as possible. And so if there are, solutions that cost less and they're faster and robust, the community will adapt them. And so there are new questions that are raised. I give you 1 million neurons. What tasks can you do? Like the bee has about 1 million neurons. They can do these amazing things. Or I give you 1 billion neurons, like the hawk has. What can you do then? And so on. Okay, so let's come to the second point. Perception and control. And let me come directly to the gist of the argument. Actions that we do are really guided by prospective information as opposed to instantaneous feedback. Because adaptive behavior has to deal with the fact that events precede the feedback signals about them. So, as David had mentioned, you have delays in the control pathways, about 250 milliseconds, maybe a bit less. So relying on feedback is not adaptive, and the only way to overcome the problem is to anticipate what is going to happen next and to use that to control the behavior. So the important question is the one of prediction. How is this prediction going to happen? So prediction becomes, you have to predict many things. You have to predict the vision, you have to predict the sound, you have to predict the motor, you have to predict everything. How will that happen? If you have errors in the streams of predictions that you're making, it becomes very difficult to make those streams consistent with each other. So we can predict only if we can predict one thing. What this one thing could be. So when you think of a robotic mind, because you have an agent that is solving problems, you have some form of a mind, okay? Simple one. But it is an amalgam of many competencies, like perception, action, decision, knowledge, language. All of those together, they come to integrate into one intelligent system. And if you look at the field today, for those particular disciplines, in general, they speak different languages. The planning people speak one language, the vision people speak another language, the sound people speak another language, and so on. And so hyperdimensional computing provides this new language. It is a mathematical field that allows the creation of the same currency for all the components of an intelligent system. Okay? So as many scientists have been telling us that the problem of intelligence is really a problem of prediction. You have to be able to predict the events that are about to happen. And from this prediction and the current situation, you can generate the control signals. Okay? And as I said, it can only happen if you take all the perceptions and all the controls and you bind them and you make one signal out of them. So, informally speaking, imagine, for example, that you make a convolution of a video that you are collecting as you are moving with the control sequence that produces the movement. Okay? informally speaking. Then you get a new function that has inside both. So this is what the hyperdimensional computing will allow us to do. All right. So this another name for it is vector symbolic architectures, and it is about 20 years old, this field. And it tries to compute things with very high dimensional vectors, about 10,000. And these vectors make elements of a vector space. So if you use zeros and ones for the elements of these vectors, because you can use also real values, but if you use zeros and ones, then you are on a 10,000 dimensional hypercube on the vertices of it. And the idea is that whether you are an image or a video or a sound or a movement or a concept or a word, you are represented as a high dimensional vector. The representation is the same. The language people have been using this idea somewhat related, using the representation word-to-vec that produces such kinds of vectors, okay? But only for language. To produce such kinds of vectors from images is still an open problem. There are various approaches for the time being. Okay, so there are two basic operations between these vectors. One is addition or bundling. You can just add them. The consensus sum. If you have more ones, the result is 1. If you have more zeros, the result is 0. And then the other operation, which is the most important, especially for the active perception problem, is the binding of two vectors. The binding has many definitions. You can have circular convolution, you can have the exclusive OR operation. There are many ways that you can implement the binding. And there are these properties. So the bundling or addition puts things together, makes sets. The binding associates things with each other. And that's exactly what we want to do with the vision and the control. We want to bind them together and make one thing so that we can predict. There are various ways to do this implementation in the literature. As you see here, we focus on the binary vectors, but for which Canerva introduced a framework. The distance between those vectors is given by Hamming, the Hamming distance, and you can, using permutations, you can create sequences, right? And using these operations, you can create records and so on. So basically, you can do anything with this framework. And what we are attempting to do in my lab is work computer vision again from the ground up by addressing the fundamental vision questions, but now in this framework. Okay, so we would like to apply this theory to a very simple problem, let's say an ego motion problem, in order to understand the basic principles, because every other problem will be addressed in a similar way, because solving these problems, learning in this new framework, amounts to developing the appropriate memory so that you can probe it. So, as Davide talked about, we are going to use an event camera, as you see here. And we have a reason for this. Besides, of course, all the reasons that Davide showed that we should be using these cameras, they are also having sparse information. And remember, what we would like is we would like to start from images and videos and translate them to hyperdimensional vectors. And we can do that for event images. We cannot really do it yet very robustly for RGB images. Okay, so we use that sensor, and I won't tell you much. David's introduction is very good for what I want to say, and in the past few years, we have been developing in David's lab as well several approaches on how to analyze the local movement given a DVS sensor. And here you see one example where you can basically, by taking many of those events over time, we can create an image like this here on the right that shows basically the movement, the normal flow. And so what we would like to give to the algorithm as input is images like that, okay? And we would like then to generate hypervector representations for numbers, okay? This is not very hard. So suppose you have a range, then you generate random representations for X and Y of length L, and then you create n bins by randomly changing L over 2n bits of X into Y's bits where they differ. So this shows this is X to Y. Okay, and see here you can see a heat map of Hamming distances between integer quantities. Now to encode an image as a hypervector, you got to choose random permutations for rows and columns, because by applying this permutation r to the x, c to the y for rows and columns, you can basically bring this pixel over here. So basically the image, by following this logic, is going to be the exclusive OR sum of all the pixels. So let me give you a heads up. If you run a CNN on an example autonomous data set of time images, then you will get about 7 centimeters per second accuracy of magnitude of echo motion at the state of the art. And we're gonna get 9 centimeters per second accuracy with this technique. However, we have 270 times compression. Okay, so basically we get data from the event sensors. We create those images that I told you, and we turn those images into hypervectors, and then we associate that image with the actual velocity. Let's say velocity in the x-axis, in the y-axis, in the z-axis. Okay, let's say in the x-axis here. And so you can represent that with lots of bins. And then you create an exclusive OR of those guys. So you bind them together and you put them in memory. Okay, so you create hundreds of velocity bins represented by hypervectors. You collect time images corresponding to each VI, which bin, and now you form the memories, and the memories are the bundling of those images, exclusive OR with the bin, and a bundling. You put them together, and this is your memory. And now when you have a new image and you want to find the velocity, what you do is you compute the exclusive OR with that memory, exclusive OR with every bin, and you get the result which is closest to 0. Okay. So here is some examples from data sets from self-driving cars, and you can see at the bottom how well the computed result tracks the ground truth. So here is again results from data sets in the self-driving cars, and you can see at the bottom there are various measures on how the technique is doing. And a takeaway from this is, the training time is minimal. There is a massive speed up of inference time to predict the motion, and can be trained further, be trainable on the fly, and requires a fraction of training data for optimal performance. Okay, and you can use different techniques here for translating the images into a hypervector, but then you can combine them, and you can get, because if you have a hypervector using this technique, a hypervector using this technique, and a hypervector using that technique, then what you can do is you can bind that hypervector with some identifier, a random vector that identifies this guy, and so on. And so to summarize the technique, this is a general learning strategy where you build this memory hypervector and then you match it so that you can do any kind of recognition. Start from training images. Here we have used a hash network to produce the hash values, and then you bundle them together. And then you bind them with the identifier of the thing they represent. And then you match. And you solve your problem of inference or recognition. Okay, so far, hyperdimensional computing has been considered as like a fringe application where you do applications on the edge computing, where you have to do something fast, cheap, simple, Internet of Things and many other applications. However, it turns out that there is right now an exponential explosion in the publications in that arena because there's many interesting things that you can do using this. So for example, what is the point? The point is that the memories that we develop when we move around is not just visual. They have both vision and motor together, and they are one thing. So if you have an image, and the image has a number of objects, O1, O2, etc., and each object is at location X1, X2, etc. And this X1 and O1 are hypervectors that describe the location and the content at this location, that is a small window containing the object. Then the image is the sum. And now by doing the composition of the sum, you do segmentation. Now, if you have a sound where a few people speak, like the cocktail party problem, and you want to separate it, you have, again, you have the sum, and each one of the sounds is nothing but the product of particular representations of the sound, like scales, spectrographs, and so on. So you can have, in principle, the same algorithm doing image segmentation and sound segmentation by decomposing these expressions. Okay, so basically, whether you see a dog, whether you hear the rav, rav, whether you see the word dog, they get you to the same vectors. And that is how you solve the integration problem. Because the integration problem in designing intelligent systems is not really addressed. It's always an afterthought. We say, hey, I take your stuff and we take my stuff and we integrate it. And we get $1 million in a grant, let's say. But who said that it's the right thing to integrate my stuff and your stuff? May not be. So the only way right now the different disciplines of AI can communicate with each other is with a level of concepts. So the visual system can say, here's a dog. And so now the visual system can say dog, oh, okay, I have a dog, I have knowledge about dog, and so on and so forth. But by doing hyperdimensional computing, you can communicate at any level, because the notion of signal and symbol, you know, in the older days of AI, we used to worry about signals and symbols. What is a signal? What's a symbol? Where do the signals end? Where do the symbols begin? A hyperdimensional vector is both a signal and a symbol. It's a signal because you can take the Fourier transform of it. You can convolve it with something else. And it's a symbol because you can add it with something else or multiply it. And so these ideas may lead to what we call minimal cognition. That is a system with basic visual capabilities, like the ones that we developed, and Davide and the crew in Holland and other people developed drones or robots with many visual capabilities. If in these ones we add episodic, semantic, and procedural memory, then we get a minimal cognitive system. So this is from Buzaki's book that suggests that navigation started first with odometry, dead reckoning, but then adding images and recognizing landmarks, we started making mental maps. And then the first one led to episodic memory, while the other one led to semantic memory. So this is sort of the beginning of intelligence. And so in our work, trying to make those very small drones that are going to solve problems without using SLAM, but by developing a hierarchy of capabilities like direct stabilization, segmentation, obstacle avoidance, homing, landing, and so on. When you have all this and your system is working, then, and this is what, as it was discussed before, we are developing a RoboBeehive, which is a big drone that has inside small drones and goes and perches on a tree, and out come these little guys that they can perform all these capabilities, plus they can find flowers and touch them and keep going. While they are doing this, they avoid humans, animals, avoid obstacles, avoid each other, and so on and so forth. And so, yeah, these are just some examples of the processes or a pursuit task on how these are calculated. And this is my last slide. That is, when you have a system with basic visual capabilities that has also episodic, semantic, and procedural memory, this is already a cognitive system, and it is small. Now, you can start from the ground up. This is achieving AI from the ground up, because if you make a system that is small and you can understand its workings, then you can keep augmenting it in order to achieve more intelligence. Okay, thank you very much, and good luck in your work. And if you are interested in the RoboBeehive, we are going to do a demo of it within June, before the end of June, and we will broadcast it. Thank you.
Thank you very much, Dr. Yanis. Any questions from the audience? Actually, I have a couple questions. So it's very interesting talk, and I saw in the first part of the talk is trying to generate a very long vector, a very big vector. And later, the key thing to make it accelerated is to generate binary codes using different hashing network. Actually, you have several slides and presenting, introducing the how to make it in binary. And my question is for different resources like image, sound, or motors, whether the hashing network are designed in the same principle, or they are for different images, sound, the hashing is a little bit different than each other.
Yes, the hashing networks, we tried them at a moment of desperation, and the results that they had were different. However, that led us to develop to understand one technique that we can glue together different networks and achieve performance higher than each one of the individual ones. And the way to do that, if you have a deep network, every layer is like a hyperdimensional vector. So if you have a deep CNN, for example, what it does is it starts from hyperdimensional vectors, which is the input, and it keeps transforming it. So what we do is we stop at the end, before the classification, and we take now those hyperdimensional vectors and we form memories by putting them together, and that increases the performance. Thank you.
Yeah, cool. Another question is the binary? You actually at the end of the talk, you talk about minimum combination, and is the binary long binary vector also applied in the minimum combination?
Yes. This is how we are implementing the cognitive architecture. Okay, using hyperdimensional vectors, because now all the modules, the planning module, the visual module, they all use hyperdimensional vectors, and they pass them to each other.
Okay, cool.
So,
actually, yeah.
So you have two kinds of problems here. One is how you go from the signals, the pre-processing, so to speak, how from the signals you get to create these hyperdimensional vectors, and then you bind them, and then you have the post-processing where you have to unbind them and separate them in order to perform the particular action.
Okay. Yeah, cool. Yeah, thank you. Actually, I have a minor question that is not important, but I'm curious. You have in the video, you have one drone's task is to hit another drone's task, is to hit another drone. Actually, I saw the video. One of the somehow you throw the drone towards another drone.
Right.
Actually,
yeah, one drone is chasing another drone.
Okay. How many drones did you break? Did you lab break?
About six or seven.
Very expensive experiment.
6 or 7, but we got smart in the meantime, and we have followed Davide's advice, and we have been doing most of the learning in simulation. So recently we developed a system that learned in simulation how to detect the propellers using event cameras, because the propellers are moving very fast, and we developed a pattern recognition technique, a neural net to recognize them, and all the training we did in simulation. And, it worked like the performance was in the upper 90s in the experiments.
Okay, yeah. Okay, thank you. Thank you, Dr. Yanis. Let's move to the another paper presentation that is actually is Kevin Liu here, or the same group is here?
Yeah, I'm here.
Okay, yeah. Kevin Liu and his and the team from the Institute of Automation of Chinese Automation, Chinese Academy of Science will give the talk about their paper exploring motion information for distractor suppression in visual tracking. Okay, you can go ahead.
Okay, can you hear me?
Yeah, we can hear you.
Please remind me if there are problems of the network. Okay. Okay, good morning. I'm Kevin Liu from Institute of Automation, Chinese Academy of Science. Now it's my turn to introduce our work. The title is Exploring Motion Information for Distractor Suppression in Visual Tracking. The first section is Introduction and Related Works. Generic visual object tracking is a significant and fundamental task in computer vision. Look at the following video. Given the initial state of tracked object, such as a bounding box or segmentation, we need to design a practical algorithm to output the state of the object in the subsequent frames. Honestly, it's hard and has the following three characteristics: class, agnostic, diverse patterns, and real-time. Last few years, the dominant and popular paradigms for visual tracking are correlation filter and semis networks. The former aims at learning to construct a feature embedding space that is optimal for template matching. The latter focus on learning robust discriminate features, usually equipped with online learning. Our works focus on semis networks. So what is a semis network? How should we track our interested objects? For example, suppose we want to track the player wearing green. How should we do? Naturally, we can take the interested object in the first frame as a template and search for the most similar object in the subsequent frames through sliding operation. That means tracking by detection and matching. Look at the following architecture. We crop an interesting area in the first frame with a preset size as template Z. Meanwhile, we crop a larger search area in the current frame as X. Input X and Z into a weight shared convolutional network. Thus, we can acquire two deep feature maps. Then we compute the cross correlation of these two feature maps and find out the position with maximum response value as the position of the tracked object. Last few years, most works focus on designing better backbones to acquire more proper feature. Besides, it's essentially a detector with strong ability for feature matching. It requires brilliant performance on recycle and distinguishable features. Moreover, the cross-correlation operation also has been extended to more effective operations such as depth-wise, point-wise, and automatic operations. At the end of the pipeline, there are two common decision paradigms. One of them is a two-stage method such as SPM, semis RCN, and global track. The other one is Hanning window penalty. The following formula show the final decision equation, which is our focus. W represents the weight factor. S represents the similarity scores. H represents the Hanning window penalty. Its definition is shown on the top, and its 3D surface is shown at the bottom. The center of this window is located at the position of the tracked object in the previous frame. It essentially acts as point-based distance constraint. So what is the motivation of our work? We will show the drawbacks of Hanning window and point-based constraint. First of all, as demonstrated in the left figure, the predicted bounding box marked as blue drift to distractor at the 8AA frame due to ignoring the motion information. If we exploit the motion information to predict a reference box like the red bounding box in subfig 2, we can select the right target marked as green and soft drift problem. Therefore, it reveals that the Hanning window penalty ignores the motion information. Secondly, the point-based constraint is unfair when evaluating the quality of regressed bounding boxes. The dark blue dashed box refers to the reference bounding box. In anchor-based semis networks, the 3 orange dashed boxes are corresponding to 3 different aspect retals centered at P1. Apparently, these 3 bounding boxes possess different IOUs with the reference box, but identical Hanning penalty scores. Besides, the red square P1 and the black square P2 represent 2 positions which have one identical penalty score, but different IOU scores. In summary, the above 2 defects result in drift problem. So how to mitigate drift in visual tracking object? Let me introduce our method. Firstly, we give an overview of our tracking pipeline. The submodule in red dashed box is the same as typical SEMIS tracking algorithms. We employ a SEMIS network to extract appearance features and export the classification score, a score map and corresponding regression boxes. The SEMIS network may not be restricted to a specific architecture. We name this characteristic model-free. Besides, the submodule in the blue dashed box is the core motion module, which can be set as one of the above modules, the Kalman filter or median flow. The output of the motion module is a reference bounding box. Then we use it to calculate IOUs with the regression bounding box exported by the appearance model. We combine the IOUs with the classification scores and select the maximum value together with its corresponding regression bounding box as a final prediction. In the end, we use the final output bounding box to update the state of the target, which is a vital step for the motion model. Notably, our method works with no need for training. Both the motion model and the IOU guided penalty act as an effective post-processing to surprise distractors. Next, we will concisely introduce the first motion prediction scheme, Kalman filter. This scheme is classical for motion prediction and considers uncertainty. It maintains a state vector X and a certain variance matrix P. The definition are shown in the blue bars. Firstly, given the initial estimate X0 and P0, we predict the state and the variance of the next timestamp. Then we measure the current state and update it. The definition of matrix F and H are shown at the bottom. Notably, Zn represent the final bounding box shown in the previous slide. X n plus 1 n hat represent the reference bounding box. Finally, we iterate these two steps during tracking. Next, we will concisely introduce the second motion prediction scheme, media flow. Given the teeth and t+1's frames, firstly, we initialize point to grid in the bounding box. Then we calculate locus canid optical flow to track point. Then we estimate tracking error of these point pairs. We use FB error and NCC error as two metrics which can evaluate the quality of the point. Then we use these two metrics to filter out outliers. Finally, we use the remaining point to estimate and update the predicted bounding box. Notably, this method is prone to fail, and we use the prediction of the Kalman filter as corresponding complement. So how about the performance of our method? We have accomplished many experiments. Firstly, in order to generate the reference bounding box mentioned above, we adopt and compare 4 different methods named PREV, KeyF, Flow KeyF, and Flow PREV. PREV means using the last PREV final output box as the current reference box. KeyF implies using a linear Kalman filter to predict the reference box. Flow KeyF means using Flow KeyF means using the media flow for prediction and switching to KeyF when failed. Flow PREV implies using media flow for prediction and switch to PREV when failed. Meanwhile, in order to combine the calculated IOUs and the classification scores, we explore 3 different ways named add, multiply, and nonlinear respectively. By contrast, Flow KeyF and Flow PREV perform unsatisfactorily, even if with complicated design. We infer the inferior performance of media flow result from the drastic motion of the camera or the target, and it would cause a lot of failures. We infer that by contrast, moreover, media flow essentially cannot model the long-term motion pattern. On the other hand, the simplest scheme add surpass others apparently. We infer that weighted summation is suitable to build the spatial constraint, but multiplication and nonlinear operation weaken the importance of the classification score. In summary, we select the KeyF to predict the reference box and the weighted summation. Secondly, we compare four penalty methods: NP, Hanning, WM, and our novel IOU guided penalty, respectively. NP means the original Hanning window penalty is removed. It acts as a baseline about penalty methods. Hanning represents the original scheme. Hanning WM is another penalty that we fix the Hanning window at the center position predicted by the Kalman filter. For our IOU guided penalty, we select the best scheme determined in the above section. DC, MO, and IC correspondingly represents point-based distance constraint, integrating motion information and using the IOU-guided constraint. Then we compare these 4 methods on last sort and OTB using SAMIS RPN++ and TransT respectively, as shown in the left table. SAMIS RPN++ with IOU-guided penalty increased 8.8% relatively compared with no penalty on OTB. Besides, TransT with IOU-guided penalty increases about 4% relatively on OTB and LASSOT. Notably, our IOU-guided penalty achieved the best AUC and precision score when based on TransT. The results can verify the effectiveness and universality of our method on one hand. On the other hand, in order to verify the effectiveness of our IOU-guided penalty for solving the drift problem, we compare the calculated IOUs with different penalty methods on the cross sequence of OTB and visualize them in the right figure. The IOU-guided penalty can always track the target, even if there are many tractors. On the contrary, other methods fail since the 40th frame due to distractors and drift to a distant position, which violates the assumption of motion continuity. Meanwhile, we compare these 4 methods on the specific background. The IOU guided penalty surpass other methods apparently. Finally, we combine the IOU guided penalty with the Hanning window penalty at the final constraint and compare the performance on several benchmark datasets with the baseline, which only exploits the Hanning window penalty. As shown in the right table, the result achieves the best performance and runs at approximately 40 FPS. Finally, we summarize our works. In this work, we explore the motion information to mitigate the drift problem in visual tracking. Qualitatively and quantitatively analyses imply that the typical Hanning window penalty may not be the optimal penalty style to act as the special constraint. We demonstrate that the disadvantages of Hanning window penalty and propose a novel IOU guided penalty based on the prediction of the motion. We find that the prediction of a linear Kalman filter can surprisingly improve the performance. Notably, our method is cost-free, model-free, and with no need for training. Meanwhile, we believe that the post-processing is too simple to thoroughly solve the drift problem. In future work, we will quantitatively define the drift phenomenon and evaluate the robustness of the algorithms. Thanks for listening. Any questions?
Any questions? Okay, I have a small question.
Okay.
For the common filter and the optical flow in your neural network, which contributes more improvement in the success rate and the precision?
The Kalman filter performs better.
Okay.
Okay.
How much it improves and versus the optical flow? Do you have some number for that?
Okay, I show it in the table.
Okay.
We can see it in the table 1 or the table top table. The Kalman filter performs 0.709, and the optic flow performs 0.690. So I think the results reveals that the Kalman filter performs better than the optic flow method. Yeah.
Okay. Another question from the audience. If there is no further question, we end up the first small session, and we will have a short coffee break, and we'll get together. Actually, it's a little bit late, but we probably need to catch up time. We'll meet up at 10:40, and right now we can have a short break.
Okay, thank you.
Thank you. Hey, Luca, please go ahead. Yeah, so sorry again. I was on extended screen. I couldn't really see the screen very well, actually. When you raised the hand, I didn't see your hand.
No worries at all. Hybrid format is always a bit challenging. So
yeah, because this is a hybrid, and if that is something like totally online, I will duplicate the screen. But later there will be some people who give the talk exactly here. So I was thinking probably it's easier extending screen because the speaker can see in the other screen about the slides and timing.
Right.
So sorry for that.
So listen, if you want, I can try to screen share and make sure that I can do that. So let's see. So at this point, you should see my slides, right?
Yeah, I can see very well.
And I think that's pretty much it. Okay, all right, I will stop it for now. Seems to be all set.
Okay, cool.
Okay, thanks.
Hi, Luca. I think we can get started.
Okay. I'll start sharing screen.
Yeah, let me first introduce you. So it's already 10:40, sorry. Okay. It's our great pleasure to have Dr. Luca Calone to give us a talk to introduce his research. Dr. Luca Calone is the Leonardo Career Development Associate Professor in MIT, at MIT, and he's also a PI in the MIT lab for the information and the decision systems. And he's also the director of MIT Sparklight, where he works on the cutting edge of robotics and autonomous system research. And his research interest includes nonlinear estimation, numerical and distributed optimization, and the probabilistic inference applied to sensing, perception, and decision making in single and multiple robot system. He received 2017 IEEE transactions on robotics, Kim Sun-Fu Memorial Best Paper Award and the Best Paper Award at WAFR 2016. And some of his research has already been used by the public quite a lot. And for example, his group is the main has developed an open library that is quite a lot used, which is called Chimera and for semantic mapping and localization. And today, he will give us the talk to introduce his research on the topic from visual odometry to real-time sensing, to real-time scene understanding, and 3D scene graphs. Thank you, Luca.
All right, thanks for the nice introduction. As Yuju mentioned, I'm Luca Carlone, I'm associate professor at MIT, and in this presentation, I want to tell you about the work we are doing on going from visual odometry and SLAM to real-time scene understanding, and I want to introduce this idea of 3D scene graphs. So the starting point of a lot of work we have done over the last few years is to realize that there is still a large gap separating robot perception from human perception. So for robot perception, we have now excellent systems. We have to be very proud of the progress we made in visual odometry, visual inertial odometry, and SLAM. And right now we have pretty much off-the-shelf libraries that you can download, and you can just move a camera around and build a geometric reconstruction of the environment in real time, as the one that you see here with DSO. And of course, there are many other examples like ORB SLAM and things like that. At the same time, with progress in deep learning, we now have quite powerful tools for semantic understanding, for 2D semantic understanding. For example, at the bottom left here, I'm showing some example of pixel-wise semantic segmentation in which you have to attach a semantic label to every pixel in an image. And of course, there are many other examples, such as bounding box object detection and so on. At the same time, we have to realize that humans are doing much more than that. And to convince you that that's the case, I typically just show an image. By staring at the image on the right as a human, you can parse it for a few seconds, and then you can immediately understand what is the geometry of the scene. For example, there is a road, there are buildings, and so on. You can understand the semantics of the scene in 3D. For example, you can understand the location of cars, and you can understand that maybe a yellow car is a specific type of car, which is a taxi. And you can also start reasoning about the relation between elements in the scene. For example, I don't know, a car is crossing a traffic light, or maybe a pedestrian is trying to cross the street. Okay, so this kind of 3D scene understanding, which is about jointly capturing geometry, semantics, and relations in 3D, is something that is still out of reach for robotics. And it's motivating a lot of the work I'm going to discuss today. But before we even start, the question is, why do we care? So why do we care about 3D scene understanding for robotics? The first answer is simple. 3D scene understanding is key to interaction. If my robot is doing just visual odometry, or doing just SLAM, maybe, I'm doomed to provide geometric instructions. So I can tell my robot, go to position X, Y, and Z. But in the future, that's not the way I want to interact with my robot. In the future, I want just to tell my robot, go grab me the cup of coffee on the table in the kitchen. And for the robot to parse and execute this complex high-level instruction, the robot will need to know about geometry, right? We need to know where is the kitchen. We need to know about semantics. What is a cup of coffee? What is the table? What is the kitchen? And we need to know about relations. What does it mean for a cup of coffee to be on the table and for the table to be in the kitchen? An aspect that I also think is even more interesting is that 3D scene understanding is key to robustness. And I love using this example to convince you that, that 3D scene understanding is fundamental for robust perception. Of course, like, if you look as a human, if you look at this slide, you see a car. But if I show you the full picture from which I cropped the image of the car, you can be confused. You can stare at this image for a few seconds, and then you realize that in this picture, there is no car. Actually, there is a white van, and then the car is only painted on top of the van. And probably your mental process has been something like the following. You've been detecting the ground floor, you've been detecting the car, you've been detecting the van, and then you reasoned on the fact that these two objects cannot be on top of each other. So you reason over the relation between different objects to figure out what is a reasonable explanation of the scene. So in other words, what I'm saying is that robust perception relies on simultaneously understanding geometry, semantics, physics, and relations in 3D. And a lot of the work I'm going to present today is about capturing all these aspects. So I'm going to start by presenting Chimera, which is an effort to capture and to describe jointly geometry and semantics. Many of you have seen Chimera in the single robots case. I'm going also to present extensions to the multi-robot case. Then I will switch to Hydra, which is a very, very recent work and is about building 3D scene graphs in real time, and to me is a step forward towards real-time 3D scene understanding. So let me start with Chimera. So what is Chimera? Chimera is a real-time library for metric semantic SLAM. So Chimera is taking as input standard sensor data from a camera. So this camera is a real sense, will provide the images as well as inertial data. And as output, Chimera will produce a metric semantic mesh model. So what you see here in the video is a 3D mesh. You can see a first-person view or a third-person view and a top view of the mesh here. But each phase of this mesh is labeled with a semantic label. For example, gray corresponds to ground, dark green corresponds to wall, light green corresponds to chairs, and so on. So each color is about the type of object the robot is observing. We proposed this at this point more than a couple of years ago. We have a very efficient implementation on GitHub. You can go and check it out. What I want to do for today is to tell you a little bit about the building blocks of Chimera, and then show you an application which is more recent about applying Chimera to multi-robot systems. So Chimera has three main building blocks. Chimera will start with sensor data, and will apply Chimera VIO, visual inertial odometry. The result of the VIO will be passed to Chimera semantics, which is building a 3D mesh with semantic labels. And then Chimera RPGO, or robust post-graph optimization, will be in charge of correcting the trajectory of the robot and possibly the map in response to loop closures. So let's review briefly each module. The VIO module is a standard keyframe-based visual inertial odometry approach based on GTSM. This is based on an approach which is called IMI pre-integration, which at this point is standard. It is implemented in most of the visual inertial odometry libraries. It's something that we proposed with David actually back in 2015 and 2017. And for those of you who are not familiar with this approach, the idea is that you start with a sequence of camera images as well as inertial data. You extract features from these camera images, and then you solve some optimization problem to figure out what is the trajectory of the robot as well as an estimate of the location of the points seen in the image that you estimate in 3D. So again, this is fairly standard by now. It's an optimization-based or factor graph-based visual odometry estimation approach. And again, this is just about computing the odometric trajectory for the robot. So this is something that will drift over time. This odometric trajectory will be passed to Chimera semantics. So Chimera semantics will take the trajectory and will build a mesh model around the trajectory, as you can see in the video here. So what happens here is that imagine that you have a stereo camera. There will be you're going to construct in Chimera semantics a volumetric grid around the robot. And you can imagine that for each pixel of the camera, you will essentially ray trace the corresponding depth measurement to update a voxel-based map. That standard is actually taken from VOCVALC. What you do on top of that is also to keep track and to Bayesian updates over the semantics of each voxel. So not only we store information about occupancy, we also have information about the semantic class of each voxel. The thing that I think in practice is very cool about this approach, besides the fact that we can get fairly nice maps, is that this approach is running fully on a CPU and can run in real time at 10 Hz on a standard computer. The last module in Chimera is Chimera Robust Post-Graph Optimization, RPGO. So the basic of this observation here is that if you look at just the odometric trajectory, so the robot is starting here and is driving around, odometry will drift over time, right? So we need some loop closure to correct the trajectory. In this case, I'm showing 2 loop closures in blue. And as a result of enforcing these loop closures, we can correct the trajectory and make it globally consistent. So in this phase, like in Chimera, we have a very simple backwards approach for loop closure detection or for place recognition. What we are quite sophisticated about is to be very robust to incorrect place recognition results. In practice, place recognition will produce a lot of outliers, a lot of incorrect matches. If you're not careful about those, you can get a very bad trajectory estimate. Instead, in Chimera, we have state-of-the-art approaches for outlier rejection, and we can get a nice and smooth trajectory estimate in red, while being able to select the few loop closures in blue, which are correct. And these approaches are based on either PCM, which is a very cool approach, it's called pairwise consistency maximization, proposed at TCRA like in 2018, or more recently, our approach based on graduated non-convexity, which works in a great way and is robust to up to 90% outliers in the loop closures. So many of you have already seen, this part of Chimera. This is already, released open source. What I want to do next is to cover a more recent module in Chimera, which is called PGMO. And that is going to be online and released open source pretty soon. Let me tell you what this is about. So PGMO is post-graph and mesh optimization. The idea is that before in Chimera, we are doing just post-graph optimization. So imagine that you have the trajectory of the robot in red, you have the mesh that the robot is reconstructing, and after we have a loop closure in blue, with post-graph optimization, we can correct the trajectory of the robot. But that's not ideal, right? Because if you correct the trajectory of the robot, but we don't correct the mesh model will keep drifting, okay? Indeed, instead, what we want to do is to correct at the same time both the trajectory of the robot and the 3D mesh in response to loop closures. And that's something that we've been working on, is something that is summarized in the journal version of the Chimera paper. So we propose essentially an approach which is able to simultaneously deform both the trajectory of the robot and the 3D mesh in response to loop closures, and it's a quite fast approach. So this is based on an idea from computer graphics. It's an old idea from computer graphics, which is called embedded deformation graphs. So what you do here is you have the trajectory of the robot, you have the mesh. What you do is you attach local coordinate frames to the mesh, which are these ones in violet. So each triangle here will correspond to a pose. And then you connect with edges, you connect nodes in the mesh, which are co-visible by the cameras, as well as you connect nearby frames on the mesh. And then what you do, you solve a joint optimization problem involving all these poses such that you can enforce a loop closure, again, the one in blue. Okay, so the result is that you deform at the same time both the trajectory of the robot and the 3D mesh. And not only we do this, but we also show that mathematically, actually, the embedded deformation graph approach under simple assumptions, can be formulated as post-graph optimization, which is a very well-studied problem in robotics. So you can just use state-of-the-art libraries such as GTSM to solve this kind of problems very quickly. So this is a little bit the pitch of the idea. Let me show this working a little bit in practice. So imagine that the robot is starting at this point, is traveling around, and what you see is a top view of the map that the robot is reconstructing. So that's a mesh model reconstructed by Chimera. As soon as the robot is coming back to the original location, a loop closure is triggered, and this post-graph and mesh optimization will correct at the same time both the 3D mesh and the trajectory of the robot. You see how powerful is the approach. Essentially, this small correction will propagate across the entire mesh up to this point. Okay, and in practice, this approach will just translate in more accurate maps, right? You can refine the map in response to loop closures. So these will result in more precise maps. For instance, on the right, I'm showing a trajectory, a map reconstruction with Chimera. This is before using Chimera PGMO. And this is the reconstruction color-coded by the error. So you see that the errors are actually pretty large here. If you look at the corresponding reconstruction color-coded by the error after Chimera PGMO, you see that the errors are largely reduced. So loop closures can just help the 3D reconstruction. So just as a summary, Chimera is a library that we release open source. In this slide, I'm kind of summarizing, I think, the things that are unique to the library. The first is the capability of doing a metric semantic reconstruction pretty much out of the box. The second one is the high robustness to wrong loop closures and the robustness in general of the SLAM solution. The third one is this capability of doing post-graph and mesh optimization, in which you can correct the map on the fly without too much computation. And in general, like, something that stands out for Chimera is that the code runs in real time thanks to an efficient multi-threaded implementation. And we can actually run easily, like, the library on embedded computers, such as the NVIDIA TX2, NVIDIA Xavier, and so on. So the PGMO, the post-graph and mesh optimization, is not in the public version of Chimera yet. We are planning a release 2.0 shortly. So hopefully all the modules I'm presenting today will be available to you on GitHub. In the second part of this discussion about Chimera, I want to tell you about recent work we've been doing about extending Chimera to multi-robot systems. So this is what we call Chimera Multi, which is a distributed approach for metric semantic SLAM in multi-robot systems. So what's going on here? You have three robots navigating, in this case, in simulation. The robots are navigating in a completely unknown map. And as they go and navigate, they are building this 3D metric semantic mesh model of the map that you see on the right. So the trajectories of the robot are barely visible, are the one in yellow. And these that you see is a mesh color-coded by semantic labels, such as building, grass, dirt, and so on. So here, not only each robot is applying Chimera to reconstruct the 3D mesh, but also when the robots are meeting each other, they're establishing some loop closures within the robots, and they are correcting their own trajectory and the corresponding mesh. And the result is that you have this large-scale map built in real time by a team of robots. Let me tell you a bit about what's in Chimera Multi, and then I'm going to show you an example of this working on real system, on real robots. So what you see on the left here is an architecture of implemented by each robot in the Chimera Multi team. So essentially, the robots are collecting sensor data, and then they're using Chimera to process the sensor data, Chimera VIO for the odometry, Chimera semantics to build the mesh. The thing that is unique to Chimera Multi is the distributed loop closure detection and the robust post-graph optimization module. Because in this case, since there are multiple robots, each robot will chat with the others in the team, according to this symbol, like, for Wi-Fi communication. And essentially, the robots will chat with each other in order to find loop closures, and in order to use these loop closures to correct their trajectories. So how does this work? By the way, I hope you're not hearing, like, too much noise in the background. Actually, I have the fire alarm going off at this point. I think it's not. I think you cannot hear it. Hopefully. So the way Chimera Multi works is that imagine that you have two robots, alpha and beta, The robots will have keyframes along the trajectory. It will compute a bag of words vector for each keyframe. And then the robots will keep exchanging whenever they are in communication range. They will keep exchanging this bag of words vector. And whenever they find a match, they will start exchanging also a little bit more information to compute relative poses corresponding to potential loop closure opportunities. And then they will run a distributed post-graph optimization approach to correct their trajectories. It's a distributed approach in the sense that we are very careful in using these distributed optimization protocols here to minimize the amount of communication between the different robots. So we've been testing these on real systems for a while at this point. This is one of the tests we have been doing. We have 3 robots, robot 1, 2, and 3. And in this phase, you see the trajectory estimate from Chimera Multi. This is a real test at Medfield, in Medfield, Massachusetts. Of course, the satellite map is not known. The robots do not know anything about the environment. What you see about this test is that as the robots go, the robots are estimating their own trajectories. The odometry is drifting quite a bit, but thanks to the loop closure detection in Chimera, essentially whenever the robots are meeting each other, they can correct their trajectories by applying and enforcing loop closures. And the more the robots meet, the more the map gets, the trajectory estimate gets more and more accurate. And eventually the trajectory estimate matches pretty well the satellite map. The second part of this video is showing instead the mesh reconstruction. So in this case, the robots are not only estimating their trajectories, but they're also estimating a local mesh. And the video is showing the same idea. When the robots are meeting, they are establishing loop closures, and they are correcting not only the trajectory, but with this idea of post-graph and mesh optimization, they are also correcting the corresponding 3D meshes. So as we approach the end of the video, the 3D mesh of the environment will get more and more accurate, and will be like quite nice representation of the environment. And again, all of this is running in real time. Let me give you a little bit of quantitative results just to tell you what are the main features at the end that we like out of Chimera Multi. So for the tables on the left, you see the trajectory errors. So this is number of meters of error in the trajectory for each robot for different experiments. So first of all, you see that the trajectories are fairly long. We have hundreds of meters to kilometers trajectory. Here you see the column corresponding to the errors in the VIO. Chimera VIO has a decent error, but in this case is quite large. So trajectory errors in the order of up to 10% of the trajectory, I would say, 5–10% of the trajectory, and which results in tens of meters of error. But after you do Chimera Multi, which essentially is including loop closures, the error just goes down. And the error goes down to centimeters in most of the cases, which tells you how powerful is to include loop closures, in this case, in the SLAM estimate. Of course, in some cases, you do not have loop closures, and you cannot bring the error down, as in this case. Chimera Multi is distributed, so we are pretty careful in having distributed protocols which are saving communication. And indeed, if you compare exchanging raw images against the communication which is involved in Chimera Multi, we have a huge reduction in the amount of megabytes that we have to exchange between the robots. And finally, the last table is about runtime. If you are careful with stopping conditions and so on, the post-graph optimization happening in Chimera Multi is something that happens in a few seconds, which is typically the timing that you see for large-scale post-graph optimization. And indeed, these are quite large post-graphs, right? There are thousands of poses. Okay, so in the second part of the presentation, I want to switch gear and move to more recent work, which is about constructing 3D scene graphs with Hydra. This is work that will be presented next week at RSS, so it's very fresh, and I think it's quite cool. So I'm curious to get feedback and discussion after this presentation. So let me start by saying, what is a 3D scene graph? 3D scene graph is nothing else than a new map representation for robotics. So a 3D scene graph is what you see in the video here. So you have a graph with different layers, such that at the lowest layer, you have a 3D mesh. This is the same as the one that we estimated in Chimera. And as you go up in the layers, you're abstracting the low-level geometry into high-level concepts. For example, you abstract the mesh in terms of objects and agents, in terms of places and structures, rooms, buildings, and so on. So all the layers here are pretty easy to understand. Objects and agents is clear, rooms, buildings are clear. Just for your information, structures are essentially walls, ceiling, ground, and so on, while places are obstacle-free location. Places are location XYZ the robot can go to without hitting obstacles. This is what in robotics is called a topological map of the environment. So more formally, a 3D scene graph is a directed graph where nodes are spatial concepts, things which are living in 3D, and edges correspond to spatio-temporal relations between different concepts. For example, agent I is in room J at time t. The reason why we really like this representation is threefold. First of all, finally, this representation allows to capture relations among different concepts, which is one of the motivations I started from. We want to capture relation within different objects in the scene. Second, this representation unifies typical map representations using robotics. For example, there is a metric map at the bottom, which is a mesh model. There is a landmark-based map in layer 2, and there is a topological map in layer 3. So all these representations, which are common in robotics, they are unified in a single model. And finally, this is an actionable representation for planning and decision-making. In other words, the scene graph contains information about rooms, objects, and relations. So finally, the robot with this representation can parse and execute commands such as go to the kitchen and grab me a cup of coffee. So of course, our research has not been just to define a 3D scene graph, but was focused on defining algorithms to build a scene graph from sensor data. Our first attempt is what is called Chimera DSG, Chimera Dynamic Scene Graphs. And I will just summarize it in a slide. Essentially, what happens here is that we start with sensor data. We build a mesh in layer 1 of the scene graph by using Chimera. Then we take the mesh and we segment out different objects. For example, we cluster all the points classified as a chair, and we fit a bounding box to them. Or if you have a CAD model for the objects, we even fit a CAD model to the set of points. And then what we do is to build a skeleton, a graph of places, or a skeleton of the environment, and segment out the different rooms in the environment. So the way this is done is to, in Chimera, I mentioned that there is a volumetric voxel-based representation being built. These approaches for layer 3 is taking that voxel-based representation and is computing what is called a generalized Voronoi diagram. And the result of that is just a skeleton of the environment that you see being in red. And from that skeleton of the environment, we cluster the different rooms in the 3D map. And finally, in the original proposal for Chimera DSG, we also had, let me go back for a second. We also had this nice capability of tracking humans actually moving in front of the camera. So not only we could reconstruct the 3D map, but we could also reconstruct 3D meshes of humans in real time and tracking these models over time in the map. So this was pretty cool. And indeed, with Chimera DSG, we were able to reconstruct already 3D scene graphs of fairly large indoor environments as the one that you see. Now the video is going to zoom in on layer 2, where you can see clearly the different objects, and you can also see the humans moving around. So we're very excited about that, but unfortunately there is a catch here. The catch is that Chimera DSG was running in 30 minutes, so it's not really something super useful for robotics. It's too slow to be useful for robotics at that point. And there were a couple of challenges towards real-time performance, which I'm summarizing here on the slide. The first challenge is that, as I mentioned, the original version of Chimera DSG was building a voxel-based representation of the entire environment. And then by processing this voxel representation, was extracting rooms, was extracting places, and so on. Unfortunately, voxel-based representation are not great. Will not scale super well in very large environments. And also doing batch processing on them to extract places and to extract rooms was quite slow in practice. So that's the issue number one. The issue number two is even more fundamental. During online operation, the robot will estimate its own trajectory and will do more and more loop closures, right? We'll do place recognition and loop closures. So the trajectory will keep changing over time. And unfortunately, in our original proposal, for each change in the trajectory, you had to reconstruct the scene graph from scratch, which clearly is not compatible with real-time operation. So today I'm happy for the first time, to tell you that we have worked and we've been showing that indeed it is possible to build a 3D scene graph in real time from sensor data. And the corresponding approach is what we call Hydra, which is again an approach to build a 3D scene graph in real time using camera information and inertial sensors. So in the video, let me play this again. Imagine that the robot is starting in a completely unknown environment, is building layer 1, which is the 3D mesh as it goes, but at the same time is also reconstructing its own trajectory, is reconstructing a constellation of objects in the environment, is reconstructing a graph of places, which again is a topological map of the environment, and is segmenting these places into rooms, buildings, and so on. So there is a lot to unpack here, but I think that there were a few insights that I'm going to tell you about in the next few slides. The first insight was that to extract the graph of places, there is no need to really post-process a voxel-based representation, because essentially what we realized is that a generalized Voronoi diagram, a generalized skeleton of the environment, can be actually computed on the fly as a byproduct of the integration of the voxel-based map. So actually that can be done for free, which is great. And second, we developed fast approaches for room segmentation, leveraging techniques from community detection. So essentially we show that it's possible to segment the graph of places into different rooms in a very efficient way. And in general, we show that there is never, you never need to reconstruct a huge voxel-based representation of the map. You can just build a local voxel representation of the map and then slowly transform that into a scene graph. So we never store a big volumetric model here. So let me tell you in one slide what is an opportunity that we also realized about when preparing Hydra and so on, another opportunity that we realized. The opportunity here is that when you start having this scene graph, you can start seeing that there are opportunities even for place recognition, right? So in this slide, I'm going to present the work. Again, it's part of the Hydra paper about developing hierarchical descriptors for loop closure detection. So the basic idea is that while in standard place recognition, if you want to compare two different places or two different images, you look for the visual features. If you have a 3D scene graph, you have much more information that you can use. So you can ask to compare two places, you can start asking questions like, do the places have similar objects in the neighborhood? Do they have a similar topological map? Do they correspond to the same room? Do they correspond to the same building? So you can start having a richer model that you can use for place recognition. And indeed, what we've shown is that we can define these hierarchical place recognition techniques in which imagine that you have to compare two different places in the map, this one and this one. You can start having a comparison at the level of places, objects, and visual features. And if any of these is matching, you can compute a loop closure hypothesis between the two places. And in practice, we just noticed that with this hierarchical approach to loop closure detection, we just increase the number and quality of the loop closures we detect. So let me just stop for a second telling you about this figure. This figure corresponds to the number of detected loop closures and shows on the x-axis the corresponding translation and rotation error. And in orange and red, there are standard bag-of-words approaches, so something very simple. Bag-of-words approaches with different configurations, while the one in blue is the type of loop closures that we can get from the scene graph. So essentially, you can see that we can get way more loop closures, and the loop closures have a relatively small error, so they are also high-quality loop closures. So in this slide, I will tell you about, first of all, real examples of deploying Hydra on real scenes. So this is an apartment building near MIT. What you see are the images on the top left, and you can see a 3D scene graph reconstruction here, and the corresponding top view here. So first of all, in the first part of the video, I just want to show you that the room detection just visually makes sense. For example, you see that this room is in blue, this room is in orange. So just visually, this makes sense. But then I want to show one last feature of the 3D scene graph construction, which is what we call 3D scene graph optimization. So I told you before that with Chimera DSG, every time there is a loop closure, you have to regenerate the scene graph from scratch. Instead, what we show in this in Hydra, we show that if you have a loop closure, you can actually solve an optimization problem, which is what we call 3D scene graph optimization, and you can correct all the layers of the scene graph. As you typically do in SLAM, you can correct all the layers of the scene graph to correct for the loop closure. And I'm going to show you this example in this video. So here, imagine that the robot is going on the first floor, then it's going upstairs. This is the second floor. And you see that there is quite a bit of a drift, right? So the robot, since again, we're using odometry, visual inertial odometry, the robot is drifting. But as the robot goes downstairs and comes back to a location that's seen before, there is a detection of a loop closure. And there is this scene graph optimization approach, which in one shot is correcting the entire scene graph. And after the correction, you can see that the top view of the scene graph actually looks pretty accurate. It's already a fairly large experiment with a couple of floors and so on. But you see that now we do not have to regenerate scene graphs. We can just correct them as we collect more information and loop closures. Last thing I want to showcase here is that we're having some fun at this point deploying Hydra on a real robot. This is probably one of the first experiments we did. It's very preliminary. It's not even in the paper. But essentially, we're using the A1, Unitary A1 robot, which is this quadruped. The robot is going around. We use standard off-the-shelf 2D semantic segmentation, and we're using Hydra to reconstruct the 3D scene graph of the scene observed by the robot in real time. So here you see that we have a decent 3D reconstruction. It's not perfect. It's not photorealistic. It's not like, you know, as accurate, but it's still like, you know, pretty good 3D reconstruction. We can estimate the trajectory of the robot. We can segment out rooms, buildings, and so on. But more than the accuracy, for which there is still like, you know, some work to do, I think these are preliminary results. What I'm excited about are the timing results in the table here on the right. So these are the timing results of running Hydra on Xavier NX, which is a small credit card-sized computer. And you can see that we can reconstruct most of the places in the scene graph in a matter of milliseconds, thanks to a very parallelized and a very optimized CPU-based implementation for Hydra. So it's actually feasible to run these in real time on a robot. So the last slide I have is just about telling you about a few other things that I will not have time to cover today, but I think are pretty exciting extensions or opportunities provided by 3D scene graphs. So today I told you about Hydra, which is an example of spatial perception system to build 3D scene graphs from sensor data. But now that you have this capability of building a 3D scene graph, you can do much more. For example, you can start infusing common sense knowledge in the way you reconstruct the 3D scene graph. Let me give you an example. So as a human, if I tell you that in some room, these are the objects found in some room, there is a bed, there is a book, there is a clock. Probably as a human, you can infer that, you know, if there is a bed, most likely that room is a bedroom, right? It's not going to be a bathroom, it's going to be a bedroom. So we want to infuse the same type of common sense knowledge for our robots. And indeed, in our new RIPS paper last year, we proposed this idea of neural tree, which is a new architecture for graph neural networks, which is able to do this kind of inference and populate missing labels in the scene graph. So in the scene graph, we might know that there are rooms, but we might not know if a room is a bedroom or a bathroom, for example. With this neural tree idea, we can also populate these missing labels. And at TICRA, a few weeks ago, we've been also showing that the 3D scene graph representation is actually very powerful for reinforcement learning-based navigation, and in this case, searching for objects. So I'm not going to present today, like, you know, I'm going to wrap up, like, you know, the talk here. If you're curious about the neural tree idea, we're going to give a tutorial a tutorial tomorrow on neural tree at the Graph Machine Learning for Visual Computing tutorial at CVPR. So in conclusion, what I argued here is that there is still a large gap separating robot and human perception, and we need to go beyond visual odometry and SLAM and think about real-time 3D scene understanding. I provided Chimera as an example, an early example of performing metric semantic SLAM, and I also discussed about this idea of post-graph optimization. post-graph and mesh optimization, as well as extensions to the multi-robot case. I also argue that 3D scene graphs are a powerful model for representing 3D scenes and in general for the future of robot perception. And I was very excited to present Hydra, which is the first system to create these 3D scene graphs from sensor data in real time. So we'll close here. Of course, lots of credits. All the credits goes to my students and postdoc, which I'm listing at the top of the slide. I want to thank the sponsors supporting this research and to thank you for your attention. Hopefully there will be some time for questions.
Thank you, Luca. Any questions from the audience? Yes. Do you want to come here to? I'll go here.
Yeah, I have a question. This is Yannis Alimonos.
Hey, Yannis.
That was an amazing talk, Luca.
Thanks.
So thank you. Now, regarding places, it is very clear that the scene graphs are very successful. Now, I would like to concentrate on a situation where you have, let's say, a table in a room, and on the table, you have many objects that are placed on top of each other. Okay, I would like to ask for your experience, if you have done experiments like that, how successful you are in segmenting those objects so that you can make the right scene graph.
It's a great question, Yannis. I think there are, I can answer and then I can tell you, what needs to be done here, because, here we're scratching the surface. There is so much work to be done. But what happens, when you construct the scene graph and when you start from the bottom layer of the scene graph, is that we use Chimera. So essentially, what Chimera does is to take a 2D segmentation, 2D pixel-wise segmentation of each image, and to fuse the corresponding segmentation in the volumetric map. So the answer is that if your 2D segmentation is able to pick all these objects, the map will look correct and the semantics will be nice in 3D. If your 2D network is not good, you will not be able to do that. In practice, just to give a very practical answer, Chimera is more tuned for navigation tasks. So because of the size of the voxels and so on, I'm expecting this will do quite well in navigation tasks and large environments. You will need to do something on top of what we do to handle small scenes or tabletop scenes. Okay. Maybe you have to think about more varying resolutions and so on. Just because of the size of the voxels, I think you will have a bottleneck there. And again, as I mentioned, the other bottleneck is to make sure that the semantic segmentation is able to capture the objects you want. To be honest, I was not super happy. If you look at the videos in this presentation, whenever I use a state-of-the-art network for segmentation, the results are nice, but they're not perfect, right? So what we are starting to look into right now is more of adding a little bit of self-supervision or self-training on top of these to get nicer semantics instead of using off-the-shelf approaches.
Okay.
Also, as a more fundamental answer, just to tell you about what's missing here as well, is that a lot of what we do for scene graphs right now is bottom-up. Is bottom-up reasoning, right? We start from the sensor data, we abstract to the mesh, we abstract to objects, rooms, and so on. You are an expert, also on the neuroscience aspects, and you know that there should be some top-down processes as well informing perception. We are trying to figure out how to include those. We do not have a good answer to that, but I think it's something that is needed. For example, I would like for if the pipeline knows that we are in the kitchen, we have priors about which kind of objects are in the kitchen and what is the shape of these objects. And that's kind of a top-down flow of information that we are not able to capture right now.
Very good, very good. Also, you could, in principle, interact with the scene. Since you have a robot, you could put your hand, and move objects around to facilitate the segmentation.
Indeed.
Like a human. Like if I show you a table and I have 10, 15 objects on top of each other, and I ask you questions about those objects, you're going to put your hand and start moving things around so that you can see better. Very good,
Indeed.
Luca. Thank you.
Thanks, Yanis. And last thing I want to mention, I will have to take a closer look at the work you guys are doing, because another question we are looking into. So if you see at the top of this scene graph, I'm putting a bunch of symbols, right? Rooms, buildings, and so on. These are all symbols. We are thinking about what's a more grounded way to establish the symbols we want in a scene graph. And I think your work, is also very informative in that sense. So I will follow up about that as well.
Great.
Thanks.
Hi, Luca. My question is regarding the loop closure part. So you are showing a loop process at a hierarchy level of the higher levels of the map, and then all the semantic maps. I was just curious as the trajectory and the streams get larger and larger. Will you get to a point where it's unreached all these
Unfortunately, I cannot tell you. I understand the hierarchical loop closure part, but I cannot tell you at all. I don't know if you can get closer to the computer, or somebody can repeat the question, maybe.
My question is regarding the loop closure part. So you are showing adjustment to the trajectory and the metric semantic maps at a very hierarchical level of doing it in different levels of the map. I was just curious, since these maps and trajectories are quite big, do you at some point get to a level where it's unrealistic to do loop closures because the map is so big and the trajectories are so big? Is there a fundamental limit on the size of the metric semantic maps you can store in a scene graph, or the trajectory that you can optimize in terms of a loop closure? That was my question.
That's a great question. Could take 30 minutes to ask that, because there are so many things to say. But let me start with the basics. So what happens right now is that with these kind of scenarios, again, these are hundreds of meters. Each corridor is hundreds of meters. Is not a huge but a relatively large environment. The optimization takes probably around 10 to 15 seconds. And again, everything is multi-threaded. So the frame rate threads will remain frame rate, but in the background, you will have this slow thread, which is doing the optimization. The nice thing about what we propose in Hydra is that essentially we frame scene graph optimization as a standard post-graph optimization problem, which means that now you can start using all the tools from traditional SLAM to solve that problem more efficiently, right? And if you go back in the SLAM literature, you will see approaches for hierarchical solvers. You will see approaches for sparsification. You can start having access to all these tools to make computation faster. So I think the problem is exactly like SLAM, in the sense that the complexity of the optimization will grow over time, but now you have access to all these heuristics to break it. In the scene graph case, I think there is an extra opportunity, which is now that you have this hierarchical representation, you can start thinking about what's important to store, right? Maybe if I'm traversing an entire city, my robot is traversing an entire city, I'm not interested to store a very accurate mesh of the city, right? I'm just interested in storing the fact that there are buildings, there are certain objects I care about. So you can start pruning portion of the scene graph for things that you do not have memory to store. And you can focus your computation and storage of things that you care about. So there are new opportunities in again, making storage and computation more tailored to what you want to do with your robots, and also to make computation more hierarchical, right? Instead of optimizing the low-level mesh, maybe you just want to optimize the location of buildings in the map. I hope that answer. Of course, these are all things to be explored, in the sense that right now, as I mentioned, we just do post-graph optimization. It takes around 10, 15 seconds to do this. So all the things I'm saying are future work, and I see plenty of opportunities there with these kind of hierarchical representations.
Go ahead.
First of all,
Thanks.
I would like to say thank you for a great talk. Very interesting. And I have a question regarding how Hydra deals with a dynamic environment, because that wasn't quite clear to me.
So I'm hearing that the question is about dynamic environments, right?
Yes.
Yeah. So it's a great question. I get that question a lot. It seems that that's one of the big questions, or the big opportunities for this kind of representation. Then we don't do much about that. You saw that there is, we do something clever about humans moving in the scene, because we know that the humans are typically moving over time. What we do in the slides I presented is we avoid integrating the humans as part of the voxel-based representation, which is something that is very standard at this point. And we instead track these dense meshes of humans moving over time. So that's what we have. We consider humans as moving objects, and we're careful about how to handle them, but we don't do much about objects. At the same time, I believe that this kind of representation makes it quite easy to think about moving objects, because again, we have a representation which is this colored mesh, which is quite easy to break down into different objects and to have even objects moving with respect to each other over time. So I think the representation is just right for that. But we haven't, we haven't done much in terms of reasoning over moving things or tracking moving things.
Yeah. I have a question from the online audience. It's great to see quite a lot of questions, but we need to run up quickly because there is another one speaker coming up. But I want to Luca, can you give some quick answer for this question?
So the question is about
what would be your opinion about reducing data redundancies in the scene graph? Seems like the scene graph would grow very large to large scenes and buildings, etc., etc. But many features, patterns, objects are repeating. Can this be utilized to obtain a reduced representation? And actually, there is something like similar, very close to this question. That is, I can see also related to Yanni's question, and I can see there are quite a lot of noise could be from 3D segmentation, semantic segmentation. And how do you deal with the noise? And also related to this online audience, and how do you process these kind of redundant scenes?
Yeah, it's a good point. For redundant scenes, I have maybe I can tell you about the experience we had so far with that, which is really about redundancy. So what happens here is that if the robot, for example, in the video here, when the robot is coming back to a place it had seen before, we'll keep mapping, right? So we'll keep building a mesh. I'm talking about this part in which the robot is revisiting the place and is building again a mesh. So in that case, there will be a lot of redundant information about mesh, portion of the mesh which are re-observed again. We don't do much about that. We have an approach in the paper to remove the redundancy, that redundancy, but at the same time, we want to store both. We don't want to throw away information because, again, we are very careful about outlier rejection. So maybe something that looks like a good loop closure and an outlier at some time may turn out to be an outlier later on. So we are careful about storing enough information, even if it is redundant, to make sure we can correct mistakes as we go. So that's one answer. If I have to think about large scale, very large scale mapping, my answer will be the same that I gave before. Rather than worrying about redundancy of information at the level of the mesh, I would think about pruning this representation just to keep layers that you care about, for example. So that would be my answer. Of course, there are other things that you can do. For example, if you have a mesh representation, you can start doing mesh simplification or standard techniques from computer graphics to reduce the amount of memory or the amount of storage that you have to invest. So there are multiple opportunities, but so far, we haven't done much about those. And I think, Guyu, I think your question is more about the quality of the semantics.
It's about noise. Yeah,
the noise in the semantics. Yeah, I think that's rather bottleneck. And again, we were optimistic about using the best semantic segmentation out there, but that optimism is getting is translating into very noisy reconstructions at the end. So we were thinking about fixing that part in two ways, which I mentioned in the previous answers. The first one is to think more about self-supervision, so replacing standard networks with something that can improve and refine the quality of the segmentation as the robot goes. We're going to put a paper on arXiv very shortly about that. And the second answer is what I was telling Yannis, which is top-down reasoning, which means the following. If at some layer in the scene graph, is telling me that a portion of the mesh corresponds to a chair, ideally I would like to enforce that the corresponding portion of the mesh has the shape of a chair. So that kind of top-down reasoning that can improve the quality of the mesh is something that would be nice to have. And we do not have a solution for that. I think it's a big question how to do that kind of top-down reasoning in a grounded way. But that would be another opportunity to improve the quality of the segmentation.
Okay, thank you, Luca. Probably there's some other questions. Maybe could you stay a little bit longer to answer on Zoom? I can see there are some people only on Zoom, but we need to line up with another speaker. Sorry for that.
Okay, thanks. No worries.
Yeah. Okay. The next speaker is Dr. Dezhen Song, and Dr. Dezhen Song is a professor and associate department head with the Department of Computer Science and Engineering in Texas A&M University. Dr. Song received his PhD in 2004 from UC Berkeley, and Dr. Song's primary research is in robot perception, network robotics, visual navigation, automation, and stochastic modeling. He received his NSF Career Award in 2007, and he was associate editor of IEEE Transactions on Robotics and IEEE Transactions on Automation Science and Engineering. And he was also a senior editor for IEEE Robotics and Automation Letters. His research has resulted in 2 books and more than 1,200 refereed publications. Dr. Song received a Kayamori Best Paper Award from 2005 ICAR conference. Dr. Song has tried quite a lot of different work and especially on using geometric information to improve the roboticness of SLAM. And now he will talk about his research on the title of a few attempts to improve roboticness of visual SLAM.
Thank you, Goyi, for the introduction. It's a great pleasure to enjoy the talks, and hopefully we can share some of the recent results we have here. By the way, today is also the Father's Day in the United States, and I wish every one of you who are a father a great happy Father's Day. And also do not forget raise a new generation of visual odometry and SLAM researchers. Okay, so can you guys see my slides? I just want to get a quick confirmation. All right, thank you.
Yeah, very well.
Okay, so I'm gonna the good thing about giving a talk in this community is I don't have to introduce how important the SLAM problem is. I'll just go ahead directly go into the topic. So when I talk about the visual SLAM, I try to include the more approach that involving vision as a primary sensor, which including the combination with IMUs or RGBDs and things like that. As long as the visual information is the primary sensor modality, some of the approach we're going to talk about will apply. So a really partial or personal view of the milestones in the visual SLAM since the beginning. This is actually omit a lot of important work done recently. Just give you a historical perspective. It actually visual SLAM live in the joint community between computer vision and robotics. It can be viewed as a branch of the SLAM from robotics, and also can be viewed as a branch of the structural motion in the computer vision domain society. You can see the work covered in both communities from different perspectives. As you can see from here, this involved the earliest work from 1970s. We have almost a half century of the build up toward today. So with understanding of geometry all the way to today's deep learning based method, we are getting better and better in applications. Actually, there's a lot of important work. I probably missed many of them. But a couple of things I really want to mention is by 2017, the visual SLAM work has entered the commercial domain. This is probably before that point, all the work we've been doing is kind of can be considered as the self-entertaining among robotics researchers. We share the result, we're happy about each other's work and the nice demos, but we didn't see that in a commercial product. In 2017, Apple demonstrated the AR kit, which is essentially the first visual SLAM SDK. that only useful in the Apple device, but it's deployed 800 million Apple devices. So it's probably the most successful SLAM source code. But it integrates with many of the contributions from this community. I was very proud of this, and that's also making me thinking, what make commercial development different from academic research? And this is the thing is, okay, so we probably, as academic research, we're not in the position to competing with commercial company in terms of resource and manpower. So gradually I'm thinking, instead of developing a full pipeline with SLAM and integrating a cutting edge technology, probably most of research we should focus on what commercial research cannot address in their deployment, what affecting the SLAM in our performance, or it's the main road barriers when they meet the real world. By the way, I was very aware of the commercial development because my former PhD student Yilang Xu, Dr. Xu, has developed lead the development of ARKit back to the days when he was an employee at Apple, and I think he's also attending this workshop. If I cannot see from here, if you are in the audience, please wave your hand, and he can tell you more details about the progress, how he did this development. So before we tackle the problems, we have to give you a brief review of this traditional SLAM framework. This is actually very low resolution, 10,000 feet view of the how SLAM works, right? So basically you take image from cameras, you extract feature points, and then you can start tracking and matching this feature point using corresponding feature across frames to estimate the camera motion. And then you put a small window of the frames that run things called local optimization or local bundle adjustment, and you output the pose. This is actually the front end, which is often referred as visual odometry. And in a full visual SLAM, you also include the back end, which might not be run in real time, but you can detect the loop. You can perform loop closure and run the global bundle adjustment or global optimization to refine your map representation, and you generate a map or scene recommendation. No matter how complicated it is, but it can be stored either on board or in the cloud to be shared with one or multiple devices, and also can be used to guide the feature matching in the future. That close this very introductory low resolution view of this pipeline. And this actually, the reason I mentioned this, I will tell you where the problem can occur and cause the failure of the visual SLAM. So, well, in fact, we can see a lot of nice demos and showing successful examples, but in reality, inevitably, you will see the failure case of the SLAM. In main papers, we mostly talk about speed and accuracy, which are the focus of the presentation for many of the SLAM papers, but we didn't talk enough about when it fails. The robustness issue, actually the key problem of visual SLAM in application. So if you use camera, you probably know we always limited by the environment, right? So lighting and perspective limitations. When you try to matching image from larger perspective difference, you will have trouble to manage proper matching. You also have different degeneracies when there's motion degeneracy or scene degeneracy. Motion degeneracy means if your camera only perform rotational motion, you don't have a stereo cue. If a scene degeneracy, when you face a larger planar object that block the field of view and you don't really have enough reference to get your the stereo information correct. So you also have scale drift if you run a strict monocular system, and the scale drift can be more serious. We always have to face the uneven distribution of features, and some of them will cause our model really ill behave. And especially you have long corridor monotonic scenes, which is quite common in indoor environment. Actually, quite even in modern buildings, it gets even more serious because people like the building to be very simplistic. If you will visit the Apple's headquarters, you might have seen this type of the things. Also, there's a lot of features in corridor scenes are very close to vanishing point, which make them very, very useless to compute to serve as a landmark for displacement estimation. And later on, we're going to talk about even epipolar constraint itself using the stereo vision cause problems. And they are not very good constraint to use when you compute the camera motion. And even optimization itself can jump into local optima, give you wrong solutions. So those things combined together as a whole will cause SLAM algorithm to fail from time to time. It's not a, it doesn't have the robustness of a human perception because it's strongly rely on a sequence matching. And so how are we going to deal with this? And because, you know, in reality, this is something you cannot run away from. So we have a lot of existing techniques being developed. Even you can open up source code, you can find it. For example, degenerated motion degeneracy, we simultaneously estimate both fundamental metrics and homography, trying to see which model is a better fit, and then we take the best model forward. And you know, if you have more lighting and perspective changes, we do a lot more deep learning based methods trying to find the matching that is using semantic information and things like that. It helps, but it can alleviate quite a bit of problem, but cannot eliminate it. We also have scale drift. This is the place where we say, hey, this is we run into fundamental issues of the computer vision. There's a problem for the error accumulation and the opposite problem, lack of enough constraints. So sometimes we have to say, you know, add more sensors. You know, RGBD sensors give you more actual depth reading. Also, you have IMU to help you find a better initial solution to start with. Those things helps. But we still have a lot of problem exist, and there's still have a lot room for improvement. So which we're going to talk about today. My group has been started this work with focus on robustness issue. The first thing we are taking is looking at the feature itself. This is really the work we started about 10 years ago. The approach we are taking at the time was, instead of using you know, the raw features like ORB, even the most expensive SIF or SURF features, we try to see if I can use features with different types and combine them into a sparse representation. So this is basically a sparse scene representation by utilizing the relationship among features. The idea is actually quite simple. As you can see, it is a building. We try to extract the feature point, line segment, and also vanishing point. This gives us a very sparse representation, and the plans, of course. It's kind of like a scaffolding of the 3D scene. It's not enough, does not require a lot of per pixel rendering, just really the feature space stereo representation. But it's actually can reduce the chance that a single feature that may ruin the entire computation, the outliers, or a single set of features, because you are utilizing the structure within in the features. So the idea is quite straightforward. You extract raw line points and line segments, and then you actually think, okay, how many of this line segment actually belong to the same line? That same line we call ideal line. So we can extend those ideal line to study the parallelism that will allow us to find all the vanishing points. In fact, a typical indoor thing or a human thing dominated by human structure, you will find the 3 vanishing point, one vertical vanishing point, and 2 horizontal, maybe more than 2 if you live in a relatively less structured environment. But this is actually very good index point for us to really put this scaffolding together so we can organize the relationship between all these features. So we can explore the collinearity, adjacency, and also with all those parallel lines, we can establish plans. So we can also establish coplanarity of the features. And this allows us to form this multi-layer feature graph. So multi-layer feature graph, it is a very simple, sparse way of representing the thing. It doesn't have any semantics. Of course, it can serve as a scaffolding for semantics, but at that moment, we haven't really integrated this yet. But it can also exist in both 2D environment or 3D environment. This is a perception-guided scene representation, so it is purely on the geometry side. So definitely, it can be an augment if you need to. But it's the purpose of that time is really trying to really improve the robustness and accuracy of the SLAM at the same time. So of course, you want to incorporate those relationships into the scene reconstruction into the whole SLAM process. So basically, we have to incorporate the cost functions that validate the key point positions, collinearity, parallelism, and coplanarity into the cost function when you do the local optimization and the global optimization. So that allows us to extend the existing framework to a framework like this. So when you're moving the camera, then you have this partial scene recommendation being gradually connected together, give you a more robust sparse scene recommendation. Of course, you solve that in your optimization problem. You get both. You can extend the existing framework using both LB and GBA at different places, and of course we test that in the environment. And it, as you can see in the one I want to highlight is the on the bottom left is really the sparse scene recommendation we established back then. This is actually the work was done almost 10 years ago, so it doesn't really have the fancy segmentation network up at that time. But I think the pure geometry perspectives can still provide insights today about the robustness. So I'm gonna skip the video demonstration for time's sake. You already seen enough SLAM algorithm that works. But we're gonna move into the next part of the work. We're trying to tackle the robustness issue. And another problem we found that that can cause the SLAM algorithm to fail in the robust estimation step. So that itself is still a vulnerable link in this pipeline. So what do we mean? Allow me to really review what is the robust estimation, just for newcomers who haven't really seen this before. A typical framework called the RANSAC, random sample constants. If you want to estimate the geometry relationship, for in this example, it's a 2D line. You want to sample the minimum number of samples. In this case, either A or B at 2 points determine line, or C and D, that's a round sample, and to try to establish a model. When you establish a model, you can use a model, check how many more points we call inlines agree with your model, and using a voting-like scenario to pick up the model with most support. And that will allow you to reject outliers, like in C and D, like it's point C in this case. Of course, if you don't reject them, you'll create results like the one shows in the right figure. This is actually typical SLAM result we see in the multi-view geometry textbook. And this is very important in the process because this model could be the fundamental metrics we're estimating, camera motion, and or could be stereo reconstruction, because this is a wide applicable model in computer vision computation. We call the gold standard method as part of it. So what's the problem when you're computing fundamental metrics? And for those who do not know, fundamental metrics is really encode the camera motion. It's really when you know the camera intrinsics. So problem is, from a two-view geometry, we know that this is actually a point-to-line relationship, not a point-to-point relationships. If I give you a point, XL in the image left view, in fact, you have infinite points in the right view that corresponding to this point. And that means all this will satisfy the fundamental metrics constraint. It's a relatively weak constraint. What's the problem of a weak constraint is it is very easy to find the matches, wrong matches, when you perform inline check. And so if you run this with RANSAC, if with non-negligible probability, you can pick up a wrong model. And you also can find a good amount of inliers if your inlier ratio is relatively low due to the thin challenge. So in this case, in fact, we did a test using the front end of the ORB SLAM algorithm, and we basically pulled out that front end to try to see how many times it's RANSAC can pick up, can fail to pick up the right model to start with. In fact, it still have a failure rate about 1.83%, which is not negligible. If you think about baseline distance of 1 meter, that means every 49 meters, you might run into a wrong initial solution, because that's output of RANSAC is the initial solution for your optimization. That initial solution sometimes may not be recoverable in optimization, can lead you to jump into a local optima, which we're going to talk about that too, that cause a non-recoverable failure in the downstream of the SLAM algorithm. So what are we going to do about this? We're just like, okay, we have to do better than the traditional RANSAC, because it just, this 1.83% is just not tolerable. So we basically modified this. Instead, we call it a robust even a more robust version, or we call it RCME in short. So if you on the left is a standard RANSAC approach. So model instantiation step is the sampling step allow you to sample enough number of the points establish the model. The model verification step, you verify a rest of points, how many of them agree with that. Then you terminate and select the ones that with maximum support. Of course, there's a lot of more probability bounds associated with this. We skip it. But in fact, we did a few modifications on this. We do in the model instantiation step and model verification step, termination step, we add more rigorous statistical based check to improve its robustness. Also make this module be aware in some scenarios, you just cannot find a good solution, and make your algorithm aware of that too. So that's the reason we also have the output for failure in that reported failure. In previous RANSAC, you don't have that. You just take a solution as if it is correct. Here we give you an indicate on this. So how we did this? For example, in the first step, model instantiation, if you're familiar with fundamental matrix estimation, you know that fundamental matrix, we need a sufficient amount of the points correspondence to establish it. Depends on your assumptions on the robot motion model. You could add from 1-point methods to all the way to 8-point method, right? 8-point method apparently is a over-parameterization, but it's a linearized model, so it's really easy to compute. People sometimes just like it, but problem is those over-parameter model may not be good. Sometimes you may not know. So for the over-parameter model, we perform this step called the model quality check. So this model quality check basically just say, hey, assuming all these 8 points you are using, or the number of points you're using are good, they agree with each other. So what is the probability distribution for this model? And when you come to uncertainty, then you put the 8 points back to see if they're within this reasonable fitting to this probability distribution. And then in fact, if they're because it's such a compromise, you will know that the quality of this model is not good. You can reject it. So basically that allow us to, first of all, in the model instantiation stage, you reject a lot of round samples to start with. So that's really, it also speed up the speed of the RANSAC, because you don't choose the low quality model to start with. Also in the model verification stage, if you remember the previous example of the line fitting, that was a simple distance-based threshold. In fact, most rudimentary way of looking at this also using distance-based threshold for, basically look at the model as a linearized hyperplane. You see the point to plane distance, you threshold that using, you're using that threshold as the way to reject a point that as outliers when you select when you count the number of inliers. Okay, but this is overly simplified. So what are we going to go deeper into? This is because we know the point distribution of this the samples used to establish a model, we know the model uncertainty. In the using the model uncertainty, we can establish the distribution. So we can see whether a point is inline or not based on the model uncertainty itself, instead of using a fixed threshold. So that allows us to really pick the good inline set, a more reasonable inline set to support the model. And then in fact, the computation-wise, it's not that much more than the previous simple distance-based threshold. And we also can give you probability bound on that more explicitly if we need to. So at the end, termination step, we also verify how well our model is supported with the current inline set. So that we can do based on that model fitness metric we defined in previous step to look at the average fitness on this. Then we can decide if the best model is still not good enough to tell you there's just no good model. Maybe you should increase iteration. Maybe this is just a very bad thing to start with. At least your downstream algorithm will be aware. So you can either at this step, you can make a choice whether you go back to keyframe selection to pick a different keyframe, or you decide to rely more on IMU. You have a choice on this instead of blindly trust the result from the RANSAC. This is actually one of the advantages of our algorithm. So in fact, of course, after that, you can do MLE-based refinement as part of the standard approach. So to validate this, we actually using, you compare to a lot of common approaches that are trying to improve the RANSAC process. For simulation-based test, we have two ground truths, so we can see our algorithm achieve the best result in both the orientation and translation estimation. The model, really the choice is the best. Of course, the problem we run into is how to evaluate the physical experiment data, because that is very difficult, because all the physical test data sets is the ground truths come from the motion track system, which is also estimated from a standard RANSAC process. So you're not going to compare your result directly to RANSAC, because that would be unfair comparison. So we come up with a different metric. So the metric is, I look at the number of points in the inline set for applying a robust kernel before and after you're applying MLE refinement, to see how many points actually fall out of the optimization after you perform the computation. If many of the points being discarded after the optimization with robust kernel, that means you don't have a good inline set. The previous choice was bad, so that's actually a bad solution, initial solution to start with. So we did that. So we're looking at, we put a threshold, say if it's over 50% trench in the inline set, that means your initial solution is bad, your RANSAC did not give you a good result. And using that as a metric to really monitor effectiveness of the RANSAC, applying to 3 different data sets. The Kitty data set is a typical street data set, and the Eureka data set is a more indoor collective thing, and HRBB4 data set is a typical corridor indoor set. And all these 3 data sets, in all of this, we can find a better performance in the our algorithms. In fact, if you see we have 0% failure rate, part of the attribute is the PQI is the reported failure. So basically we detect all the potential failures. 0.16% case that is reported failure. We know our algorithm knows that we're running into a difficult thing. So basically, as opposed to just blindly use that solution. So anyway, so this is actually the one approach we apply to the RANSAC link, trying to improve this pipeline. Now we'll talk about what else we can do to improve the robustness. So we all know that as you see in Lucas' work and Yannick's work, say we do have a stored map. The map is available either from previous visits or from the other prior information. Especially in autonomous driving scenario, you almost always have a map to start with, because that's the information widely available. In many, even indoor cities, we have CAD models of the building. The question we have is, can you use this information to improve robustness, maybe even accuracy? So that is the work we have done, just called map fusion. So the idea at the time was, okay, well, assuming many smaller robots doesn't have the computation power or energy or the power or energy to carry a LiDAR, but previously the same thing be scanned by a robot with a LiDAR. So we have a 2D, maybe a 3D LiDAR compliant cloud map established from the other robots. Now we have a smaller, much cheaper robot only equipped with camera. Can you utilize the information from the monocular camera and a pre-stored LiDAR map to really improve the robustness and accuracy of your of this process? Okay, so the idea is quite straightforward, but it is trying to see in both representations we will be able to extract the planar objects. In indoor see the plenty of planar objects. Those planar objects can serve as anchor point for us to do map to map matching. Also, we can use that as a constraint to point to plan distance, because most of the same points we extract actually exist on those plans as part of the post-graph optimization process to align the post-graph generated from the image with the LiDAR map at the same time, using the plan as the intermediate landmark that cross both domains. So in fact, we can even prove if you do this, your accuracy will be better than pure vision based method, getting very close to a robot with a high power LiDAR. In fact, it should be better than both if it's done right. And so we did experiment, and the result actually agree with our the theoretical results. We compared at the time, because the work was done before 2017, so we compare with RRB at the time was the state art, and we see that the algorithm was significantly better. Of course, it utilized prior information than the state of art. And we did that for both indoor sets, like kitty sets. And of course, you can see, obviously, it is really good at dealing with the scale drift as well, because you have a plan and all this object, all this prior information to use. And yeah, I will skip the details on the experiment and go into next part of the work. So we haven't really, go into this detail about optimization, but the optimization itself is not just a speed issue. Many people say we can make an optimization faster. It's going to help you with the speed. But I will make an argument also going to help you with robustness, because as all we're very familiar with optimization is the object function we're dealing with. We cannot just simply assume them to be convex. For nonlinear optimization with non-convex object function, it's very likely your solution will fall into a local minima if you only run optimization once with a initial point. But if we perturb the initial solution, to run this with multiple trials, the chance you're getting out of the local minima would be high. That means if you can parallelly, or if you can run this, you can afford to run this optimization framework multiple times, you will have a chance to arrive at a correct solution with much high probability. So that's the thing we are looking at, is how do we make the optimization faster? So first of all, why we focus on this optimization components in this? If you really, take a deep dive of ORB SLAM 2 as an example, you can do that for many SLAM algorithms. You can find optimization, which is highlighted as a local BA, local boundary adjustment. It actually occupies 77.5% of computation time. So you can, this is also the reason you cannot afford to run too many times in optimization. Otherwise, your algorithm will not be real time. And this is a very expensive operation. So how are we going to do this? We have to look deeper into the optimization problem. Here, forgive me, I have going to a little bit of nitty-gritty details about the SLAM optimization problem. So if you look back in the history, this optimization solver is nothing but a variation of a Gaussian-Newton methods that are doing gradient or similar to gradient-based descent, looking for a local minima, go down the hill. Of course, in the in SLAM domain, we have seen work trying to improve that using the matrix sparseness like G-stem, G10 stem, and the G2O and all a series. All this approach has been proposed, trying to develop a customized optimization solver for our SLAM problems. And that's the thing. If you look deep into that, there's still room for improvement. Actually, quite big, because really right now we are looking at just really original problem sparseness, but we haven't really looked at structural sparseness of the problem itself. So to do that, let me explain what is the optimization problem we are solving in the VSLAM problem. If you look at the problem level, you are looking at, for example, your camera on the right side of camera perspective, k-1k, you both share the 3 landmarks. Then it will give you a graph level representation. Is the landmark as a node, camera pose as a node. The edges is really the visibility of each landmark in the pose. You formulate a graph optimization problem by nature, and immediately you go into the very special structure, sparse structure of the problem we're talking about. So here we are really trying to see, if we expand this into a more mathematical details, you can see it really uses camera reprojection model. There's landmark positions in 3D space. And of course, you minimize the cost function, really a reprojection arrow across multiple frames. Maybe it's a local bundle adjustment, it's across probably 5 to 10 frames, depends on your parameter settings. We solve this problem actually in real time, actually 10 to 30 times a second. So it's a very computation intensive. So if you look deeper at this, is the solver itself, if we just simply treat this as a standard nonlinear optimization problem, you have a lot of repeated computation. So why we said this? Okay, first of all, let's look at really the nature of this problem. As all these optimization problems, basically we are solving for the first order nonlinear, the first order optimality condition, which is you take it derivative with respect to object function, and the first order derivative equal to 0, then you get this nice format. Essentially, is ax equal to b, a delta x equal to b. It's a very interesting. It's just a linear equation that need to be solved, right? So every time when we refine the solutions, we have a little increment of data X, but we are moving the candidate solution in this case, and the landmark positions, they're all embedded in this data X, and moving to a different location, and repeat the whole process again and again and again until we find a solution we are happy. So in fact, a lot of computation focused on this computing this sparse nonlinear equation, A data X equal to B. And this particular equation, in fact, we don't directly compute this as A inverse times B because it will be very, very time consuming. In fact, a lot of existing approach stop here by simply using a standard sparse matrix representation of a package to do this inversion. So if you're really deep into this, we're gonna do you have to do a Cholesky factorization, and instead of solving these, you have to solve a sparse version of the problem using these standard libraries. But at this moment, you are not fully utilize the problem structure. It's all the existing like G2O, like GSTEM that stopped here using existing sparse matrix optimization. But we think you can do better. So how are we going to do better? If I look at the LBA process itself, so now if those little crosses are the feature points, we're just using feature points as an example for landmarks, but you could use other features as long as it can be represented as a standard optimization formulation. And then we also use little pyramids of camera pose. At this moment, we have a little LBA formulation with the 4 keyframes optimized. So you can see the solver trying to at this step trying to solve for each of these data X, that data X encode both landmark position and the camera pose. So when we move to a next instance, when new features will be observed, some old feature gets dropped, and we solve the problem again. What do you see? There's a lot of overlapping between these continuous problems, right? The problem is you solve actually a lot of landmarks and posts remain the same. That means a lot of conditions you resolve at the same time. So this is not very inefficient from a computation perspective. You keep it moving, you're still doing the same thing. So it's a lot of wasted computation in these steps. So that's why the LBA is time consuming. You solve still a pretty big problem every time, when every keyframe comes in. All right. So if we look at this process, the really immediate idea you're going to see, can you reutilize the previous computation from its formulation? And we want to catch this and gradually utilize that to save entire computation cost, right? So if you look at that, we will find even a lot of computation, focus on these 2 steps. You have to build this X equal to B clustering, then you solve this. So the idea will become how we reduce number of steps in building this clustering by utilizing previous computation, or can we really also speed up the process of solving these questions? If these two sources lead to the 2 accelerating approach for us to really compute the SLAM problem fast. The first is called graph tuning. You look at the landmarks and the posts and all these figures, and try to reduce the original optimization problem size. You generate a smaller problem by ignore the repeated part, and that would actually, of course, end up give you approximate solution. But in fact, the approximate solution can significantly reduce your computation time. Even we know that even the optimal solution is not truly optimal in our sense, but so why not use approximate if it's good enough, right? If you can save a lot of time. The second step, you modify the Cholesky factorization, get even sparse representation, and get your computation further speed up. All right. So in these steps, if you really look deeper in the estimated parameters in the LBA structure, you can see only a few new ones are being optimized, usually with a very large reprojection errors, and the others are old. Even you change the solution, the change of them when it comes to influence to the objective function value, it's really, really marginal. So you can say, hey, if even I fix those those ages, then we probably won't change the optimal solution that much, at least. So that means I have a ways to look at to really reduce the problem size. So let's just do this over time. It will really save a lot of computation costs. I'm not going to go dive into the details, but I'll just give you this idea. We can look at this and we can sort the how the changes with respect to potential impact to the object function, and select the edges to perform the optimization instead of doing that all of them. So the next step would be for those we have to update. We instead of doing that, using a brute force way, we're going to modify Cholesky factorization, doing ranked update instead of a triangle update. That will give us a much quicker computation as well, that we can gain quite a bit from there. Of course, in this process, we essentially still did a little bit more approximation. And I'm not going to go into the details of this to bother you with all these nitty-gritties, but just give you this idea. We can look at how much each vertex is contributing to the objective functions. We can fix those, those very small contributions to, not really optimize them much, and focus our computational resource on the ones with larger contributions to the object functions in this process. And in fact, by performing the modified Cholesky, we can really reduce the computation a lot. So in fact, it gives us a way to tune the parameters for the solver. You can say, how would you like to make a trade-off between speed and the accuracy? So, and if we can do this, this is actually the rank update process. I'm not going to go into detail for this, but we'll show you the result is if you're willing to trade the accuracy by 4.5%, you can gain 2 times speed. So things like that you can do. And initially, you can even run this as an initialization step for your true optimization. And so you can really get closer to the good optimal solution. And you can turn on the full optimization and get yourself into a better result. You can use this to run on different initial solutions due to its speed advantage. So that's the way you can really help increase the robustness. Of course, this is also possible to be implemented in the future. We're exploring to do a parallel implementation. We can run this low sparse solver on different cores. Then we aggregate them together. It will give us even better solutions. But that's actually something we have to do in the future. All right, so I actually just briefly talked about the 4 pieces of work I've done in the past decade trying to improve the robustness of the visual SLAM. We are a more traditional approach, as you may see. But I think still there's a lot of room here for improvement, and that concludes my talk. For this, I really have thank to my collaborators and grad students in particular, also highlighting Redcard that directly contribute to the work I'm presenting here. Now I'm opening for questions.
Thank you, Dr. Song. Any questions from the audience? Actually, it's a very impressive talk, Dr. Song. You're trying to optimize from really a pipeline is from feature selection, outlier exclusion, optimization. You really is a very impressive pipeline. I have a question to follow up, and you at the very beginning you talk about using the line segment as a kind of feature, and here I want to clarify a little bit. Are you using the line segment as a kind of feature for tracking, or you use the line segment to track the vanishing point and later for the verification part?
Oh, we use that for tracking as well. Yeah.
Okay. Okay. And for tracking, and in the past, and the line segment for tracking, line segment as a feature used to be considered as kind of fragile. And how do you optimize the line segment for tracking here? Do you have some? Can you introduce more details?
You're absolutely right. If you only use line segment, you will have a problem of fragility. So basically, let me go back to that slides. I actually omitted some of the details in that talk. So in this point, I have the mention called adjacency. Basically, we also have the line segment not coming just pure line segment. It also has supporting key feature points. So you can treat the line segments not just defined by its endpoints. It's also defined by the feature points closer to it.
Okay.
Yeah.
Okay. Okay. Got you. And also from the multiple perspectives, and which do you think is you at the very beginning talk about lightning, epipolar constraint, and the repeated patterns, many other things. What do you think is the most influencing factor that is making the current SLAM, especially in traditional SLAM, not in deep learning based SLAM, is failing?
I would say the biggest challenge is the feature distribution. So in fact, if you go into the indoor scene like this, I don't know how much you can do about it, even with deep learning method.
Right.
You have to incorporate different strategies. You have to prepare the failure. The one thing I think we should do is to prepare for the failure, can be able to reconnect at a certain time we can recover. But what I proposing is your scene recommendation should allow the point of a failure instead of one continuous things. Yeah.
Okay, there's an audience on the inside, and continue.
My question is regarding your discussion about incremental updates and making them faster. So we're discussing that. My question is to compare and contrast with something like an ISAM incremental smoothing and mapping using factor. Is your strategy similar or different from the incremental updates using factor graphs? If there is a difference, are there any trade-offs?
I'm sorry, I really cannot hear you. The echo and the sound is really bad from my end, from your end. Couldn't tell. Can someone repeat the question closer to a microphone?
Yeah, my question is regarding the incremental updates and the strategies you shared through pruning for making the incremental updates faster. The question is regarding comparing and contrasting this with something like an ISAM incremental smoothing and mapping using factor graphs. I realize, I mean, is there any similarities to ISAM and works like that, or is there something? I mean, is there a trade-off involved in strategies like this pruning, or is it something similar to strategies like ISAM where factor graphs are used for incremental updates?
Well, at the distance, let me see if I can get your question correctly. You're asking whether the trade-off in the sparse solver made it similar to ISAM, or also what other trade-offs? That's what I'm asking, because I still have a hard time get it.
As per my understanding, ISAM solves a similar problem of, updating your states incrementally based on these overlapping calculations. Since you were sharing a pruning strategy, I was just curious if this is similar in line of work to the ISAM line of work, or is it completely different from?
It's different. So we are doing basically we get into even more lower level of the sparse calculation and doing approximation in the calculation process. As far as ISAM, it still solve the exact problem as the regular optimization does, just using the sparse. The problem in, if you keep in mind, I'm showing these slides. You can see you can imagine one axis being post, the other axis to be Denmark. They are very thin and long metrics, very sparse. Even directly using existing sparse metrics computation, you do have some advantage. So a lot of those existing sparse methods using this, directly use this, can gain quite a bit advantage over this. But what we do is we really start looking into from one optimization problem to next optimization problem. The intermediate result from one optimization problem being applied to next and using approximation to combine it, which is different.
Thank you.
Mm-hmm. Right.
Okay, thank you very much, Dr. Song. We have another speaker lining up. So she's here.
Thank you. Thank you.
Yeah, thank you, Dr. Song. Well, our speaker is preparing. I want to introduce the speaker. Here we are it's our great pleasure to have Dr. Katerina Brachiadaki. She is an assistant professor in the machine learning department in CMU. She received her PhD from University of Pennsylvania and was postdoc in UC Berkeley and Google Research after that. Her research is on learning visual representations with little supervision on combining spatial reasoning in the deep visual learning. And her current research develops algorithms for mobile computer vision, learning physics and common sense for agents that move around and interact with the world. And her work has been awarded with the Best PhD Thesis Award, NSF Career Award, Air Force Young Investigator Award, and DARPA Investigator Award. And she also has multiple awards from Google, Toyota Research, Amazon, UPMC, and Sony Faculty Award. And her today's topic is LiDAR-free bird eye view perception and for autonomous vehicles. Thank you very much, Dr. Sijo.
So the slides are not visible now because we stopped screen sharing Zoom.
Okay. Stop sharing. Oh yeah, I can stop sharing.
I think if you're in the Zoom, you can just use this because this none fits with my laptop. So so thank you very much for your invitation. And I know that we're a bit of schedule, so it's going to be, I'll try to make it much shorter. So I want to discuss with you a recent work we have on using multi-view cameras around the car for bird's eye view perception for driving. So based following up on the topic before, right? We have the world is in 3D, the images are in 2D. A big part of perception is how do we go from incomplete observations to complete 3D scene representations. And our solution, one of our solutions the last 2 years is what if we directly in an end-to-end differentiable way go from the 2D image to a 3D feature one. Okay, so this is very different than traditional SLAM pipelines where where the images which we try to stitch together and find correspondences. What if we directly using neural networks take 2D images input and spit out a 3D feature grid? So whatever you see here, this cube. So what is this cube is like X. It has 3 spatial dimensions, X, Y, and Z, and has 1 feature dimension. So it's like a featurization of the 3D scene behind the image. Okay. So this is how you can do it. You take your image and then you compute your 2D features using CNN on transformers, your favorite 2D backbone, and then you unproject those features along rays. So you use the camera intrinsics and so on to place 2D features into the 3D feature group. The first thing you do is you equip neural networks with this 3D placeholder, essentially, okay, where they can save their imagination of the scene. So once you shoot features to the features into that grid, and of course the features will be all over if you don't have the depth as input. If you have depth as input, then you can place the feature in the right grid location. Then you can do 3D convolutions or other feature operations to fix them up. And the good thing with this architecture is that you can put your objective over there, which can be detecting objects or finding similar objects or predicting trajectories and so on. And this objective can train end-to-end the weight of this 2D to 3D network. Okay. And once multiple views come in, like for example, you see here the coffee maker, and I go around it, and the scene is static. So this is standard SLAM setup, right? And you go around. If you have the camera pose, which for many, for example, autonomous vehicles or other agents, it's a solved problem because they have all these nice sensors on them. Then you can featurize every image and jump to the 3D feature space. And the only thing you need to do is you need to take that 3D feature map and work, make sure you stabilize against its estimated 3D rotation and translation. So it's as if the neural network does slump, but instead of an explicit point cloud map, it does it in this implicit latent 3D feature map. But still, you're still transforming, you still accumulate your features, and instead of accumulating point clouds, you're accumulating feature vectors, okay, in that 3D feature grid. But there is no other difference than that. And so what is the benefit of this operation? What is the benefit of dumping these neural network trainable weights for accumulating, let's say, observations over time? Well, here's the benefit. With SLAM, if I go in a new scene, let's say you've been to many office scenes and you go around and you build maps. If you go in a new scene, again, you need to go around. Again, you cannot imagine what's behind the image that you're looking at. But this architecture, because it has this 3D feature map, essentially it learns to imagine and complete what the scene has. Okay, so the weights learn to go from your 2D observations to complete 3D scene representations. So you can train this architecture actually for view prediction. For example, you take cave views as input and build a 3D feature map, a geometric consistency like we showed in the previous frame, and then try to predict the feature map of the next view. And the way you do it is exactly this. So imagine you have a number of frames coming in, and you build the 3D feature map here. Okay, and you build a 3D feature map, and then here is the new query viewpoint, and you know the relative pose difference. You featureize it, and you warp it, make sure you register. All the feature maps are now registered. So then you ask the features of corresponding 3D locations to be close and non-corresponding ones to be far away, right? So it's a standard metric learning problem supervised from geometry. And the fact that triangulation supervises feature representation is not new. I think many may know the point contrast method, okay? That just takes a point cloud, renders it from two different viewpoints, okay? And take points that correspond are 2D projections of the same 3D physical point and says, put the features of those projections close and pixels that don't correspond to the same 3D physical point further away. And you can learn great correspondable features in this way, all right? And the 2D objects that I show here essentially learns features for a robot exactly in the same way. Look at the scene from the different viewpoints. You take pixels that correspond to the same 3D physical point, and you say put those features close and no corresponding features far. Our method does the same, but because we have this imagination space, we can do exactly the same thing for grid locations that are actually not visible in both views, right? So you say, here is view 1, imagine what the scene is. Here is view 2, imagine what the scene is. Make sure your imaginations are consistent. And you discover useful features in this way. I'm showing here this 3D feature map. I put a camera, but with that 3D feature map, you can render it from any viewpoint you like now to go from this 3D to 2D images, okay? And now I rendered it from an overhead bird's eye view, and you see that features are discovered that follow the cars without any supervision, and that this is a useful pre-training objective, this view contrastive prediction that I just described. You know, people don't like grids because they have this grid, you always suffers from spatial resolution. So for in each grid location, instead of holding a feature vector, you can put a function. You parameterize that function based on the feature vector that is content of that location, and you can query that function for X, Y, Z continuous locations around that grid point. And the results of this are much better than trilinear interpolation. That's the whole point, to beat trilinear interpolation. And indeed, you beat it to death. You have much more correspondable features than if you don't use those extra functions and so on. But this is just an introduction. This is just a machine we've developed. And what I want to discuss in this talk is its application to bird's eye view perception. So of course, I just described now a self-supervised method, but you can do, like slime is also self-supervised, right? Just nobody allocates anything. So the same thing you can do here for view prediction. You can go from 2D to 3D in a way that when you render this 3D feature map from different views, actually you see the actual images. So now, so that was a 3D-dimensional feature map. For driving, often a bird's eye view 2D map suffices. So now we'll just adapt this architecture for bird's eye view, let's semantic segmentation. Okay, so you have a car, And this car, as you see, has multiple cameras around it, and that take image streams. And these cameras are also calibrated. And now you want to fuse the content from these 6 cameras, okay, into your bird's eye view map and predict labels that you care about, which is visible vehicles, lanes, pedestrians, and so on. So this is the task. And then using that input, you can drive. You can drive your car because you know where the lane is, you know where other cars are, and so on. So how we're going to do that? Well, instead of having a 3-dimensional map, we're going to squeeze it to a 2-dimensional map. So I'll show you now some details of how to do that. So here's our setup. Here's our car. And it has a very expensive LiDAR sensor there, the pink. And also it has some radar sensors that are much cheaper. Okay, so the more expensive your sensor, the denser the metric measurements is going to give you, but you know, it drives the cost up. And the challenge here is, how can I get accurate bird's eye view semantic maps with a cheaper metric sensor, the cheapest possible metric sensor? Okay. I mean, RGB alone, from cameras alone, would be one scenario. For cameras plus radar, as you see, it's going to be our second scenario. So yes, so we'll present. So in this work, we just try to do some a simple baseline architecture for this task, and actually provide a lot of ablations to really see what matters in performance. So the data set that we'll consider for this evaluation is new scenes, where all these sensors are available, and you can play with them by switching them on and off. So this is the camera data. As you see, there each image is 1,600 by 900, and these are the radar data, and they're quite sparse. I mean, if your radar is even cheaper, they're going to be even sparser. And here's your LiDAR data that is much, much denser. And this is the de facto in most self-driving car companies nowadays. We need the LiDAR sensor. So the question is, how can we get rid of the LiDAR sensor? Most of the previous works in this area address exactly this 2D to 3D lifting step. What is the right way to go? What's the best way, best differentiable, and end-to-end backbrokeable way to go from 2D perspective images to stable map representations? And there are multiple previous work. Here is one, for example, from Roddick et al. That squeezes the image across the vertical dimension and then predicts the depth, and that's how it instantiates the bird's eye view features. And here's another, the lift splash shoot method that tries to estimate depth per pixel, a distribution over depth values, and uses those to place those 2D features in the right location inside the 3D tensor. Okay, so most, for example, there's high probability the depth to be this, so most of the features are going to be placed here, for example. Okay, so it's a differentiable way to go from the image and the depth prediction all the way to the output, which means that the downstream task also can train those depth prediction, depth distributions. And here's another way of doing this with transformers. And here is the latest way that we've seen on arXiv, like maybe 1 month back or 2 months back, from BB Former, that they use deformable attentions. I don't know if you know what is deformable attention, but basically the token here in the 3D map doesn't attend everywhere in the image, rather predicts spatial locations, and then it takes their feature value and predicts its feature to place in that token. And here is our method. This is what I described from before. A very, very simple method. Essentially, what it does is you take your 3D bed of tokens, you project them down because you know the intrinsics, you see where every centroid falls in the image, and say, I'll use that feature. Okay, so you don't reason about occlusions, nothing, you just project them, every 3D token in different 2D images, and take the 2D feature vectors that sit on those pixels and place them on your 3D feature map, if that makes sense. Very simple method. Okay, you don't know how to reason about occlusions at this stage. You just have a set of 3D tokens and a set of 2D pixel locations. All right. On top of that, then you're going to squash this dimension, the Z dimension, because you don't care anymore, you just care about bird's eye view maps, and then you're going to put 2D convolutions, like many layers of 2D convolutions, and then you'll spit out your semantic maps. That's the architecture. It's extremely simple. Yeah. So it turns out that this extremely simple way of going from 2D to 3D gets very good results on per frame vehicle segmentation intersectional reunion score. Okay. Which we were very surprised. This essentially started by, we actually got the code of 3 leaf splats, and we removed their depth prediction, and we got very similar number to what they had, like 0.7 lower. And then we said, is this really the big problem of how to lift features from 2D to 3D, which it should be, but but then we started doing some ablations to really figure out what matters for performance for this task. Okay. So here it is. So first of all, I'm going to show you some results of how they look like. So on the right is the ground truth, and on the left is the predictions, okay, of these vehicle maps. Well, here's what we found. We found that the resolution of the image matters a lot. So there is a 2D, very, very deep and very important 2D featurization step. So before you collect your features on your 3D map, you featurize every image. So the high resolution is important. Earlier architectures use smaller resolutions. So now, GPUs are getting larger. So resolution is also getting larger. So we found that this made a huge impact, as we see in performance, from 36 to 47 IOU. Another very surprising thing was the batch size. As you change the batch size of this again, you have dramatic effects. And some randomization that we came up with of extra augmentations of how we're going to place the reference camera also helped on 1%. So batch size and spatial resolution were very, very important for performance. So this is our first result here, that you can do this neural mapping, bird's eye view mapping from multi-view calibrated cameras without any depth as input, and you'll get this number if you're careful with the batch size and the spatial resolution. And the lifting step, the feature lifting from perspective to overhead, does not seem to have a huge effect in performance. Now, having said that, the deformable potential, for example, may give 1.2 points based on our latest ablations, but this is still very, very tiny. Now, the second thing that we said is the following. There has been a trend to really get rid of LiDAR, but getting rid of LiDAR, we also got rid of radar. A couple of previous work tried to use radar, and they found that it didn't actually help because the fusion they used. So we said, okay, what if we try one more time? So just to compare, this is LiDAR on the left and radar on the right, and there is density is very different. So we're going to do the straightforward thing. We take radar, we're going to rasterize it and concatenate it to the 3D feature map that we obtained from our 6 different camera viewpoints. So that's what we're going to do. So now again, we're going to put 2D convolutions here, all right, where the kernels now see radar concatenated with RGB. And you get an enormous boost from 47 to 55, which means sparse metric information is still extremely useful. Now we are still, 5 points below LiDAR, but this is a research direction, let's say. And I think this is interesting because when Tesla proposed that, let's say a couple of years ago, many people thought, okay, this is crazy. But it turns out that we people can drive super well from cameras alone, and actually even one here, even the stereo blind people can drive very well. So I mean, now we have 6 cameras and radar. For sure, we should be able to do extremely good estimation of the drivable place. Yeah, so a couple of ablations now on this RGB plus radar. Yes, so if you use the radar metadata, as opposed to just occupied versus not occupied voxel, you get a 2% boost. You need to switch off the filtering that nuisance does on some outliers radar, because the learning model is going to figure it out on its own in a better way. And you can take 3 sweeps of radar together as opposed to operate 1 sweep at a time. Okay, so this is what this says, and this is the final results. And so, and this concludes my talk. And thank you very much. And if you have any questions, please go ahead.
Thank you for the talk. I have two questions. First one regarding the camera model. So I see you have this back progression of the 2D image information to the 3D picture of the bottom. Do you implicitly assume that the camera model is actually the narrow-field perspective pinhole model? What do you mean is the fisheye model?
Right. So if it has a narrow field of view, I don't think this is a problem. You can have a camera that's on direction. You're going to place it in the middle of your 3D feature map and still shoot the features and place them everywhere. Right? Do you see? And it turns out that those the featurization, like the operation, the neural operations on top, they can totally handle features that are slightly misplaced in the map. Now, a very interesting fact from one of those previous courses, VB-Former, that doesn't operate per frame but operational frame sequences, they have only 1% gain when they use the ego motion of how they shoot their features versus when they use temporal attention, which means the stabilization of features over time, which means also across poses, it can be handled by the learning algorithm. Yeah,
thank you. That actually relates to my second question regarding how much do you need to rely on the ego motion estimation as an input?
Yeah.
What if my ego motion estimation is not accurate? Because the bird eye view output, usually people like to use that for the localization purpose. But if you construct this observation based on the ego motion estimation, at the same time, you want to use that for the ego motion estimation, that becomes
right. Yeah. So this versus eye view featurization is not for estimating your motion; it's for driving. You know, I should be able to take this model and directly, feed it on a car simulator and show you, look, a car can drive now. Okay. So we assume that the pose has come from other sensors. Now, your question is fantastic. How accurate does this be? We can totally have it within the bolt, but we should not be assuming that it's super accurate. And yes, we have added noise on the cameras, and it doesn't have a lot of impact in performance. I would say the latest results from transformer architecture is that these localization problems can be taken into account by having features from one camera view attend on the features of the other camera view, and solve essentially this correspondence problem on their own. And I think the most surprising result is exactly what you said. There is this VB-Former, if you read. The car is actually moving over time, and they need to aggregate those distribution maps over time. So they have two methods. One is, I use ego motion to transform my map versus I dump two maps, and then I have cross attention in time to actually fuse the features. And the second does only 1% worse. And we definitely cannot rely on ego motion for, in general, to stabilize our features, because there are dynamic cars here that don't follow the ego. The motion of the ego vehicle, right? Yeah.
All right, thank you.
Great questions. Thank you.
Other question?
My question is regarding the slide where I had featurizing the voxel volume based on RGB based on T. You had a per pixel distribution along the way.
Yeah.
So is this distribution from a monocular depth estimation network, for example, or how is this distribution from?
Yeah, so this is from previous work, okay? In our works, this depth can come from a sensor. Here they say, look, you can learn to estimate it. So this is estimated depth. You have a neural component that spits out those distributions. And they say, look, we can train those end-to-end for the downstream task, okay? And what we found is that whether you estimate those depth distributions or not, it has less than 1 point difference in performance, while other contributions of the paper, for example, blowing up the spatial resolution, was way more dramatic, had way more dramatic impact in performance.
So you say you don't estimate the depth, do you scatter the...
Exactly, you just scatter the features along the ray.
So it seems to me like a lot of the insight that you found, is that a lot of the heavy lifting before you do the rasterization of the feature volume tends not to be that important. So do you think that rasterizing before you do your 2D convolutions in the bird's eye space is causing degradation of your feature quality.
So you're saying this by rasterize you mean the scattering?
Yes.
If the features are impacted by the scattering.
Yes.
Right. So these features is whatever your resident backbone gave you, right, for this location here.
Yeah.
You compute it here, and then you just dump it and you average across the different scatterings.
Yeah.
So this seems to work okay. This is exactly the model that we just showed.
Yeah, I guess I'm wondering if the precise way that you're going from your resonant features to your feature volume is not that important. And is it because a lot of those features are being degraded by the step of rasterize on the bird type step?
Right, so this rasterizing is a non-parameter, it's parameter-free operation. It just takes the feature and dumps it in the right place, right? So it doesn't change the feature whatsoever. I want to mention that this is a bird's eye view task. I'm pretty sure that if we would go to scan it, for example, we would need to fuse information. They are having an accurate depth for, I'm pretty sure it's going to impact your performance. Okay, yeah.
Other question?
Sorry, just had a couple of clarifying questions. I walked in late, so maybe I missed it. But I was wondering, how is radar being factored into this parsing architecture in the first one? And I guess once you answer that again.
Yeah, so the radar is the most straightforward way. We take our, bird's eye view map and we just quantize it. We just quantize it. When there is, we say for grid locations, this is occupied, this is not occupied, based on the radar points.
So how sensitive is it to how accurate the radar points need to be? Because, for instance, I think in new scenes, twin test, so there is no Y, for instance. So anything that's being projected displaced to it. X is also a little bit more right? Because depending on how much power you put your radar and such. So how sensitive is this architecture to say
to the radar accuracy? Well, we can evaluate that, but what I said is even without any radar, I mean, you get 8 points less in performance. So with zero metric information, you have you still get some reasonable performance, right?
Right, exactly. That's why I'm so interested. So if this is in fact done without knowing how accurate the radar was to be, and you say that we're 4 points away, 5 points away from LiDAR. Is that the difference to push radar towards LiDAR performance?
Yes, so I'm sorry, it's also the mask, and I don't really understand that for listeners don't understand the accurately, but I think your question is how far away are from LiDAR? And I'm saying RGB plus radar is 5 points right now behind, lagging behind in that bird's eye view semantic segmentation task. Is this your question?
Not quite, but I asked about the accuracy or the sensitivity of the model to the accuracy of radar points. Because
great, very good. So different radar sensors, depending how much they cost, they come with more accurate metric information and denser metric information. The denser and more accurate you are, these numbers are going to be going up. There is a continuum here from our radar that we grab from NUSIS to LiDAR, which is extremely expensive and accurate. There is a range there. But the point is, even inaccurate metric information still helps tremendously your bird's eye view featurization.
I agree. And that's why I'm asking if you guys have considered it, because you're saying you're 5 points below RGB plus LiDAR. So if indeed that there is this inaccuracy in the radar points, is that 5% can that 5% be covered by having
more accurate radar?
Exactly.
Oh yeah, sure. The more expensive radar you give us, probably these numbers are going to go up. In fact, this was the comment from Matthias Nisser when we showed this work. He said you should not clarify sensors as radar, LiDAR, and so on. Every sensor comes with its cost and with an accuracy and density, and this should be okay. It's that much accurate. It's exactly what you're saying. It's a continuum and that much dense, and this is my number. Okay, does this make sense?
Sure. All right. Thank you.
Sure.
Actually, I want to follow up a little bit. On the radar, it seems like actually has a little bit shorter value range than LiDAR. And so if you you're combining RGB and radar, is it there some estimation measurement about how much distance, whether RGB plus radar will outperform RGB or in another distance very far away that is actually dramatically down the performance drop.
Okay, great. So I think the question is, this IOU is computed by averaging across all distances, how far away you are from the ego vehicle. Potentially, if you have one nearby and one further away, then in the nearby, potentially those numbers will be closer, and the further away going to be much worse, correct? I absolutely agree. Now, my point here would be, this is potentially the wrong end task to be showing numbers for. The right end task would be, here is my driving score in Carla or in the best driving simulator. Okay,
yeah.
And because many times when I drive, I really don't care what happens super far away, right? At some point, I'll come closer and I'll see it. So the question is, end-to-end driving score would be much better, because for end-to-end driving, maybe those numbers would come closer or further. We do not know. But do you see? So this is the problem of having surrogate tasks that are not really the end task that we care about.
Okay. Yeah. Can you go back several slides actually from that one, not this one, the projecting the feature into the 3D volume.
Projecting the features into the 3D volume. Okay.
Yeah. Here, from my understanding, image feature projecting to the 3D volume needs to have depth estimation. And how is the depth actually affecting the?
Exactly. But that's exactly what we're saying here. That we also thought like this. Only our first paper, which was in toy scenes, didn't use depth. Our next ones, we would use some depth, and then we would take this feature and place it in the right depth value. Okay, and then we saw that here, just scattering the feature along the ray, all along the ray, it's still fine. It's okay for BV drive. All right. So for 3D, a dense 3D construction in a 3D environment, potentially this will not be a great idea. But for autonomous driving, you don't care that much about this. So there's no depth estimation.
Okay.
We never try to estimate that. Yes.
Okay. Yeah. Okay. Thank you. Any other questions from the audience? Okay. Thank you very much. I know you need to catch up another one actually. You start. Yeah. Thank you. Enjoy your lunch. Yeah. We will restart the workshop at 2 p.m. So we will have about 1 hour for lunch. All right, I actually misunderstanding you. I was thinking you want to control over the time, and let me stop my
okay. Also, I don't know how to do live stream. What's this live stream now?
Live stream, yeah. I was thinking if you control, take over control, and then the live stream will stop, and that's all. Yeah, something like that. But it's
it does. Yeah, it is not. Yeah, I also.
I missed your question. What were you asking? Because I think it's related to what I was asking.
Yeah.
What was your question?
It's something like, let me press the pause.
Yeah.
My question was about whether the depth estimation will significantly influence the BV map generation accuracy. Because when you project the future, will it show that great improvements on
so we are working on this, on adding such a object detection ahead. Okay. Also, we are not saying guys don't estimate them. We just do some ablations here just to show what is happening, which I think it helps. So we are all for more accurate 3D estimation. I don't have 3D detection results, so I do not know right now. But I want to say that instead of 3D box, estimating the lanes and the roads and segments and so on is still a very important task. Do you see? Like the stuff, not the things. Okay.
Yeah. So, if you have any initial results on
on the detection head?
Still affects some.
No, but right now we're running. I'm pretty sure if you have a very good depth channel, it would help.
Yeah, so
right.
the depth is like a little around 100
depth estimation.
Yeah, depth is basically the biggest problem in one of your
yeah. I mean, yeah, sure. I mean, LiDAR gave it a right?
Yeah, that's what I was thinking.
So for sure, it's important. Now, what you're saying is that this gap may not be that small for other tasks. I think this is what you're saying, correct?
Yes.
Yeah, I see.
Great.
Well, unfortunately, we need to see with an app, which we can give you, because I can tell you with LiDAR it does this, and then we just put some object queries, and then I give you some numbers.
Yeah, I think for PD, I know, like, for PD, I know, like, how much, if you put the.
I'm also changing actually.
Ground to LiDAR or ground to.
So by the way, just to pick up, I would do if I had to do the 3D detection correctly, and that's why we're doing it. I would allow my object queries to attend to images directly. So I think they will figure out on their own where to place themselves if they attend. Do you see what I mean?
Yeah. So you basically think that kind of stuff.
Yeah, where the 3D queries, and there is a paper like this called 3D to 2D query from Justin Solomon. And I think that's a great idea. There is no reason to take features and mush them and then try to predict objects. Because resolution is terribly important, and for object detection is also important. And I'm not here just to detect objects. I want to find the blinking light, right? I want to find the blinking light of the car. So therefore, sure, I need to look at the image if I want to detect what I need to detect. You see? Yeah.
Okay.
So definitely, this is not the right way to do general 3D perception. This is just something we found for believing.
Okay. Yeah. Okay. Thank you.
Thank you so much for that popularity. It's very important. I was curious if you looked into how well for those
Smaller than cars.
not just vehicles, right?
Okay.
Pedestrian bicycles and pedestrian.
Yeah. Okay, so this is very related to the previous question. I think to do this correctly, you would need not to take images and dump the features here and predict, which is what you would do for the road and for the lane and so on. I think you would have an object detection task which attends back to the image features. I think this is the right way to do it. Because then you can really zoom in the image, which is very important.
So then, did you also look at like just on the road boundaries?
Yeah, this is what we're, similar things for lanes.
And I will join the meeting.
Yes, actually, this is running right now for the lane. But some initial results we are very similar.
But anyway, you will be here with the results wherever you mentioned.
So what was being used to connect on board, or were they only connected? Like you make a separation between using the
We use it to train and test time. Yeah, we don't use the supervision for features and then at test time we get rid of the sensor. No, the sensor is there.
I'm the first one, right? This year, just come and check my
Yes.
give it test now. I don't know if
well, IOU is for semantic classes, it's not for vehicles. It's just for vehicles. You take the pixels you predict as vehicle, you take the crowd of mass for vehicles, you take the intersection of those, and then you take the union, and then you average.
Oh, it's on the whole image in BEV. It's not for a car.
No, it's not. This is assuming that the whole is semantic segmentation, is not detection. Is what people do for lanes, for example, right? We just predict the map of the lane.
I see. Okay, then we do it right now. I was thinking about it like for vehicle you.
No, you don't individuate vehicles.
This just creates a full semantic map.
Yeah.
So we work at a company called Robotics. We do like self-driving trucks. One of the things that we find very useful is just to have an understanding of just in the use stage, just if something is like the obstacle or not. Right? Yeah, so that is like this,
我带走这个也没有用啊，没关系，我就在这放着。
哦，那也行吧，没问题。
你的想回去一趟是吗？今天现在Right. We know next week. So are you the organizer for this one?
No, no.
Okay.
So the process are just lunch.
Okay.
So and when people come back to.
Okay, and are you like?
No,
Are you-
I'm just a student.
Oh, you are?
I was listening.
Oh, you are saying. Okay, so which university are you from?
Rochester Institute and Technology.
Oh, RIT. Okay, great. You want?
Yeah. You will go to the
Yeah, I was actually like eat many people from there. Okay. So what are you working on?
I'm still out. I don't have to do mostly, but I work in that.
Okay. So what are you working on?
My research is about the percent.
Okay.
Yeah, so not in the computer vision. In my research was focused on motion. We will come back.
Okay. Yeah. Sure. Yeah. So are you on LinkedIn?
Yeah.
Would you mind if I add you?
I don't have it.
Okay. Yeah, I can just send you the message that I get later.
I don't.
Oh, you don't have a LinkedIn account?
Yeah.
Okay.
I still have 3 years to graduate.
So I'm saying it's like, oh, you that's a different answer.
Are you a PhD?
Yes, I'm a PhD. Sean.
I don't know, but I know that the FSU is famous in the.
Yeah, so yeah, I'm yeah, that for the platform. So I'm the spread of platform, which yeah. Okay, it was nice meeting you. Yeah, sorry, I do the camera.
My name is Wei. Y-U-W-E-I.
So you wait. Okay. Okay. Yes, you. Bye-bye.
That's it. Just good.
And you will use more than that before, because this one will connect you to one. Okay, now let's get started with the afternoon session. And our first speaker in the afternoon session is Dr. Sudeepa Sinha. And Dr. Sinha is a principal researcher working on mixed reality and AI in the cloud and AI group at Microsoft. His research interests lie on computer vision, robotics, and machine learning. He works on 3D computer vision problems related to 3D scene reconstruction from images and videos, like structure from motion, visual odometry, stereo, optical flow, multi-view stereo, image-based localization, object detection, and post-estimation. And all of those research enable applications such as 3D scanning, AR, and UAV-based aerial photography, photogrammetry. He received his MS and PhD from University of North Carolina, and he received the Best Demo Paper Award, Best Demo Award at CVPR 2007, and for one of the first scalable real-time vision-based urban 3D reconstruction systems. He also served and will serve as area chair for 3DV 2016, ICCV 2017, 3DV 2018, 19, and 20. And he was a program chair for 3DV 2017. And he will serve. He served as area editor for the journal of CVIU, one of the best journals in the computer vision society. And actually, one of his work is he's also one of the person enables GPU for feature tracking from my learning. And today he will give us a talk on the topic of towards storage efficient and privacy preserving camera localization in pre-mapped environments. Welcome. Thank you.
Thank you. Thank you. And thanks to you and all the organizers for inviting me to give this talk. It's a pleasure to be here. So good afternoon, everybody. My plan today is to talk about this research topic on we work on camera localization. I'll be talking about joint work with a number of colleagues at Microsoft who work on mixed reality, augmented reality, and also ETH Zurich and University of Minnesota. And I'll introduce my colleagues as I go through my talk. So one of the key, okay, there we go. So the core problem that I'll be talking about today is the camera localization problem. It's very fundamental to a lot of different applications in robotics and computer vision. So the problem statement is that we are given a query image of a scene, which has been pre-mapped in some ways. From this query image, we're interested in calculating the 3D position and 3D orientation of the camera as accurately as possible. So here's a visualization on the right side of a camera frustum that has been estimated using, this is what we would call estimated pose. And this task is at core to many applications. We work in Microsoft on mixed reality, but broadly, like the field of AR, VR, robotics, everybody is solving this problem because the device or the robot has to be accurately localized within the environment. When we do augmented reality, we are interested in displaying things in the displays. Robots are interested in taking actions, but for that you need to know the position of where you are. So this is a very vast topic. This is easily like if you go back to the earlier works, they would go back into the 90s where people were already able to solve small 3D vision problems and get pretty good localization results back then. Just over the years, the field has evolved, and I've here mentioned a few representative works from the last few years. But in broadly, I think it would be fair to say that there is this sort of two high-level groups of works. In the first group, we also have machine learning. But even though there are components of the algorithms might be learned, there is still sort of this framework where the algorithms do retrieval, matching, and pole estimation. And then in the second group, which I call learned methods, and I have some representative papers there, these are the methods that are sort of trying to really take end-to-end approach, like get the poles directly out of a machine learning model, out of a neural network. And I'll talk about some of them as I go through my talk today. So here is a modern. This is a very popular implementation. It's also an open source implementation of this method called hierarchical localization by Sarlin et al. And it falls into this category of retrieval-based camera localization. The pipeline sort of has these three steps shown in the flowchart on the left. The first step is to give in the query image, extract similar-looking images from a database. Remember, the scene is pre-mapped, so it means that you have features or images of the scene in the database. Then you do some sort of detailed pixel matching. You get point correspondences. Then you use multi-view geometry solvers to get the camera pose using many robust techniques that are out there. So while this sort of method is currently still sort of the top performing methods, there's going to be some learned methods that I'm going to talk about, but right now, like in the last few years, on some benchmarks, HLOC has shown incredibly good results, so it is very accurate. However, there are two sets of limitations that I'm going to focus on. The first one is that these methods are going to, no matter what you do when you go to a large scene, they're going to have very high storage requirements, because the way these methods work, they need to store a lot of features extracted from a lot of images of the scene. That's where the accuracy comes from. And secondly, I'm going to talk about this topic of privacy, and I'll show you that there's a certain privacy attack that can be done to invert the features that are stored in the database. And from the inversion, you can reconstruct detailed image appearance. And this may have certain images that have sensitive content, and such information can get revealed. So these are the two limitations I'm going to try to address through some of the work that I'll talk about. And one thing to note is that as you go towards larger and larger scenes, if you want to use a method like HLOC, you will run out of storage on your mobile device. Oh, sorry, that was a pop-up. So the invariable solution is that these devices, these resource-constrained devices that need to localize within the environment, are going to talk to some cloud service. And so data is going to be transferred between the client and the cloud. So this is a paper that we worked on 3 years ago, presented at CVPR in 2019, where we essentially showed that the kind of sparse 3D reconstruction, structure for motion maps that we create from images can actually be inverted to reconstruct very detailed images of the scene. So shown on the left is a very sparse point cloud. And even though it's very sparse, those points have feature descriptors associated with them. And that information could then be passed into a neural network to reconstruct RGB appearance. So this is sort of the middle column in the panel shows the reconstructed frames. And you can see that a human can look at this, even though there are artifacts, you can tell what is in the scene. You can recognize things in there. So that's the fundamental privacy problem we want to try and address. And the high-level goal is to try to come up with a different approach for camera localization, where there are two goals. We want to prevent this kind of feature inversion or image reconstruction attack, but we still want to be able to solve the problem of camera pole estimation. So this cartoon diagram is trying to show that could we, at least this is the strategy that we took in our work. Question we want to ask is, what can we change? How can we change the features and put something into that question mark, so that when we transfer it to the cloud service, some malicious attacker who gets access to the data cannot do the inversion as easily, but we still want to solve the target task, which is localization. So with this goal in mind, there are two papers I'm going to talk about. In both the first two papers, this is our work. We tried to basically address this core problem of privacy preserving localization that I've introduced. And the third paper that I've listed here is being presented in CVPR during the main conference. This is a paper from the Meta AI research group, and so I wanted to mention it there because they have the same goal, and it's builds upon the work of Dushman et al. So the first paper I'm going to talk about is work by Pablo Speciale, Johannes Schomburger, Mark Bolivis, and myself, who's presented at ICCB. And in this paper, we basically proposed, we had this geometric insight of how you could transform these features to try and prevent this inversion attack. Here's the basic idea. So you take a query image, you extract your favorite kind of features, local features. These could be SIFT features. And typically what you do is you match these features, but then you take the XY coordinates of the points, put it into some ransack algorithm to do multiple geometry and calculate pose. So the idea in this paper was to say that we're going to take these points and replace these points with feature lines. So that we're going to replace the red point shown there with a randomly oriented line in the image, but the line needs to pass through the red point. After selecting the line, we're going to discard the point, and now we're going to give this feature line to the pose estimation algorithm. And so the information that will be sent to the cloud, if we were to use our approach, would be the feature line and the descriptor. So this feature line is basically an abstract representation. It's basically saying that along the line, somewhere along the line is that unknown point, but we have basically concealed the location of the point by hiding it within the point by hiding it within the line. And now the trick is, how do you do pose estimation with these feature lines? So shown on the left side is the traditional PNP algorithm. You have points in the image and 3D points. So each point-to-point correspondence will give you two constraints. So you get two equations, and so in the minimal case, because there are 6 unknowns to be solved for, you need 3 correspondences, which will give you 6 equations. So what happens now with our feature line representation shown on the right side? Here, each line will essentially give you only a single constraint. So when you back project that dotted line in the image, you get a plane, and the only constraint we can impose is that the plane, the point must live on that plane. So this turns into one constraint. So now you need 6 correspondences to solve the camera pose in the minimum case. So this is the core idea in the algorithm. And then we explored a lot of different variants of this. But the interesting point was that this point-to-plane registration problem is actually studied in the literature, and there are solvers available for that case already. So in some sense, we were able to show that just by sort of choosing the feature line representation, you automatically can reuse a lot of solvers that are out there and want to work pretty well. So here are some brief snapshot of the results. In a sense, what we found was that this privacy preserving algorithm that we proposed basically allows you to, get the desired. I'll explain in a moment that you can prevent those attacks, but more importantly, you have to trade off a little bit of accuracy because of this sort of weaker constraint that we are using. So there is a small accuracy gap, but the accuracy gap does get smaller when you do non-linear refinement, as is done typically in these kind of algorithms. And the overall compute overhead is also pretty low. So now let me show you an example where here's an image with a subject in the image, and this image is actually matched against a pre-mapped environment of the scene. So if you use regular feature points and did the inversion attack, what would end up happening is you'll be able to reconstruct the whole image, including the appearance of the person from the feature descriptors. But with our method, what happens is that you solve for pose. When you solve for pose, you get a bunch of inliers. For the inliers, you end up actually revealing the position of the feature points. But the inliers all come from the background, because this is what we have mapped primary. The person is not part of the background, so those feature points don't get revealed. And therefore, when you run the inversion attack, you do not reconstruct these areas of the image. So that's the basic idea there. And then we went further in a follow-up project. What we did was then we tried taking the same idea of, how can we transform the features that we will upload to the cloud. And this time we focused on transforming the feature descriptors. So the core idea of this paper was that instead of taking these high dimensional points, the feature descriptors, and treating them as points, we're going to sort of do the same trick of lifting them. And in this case, high dimensional points can be lifted to lines, but in general, affine subspaces. And this is exactly what this paper explored. So the idea is that for any descriptor point, we're going to construct a random affine subspace. And we're going to choose the dimensionality of the affine subspace. And depending on that, we're going to choose some vectors. So each feature vector will going to basically turn into this m by n matrix. And this is going to be our feature representation. And then there are some details in the paper on how exactly you pick these basis vectors to construct the subspace. But then once you have these representations, the idea of this paper was to then say that, okay, instead of doing vector to vector matching or nearest neighbor lookup, we're going to now use a new notion of distance. We're going to take a point and match it to a affine subspace. And this also gives you a notion of a distance. It's like a point to a hyperplane distance that we're going to use for matching. So if you have the situation where both the features you're trying to match have been concealed, then you're going to do subspace to subspace matching, shown on the right side. So you're going to basically look for the closest distance of 2 points. Each point lives within its subspace, but the closest the distance of the 2 closest points is going to be the distance between the subspaces. So with that idea, then we plug that into existing algorithms for localization. And here are some results on Octane day and night. Again, the general trend of the results is that we lose some accuracy when we change this feature representation. So shown in the yellow box are some numbers. On the top row is SIFT with 82%. When you start doing this lifting of the point to higher and higher dimensional affine subspaces, you get lower accuracy. But basically what we are seeing here is an accuracy and privacy trade-off. And here are some visual examples, and there are some details here. Left column shows 3 example images. The second column on the right shows the reconstruction from the ENN attack method. And then these are different results that qualitatively show what happens when we use different kinds of affine subspaces. And we implemented some, at the moment, these papers, I have to say that there's really no theoretical results that we can claim or any guarantees we can claim. So in some sense, the validation that we are doing and the other papers are doing, it's all about trying to basically come up with the best possible attack and then empirically evaluating performance. How well did we do in terms of addressing the privacy concern. So essentially, I've talked about these 2 particular projects we did where we took the approach of changing the feature representation, changing the matching algorithm, and changing the pole estimation algorithm. And then we showed that, okay, you can get something to work, but there is actually a completely different strategy. And this strategy would be not to store anything. So what if you could basically not store the map, not store features, images, and use a model, a trained model to calculate camera poles? This is actually something that a lot of people in the field are already doing. So starting with PoseNet, which was one of the first papers to do end-to-end convolutional neural networks for training regressive pose from an image, there has been a wide variety of works that completely avoid storing what I would call essentially map data. So assuming that these deep models are not susceptible to what are called model inversion attacks, this is a perfectly sensible strategy to take. So very quickly, like here's a schematic showing how sort of these two type of learned methods work. On the left side is absolute pose regression, so PoseNet. There have been many follow-up works, which I'm not talking about here, but effectively it's a black box you train to, given an image, predict the pose just from the appearance. And what scene coordinates, dead scene coordinates methods, so one example of that is the work by Brachman and Rother, DSAT star. So what these methods do is they use the CNN to predict an intermediate representation, which are essentially at every pixel you are trying to predict an XYZ coordinate of the surface visible at that pixel. So these CNNs have to be retrained. Usually they're trained per scene. And now the only thing that you store after your training phase is over is the model, right? So this is great. So the problem essentially is that these methods are still not at par with HLOC in terms of accuracy. So yes, if the learned methods get at par and you know we address all the problems of generalization and everything, then this is actually a great way to address both privacy and storage, the two issues that I highlighted earlier. So in this line of work, there's a project that we've done recently. There's a joint work with Tiendo and Yansu Park from University of Minnesota, and we're presenting this paper in CVPR on Thursday. The project, the paper is called "Learning to Detect Scene Landmarks for Camera Localization," and we take a different approach to solving this learned camera localization problem. The idea in our work is that we are going to take a scene, we're going to map it, and then we're going to, using some mechanism, designate some specific 3D points in the environment. And we call them scene landmarks. So we're going to then take object detection framework. We're going to train a detector to recognize each of these landmarks. So for us, a landmark is a category or a class. We're going to take some off-the-shelf object detector, you know, and train it to detect these points for us. So then once we get those 2D observations, so every 2D observation will be basically a landmark ID and a position in the image. We will then take those correspondences and try to solve camera pose. So here is a visualization of a trained model. It's actually what you're seeing are little blobs. They're actually heat map predictions for each color indicates a different landmark. So essentially what we have done is we have taken these very mature key point prediction neural nets and we've just reused all that machinery to predict scene points. And effectively, once you do this, you see that we are getting of the order of maybe 20 to 30 landmark predictions in the image, but turns out this is in many cases enough to calculate the camera pose. So we don't have hundreds of features like you would do if you did HLOC to maybe just, you know, store hundreds of thousands of points in the scene and then give you maybe 200 matches. So this is sort of different. It's 2D to 3D correspondences, but what we've done is really trained our network to recognize very specific portions of the scene, try to make it robust to lighting change and all those other factors. So if you put them side by side, our work is sort of very closely related to the work by Brachman and Rother, which is using this dense scene coordinate framework. But in some sense, it's also the reverse. So what VSAC star shown in the middle does is, given the image, tries to predict a dense scene coordinate map. So given the image, it's trying to predict the XYZ coordinates for every pixel. And after the running the CNN, you would basically end up with thousands of 2D to 3D correspondences. You put them into your favorite RANSAC robust estimation framework, and you can calculate camera pose. What we do, shown on the right side, is we pass the image to our CNN. The CNN produces sparse detections. You can use any detection framework. We went with heat map based networks because they're known to be pretty accurate. So what we get are very sparse detections of each landmark, and what we need to do is we need to store the XYZ coordinates of those landmarks. So this is going to be a table. Typically, for our scenes, we look between 200 to 400 landmarks. So given that table of XYZ coordinates and the detections, we can also get 2D to 3D correspondences that we solve the camera pose from. So now the remaining questions are, how did we define these landmarks? And the approach that we took in our work was to basically run structure from motion on the set of training images. We did this using cold map. Having run cold map, we have a heuristic that we came up with that tries to select L salient points in the environment. The saliency measure is trying to sort of look at usual things that people have done in the past to look at points that are discriminative, points that have higher repeatability. We try to also maximize scene coverage because we don't want all the landmarks to be selected in one corner of the scene. We want them to be well spread out. Then we have an iterative 3D approach. The approach is not so important. At the end of the day, we have a way to come up with a subset of landmarks. Here's an example shown here. The important thing is you want a lot of data captured over multiple sessions, different lighting, different times of day, so that you get the variability of what you need to train a good recognizer. So, as I said already, we leverage this very standard neural net architecture. There's a resonant 18 backbone. We take advantage of some dilated convolution layers. Again, I think it's very standard nowadays. And then to get more spatial resolution, we try to do these two layers of upsampling using transposed convolutions to get these heat map detections. So that's the basic framework. There is one problem though. We, as I said earlier, that in all our data sets and at the moment, if you try using this, the question will be how many landmarks do you choose? This is a decision you have to make. We went with up to 500 landmarks, but turns out that there is more work needed if you want to be there is some work needed to come up with better ways to select the landmarks. At the moment, we don't have them. And what ends up happening is that you may actually end up with a sparse distribution of landmarks. Now, given an image, you may not have any landmark visible in that particular image. It depends on where you take that image in the environment. So this actually happens. Often what happens is we have a view where only 3 landmarks are visible. So it's not enough. So what we did in this paper was we also explored an idea where we said that it doesn't matter if the landmark is not visible within the field of view of the camera. We're still going to try to predict the bearing vectors for the landmarks in the camera coordinate system. So for that, we came up with a second neural network. At the moment, we have 2 separate networks that we train. And just to give you an idea, this is how they compare. Like shown on the left side is the network that I told you earlier about, the heat map-based detection. If you see the landmark, you'll detect it. The one on the right side is going to try to predict in 3D, so it can predict landmarks that's behind the cameras as well. Those bearings are still useful for doing pose estimation. So that's the core idea. Let me try to quickly wrap up my talk and tell you some of the results. So we did evaluation on the 7Gs data set, which is very popular and very common for learned methods. On this, we are sort of doing at par with DSAC, slightly less accurate. But we actually, as part of this paper, released a new data set called VOCVALC. We collected these data sets ourselves. And the main difference is these images are collected over multiple days in environments that have changed. Objects move, windows, doors closed. There's actually a slide. This is one of the scenes in our data set. A quick sample of some images showing you it's day versus night. There's just a lot of variations that happen in your environments that our algorithms are still not robust to. And let's see how they compare on this new data set, which we focus our evaluation on. So first of all, we trained a PoseNet variant that also had a ResNet 18 backbone. It really struggles on this data set. Like the percentage number shown in the third column in block, each block is the 5 centimeter, 5 degree recall, and it's really low for PoseNet. NB is our method that does the bearing vector estimation. It's also really struggling. But it's way better than PoseNet in terms of rotational error and positional error. And then we have these methods. So there's DSAT star, which is the top performing method within the group of papers that do methods that do learning. And the bottom two rows are both our method, NBE plus SLB. And the last row is showing the results with the respiratory backbone, which gives the best results. And the row on top of that is a version trained with an efficient net backbone, which is a lot more compressed. So we lose some accuracy, but the memory footprint is much smaller. So that's the good news. Turns out on this data set, when we compare against an HLOC baseline, the bottom row is showing HLOC if you used all the resources available. So this is really using as much storage as needed, as much compute as needed. On this data set, HLOC is still beating us by a huge margin. It's beating all the learning methods. You can see that the numbers are much higher. But we compared with sort of variants of HLOC where we tried out different heuristics for reducing the storage. And then when you impose a lot of storage restriction, that's when you start to see that there's a real accuracy storage trade-off here. So the high-level summary is that, yeah, our proposed method is beating the best learned method, but we still have a long way to go to beat HLOC. But it turns out that when we combine the correspondences from a network with HLOC, we actually get slight improvement over HLOC. It shows that the kind of scene landmarks that we are learning are somehow complementing the landmarks that HLOC is using when it's doing pose estimation. Here is the real benefit of doing what we do, which is the storage requirement is a lot less. So the blue bar is HLOC, and all the learned methods of VSAT star and our method with the efficient net backbone is really using almost 2 orders of magnitude less data. Here's the same thing on a scatter plot. Y-axis is accuracy, x-axis is storage. So the red and black dots right, the left side, that's DSAC star, and black is our method. The black circles is NB plus SLB. So again, huge storage savings and reasonable accuracy. So here are some qualitative results for our method. If you can look carefully, there are some colored dots, not very easy to see, but those are the landmarks that are getting predicted by our method. So one of the important features is we often estimate pose from as low as 10 to 15 points, and we still get reasonable pose. So this is just showing that this sort of framework has a lot of promise to it. I think there's a lot of work that could be done to make it more robust and more accurate. But of course, there are lots of failure cases. Many of the failures that we have seen happen due to this ad hoc landmark selection method that we have at the moment. And so there's a lot of we think avenues for future work, trying to make the training more practical, like instead of doing training from scratch on every scene, it would be really nice to have a kind of common backbone that you can train once and then fine tune on different scenes. The big one I think is that our landmark selection heuristic is sort of separate from the learning. And so by the time we do learning and we feel that some of the landmarks are hard to train on, we don't go back and choose better landmarks. So doing them jointly, I think would give better results. So that's the end of my talk, and I've presented sort of these two attempts at trying to do camera localization while trying to preserve privacy, as well as trying to be sort of very storage efficient. And in some sense, this is sort of a new, especially the work we are facing at CVPR is trying to take a different approach, but it might have interesting avenues for doing lifelong learning in environments that change with time, which is still, I think, an open challenge for us working on localization and mapping. So with that, I think I'll end my talk. Thank you very much.
Hi, thank you. I will have a few questions in mind. First one is related to the first part of your talk. You model the feature by a line preserving the structures. Before people jump into the TMP, usually people want to hear this obvious outline using something like the train verification.
Yes.
with 5-point minimum hypothesis. Do you have something similar? Point to line minimum hypothesis.
Right. So I think what you're referring to is the scenario where you take multiple images. If you took multiple images, you can do some image-to-image matching before sending the features to the cloud, right? So it's a very interesting question because there are some works also by some of my colleagues that I haven't talked about that is trying to do privacy-preserving structure for motion. So they have a paper at ECCV 2020 where they first show that they can actually do this sort of, you cannot do epipolar matching, but you can do 3-view. There is a constrained 3-view that you can utilize. And their paper really goes into that. What we do is we say that we're sort of working on the single image case, but then we are sending these feature lines to the cloud. And in the cloud, we have a point, a 3D point and a 3D line. The 3D line back projected becomes a plane. So it's really a plane to point constraint that we utilize. But the other papers will have some more work in the direction of that.
Two more questions regarding the second part, the learn landmark-based map recognition. So the first question is it still like keyframe based or just point based?
The neural network based.
The sparse landmark kind of.
Yes, prediction. It's something that you would have to, typically you would want to run it on keyframes within a SLAM system. Our evaluation framework is all just single image. So it's the worst case evaluation setting, right? For a video, from a video we have sampled images. We're going to try to run the algorithm on each image as if it was the first image taken in the scene.
So in that case, the keyframe with the feature appearing inside one keyframe, the descriptor may not be, whatever you call it, may not be answered from that particular frame, right? Because we learned from a sequence of
it's learned from frames, video frames captured before in time. So we have to do the mapping. In order to get the labels to train our neural network, we have to run structure for motion. So, but we don't have to store the map. After training after doing structure for motion, we generate the labels, we train a neural network. Now when you're happy with the neural network, we can throw the mapping data away. And then at runtime, you only use the neural network to predict the landmark or locations.
Thanks. Last question, since you store sparse landmark in space, and maybe you just only use one keyframe to contain that landmark. What about this orientational invariance from a different perspective? Because we have a keyframe, then you can start the information from different perspectives, right?
Yes.
But you only have one landmark in space. What about this perspective?
We require a fairly large number of frames captured within the environment for generating our training set. So if I were to go to one of the slides where I show you the patches, these patches came from videos we captured, and so we extracted thousands of frames to generate these patches. The one I was talking about is here, this one. So these patches came from, so the more data that you can process in the mapping stage, and you want also the images to come from different lighting conditions. So at the moment we are collecting a lot of videos. If you can generate an image synthesis model to synthesize these images, then I think it would be great. But at the moment we have to collect a lot of data to get it variants.
Thank you.
Machine of the privacy preserving designs.
Yeah.
So an effective review discovered silhouette with what we find the silhouette.
The silhouette of the person.
You have on the line, you have the silhouette. If you have the silhouette,
yeah,
you know a lot about the domain what the find type is coming from. Now by running computer attack, I mean, as soon as you have a lot of queries to run, but obviously we already discovered the silhouette.
Yeah.
We've demonstrated already used for queries.
Yes.
So you can now know the silhouette now trying to, I mean, it's obviously in your example, it's obviously a human.
Yes.
So you can start showing humans in the image and see which one is closer and continue that.
Yeah. It is possible. You are definitely right. Like basically, if you are if you're willing to throw compute at it, and if you're going to make assumptions about what the scene has.
Sure, but I'm trying to say that the first basically we're using lines, and lines are very constrained. Already discovered tells you a lot about as the malicious part.
Right. So the reason we need these structured things is we generated instead of lines curves, then we're kind of throwing out, well, yeah.
So I'm almost sure that if what the parameter is taking and occupying feature space, and just the dimensionality will kill the type of thing.
That was the second paper.
Yes,
but the geometric one.
I'm fairly sure the first thing. The first method.
Yes. So what I would say is that I think in these kind of problems, we still haven't formalized the privacy question very well. It's a bit like saying that if you can hypothesize that person A was in this image, then I'm going to be able to do some compute with VNNs and reconstruct and say that this is likely true. So the more information, side information you have, it is possible to attack, I think, these privacy methods that we were exploring. And it's really hard to formalize it. But the thing that I showed earlier, where we were inverting the features, that works. Like a lot of people have replicated the results. It is inverting the regular features is easy. So this is at least making it slightly harder to invert. Thank you.
Any other question? Actually, I have a quick question. Actually, when you train those kind of landmark detection, you are using the traditional structure from motion, right? Yes. And that means actually structure from motion reconstruction results are largely affect the result of the landmark detection learning.
Yes.
Process, right?
Yes.
So in this case, when you try to detect the landmarks, it's something like, my understanding is the key here is you are trying to, from the landmark detection, try to reduce the number of the points that are more salient and that are more effective, right?
Yes.
And in the other thing, that is, if the maximum I try to enlarge all the landmarks, that is the same as the original 2D to 3D localization.
Yeah, you're right about that. So basically what you're saying is that in the extreme, we could have trained a recognizer for every point in the dense and 100,000 point cloud. The thing I would say though is that for us, I think there is some value in selecting landmarks because we've collected this data over time. We know that there are some textured objects that move around in the scene. So we are also using structure from motion as a big filter and trying to say that if we observe a 3D point in the same location over several days in several lighting conditions, it's acting like an importance filter to give us things that might be good clues to emphasize.
Right.
So we're sort of exploring that, but I think you're right that if we can scale up the landmark, if you can scale up the number of key points we can detect in these architectures in an efficient way. We don't have that now. I think there are some sophisticated methods, but most of the people doing human body key point or object pose estimation, object key points, they typically regress maybe up to 50 key points. So it's too less. Right now we are doing 500, but it's starting to get very complicated. It would be nice to scale it up.
You are trying to learn the best trader that can be first is efficient in memory and the timing, and then the accuracy right here. Cool. Any other questions from the audience? If no question, thank you very much, Dr. Sinha, and let's. The next speaker is Fan Deng. Are you here?
Yes.
Okay. Okay. Great. Dr. Fan Deng is currently the principal manager and engineer at Oppo Research, USA Research Center, and currently leading the Perception Lab on SLAM and 3D vision research and development. His work supports the development of prototypes and products of Oppo, including smartphones and XR HMD, etc. Prior to his Oppo's duty, and he worked at Qualcomm on computer vision and camera research and development. He graduated from UPenn in electronic engineering in 2011, and his current talk it will be involved in his work in Oppo, and from what I know, he has already developed quite a lot of engineering and research things that he's involved in quite a lot of devices supporting Oppo's mobile phone and VR and AR development. And for those you don't know, the Oppo and is actually one of the biggest mobile phone company right now in China, and quite a lot of people buying their in USA buying their +1. That is also one of the most popular high-level mobile phone as well. So Fan, thank you very much.
Yeah,
you can go ahead.
Okay. Okay, thanks. So thanks, Dr. Lu, to inviting us to this. We know each other for some time, and yeah, it's great honor to represent Oppo to speak today. So today my topic is practical VSLAM design for the real world, and I'm representing Oppo US Research Center. So there's a lot of
It seems like the sound is very small. Is it something like, can you speak a little bit louder? Or
yeah. Yes. Can you hear me now? Hello.
Yeah, we can hear, but it's a little bit loud.
Okay. Okay. Give me 1 second. How about now? Can you hear me okay?
It's better.
Okay.
It's better. It's better.
Okay. Yeah. Sorry about that. So today I'm representing Oppo US Research Center, and the topic.
It's getting worse again.
Okay.
Can you try right now?
Yes. Can you hear me okay?
Can you try now?
Yeah, they say they hear okay in the Zoom session.
Yeah, they hear it, but in the right now I think it's getting better. Right now in the on-site that is a little bit loud. Can you try right now?
Yes. Can you hear me okay?
Yeah, it's getting better.
Okay, I'll try to speak louder. Yeah, sorry about that. I can't join you in person today. But yes. Okay, so the topic today is practical VSLAM design for the real world. So the contents today, we start with this is contents, introduction, and some design. That VSLAM's design is involve mechanical design, hardware design, algorithm design, as also as a system design. That the experience for the past 2 and 3 years that trying to share it here. And also we try to look into the future, what's it going to be like for XR products in the future. So a brief introduction of Oppo and our research institute. So Oppo Research Institute, it was founded in April 2018. As of today, Research Institute has research centers and offices in Silicon Valley, Seattle, Japan, Beijing, and Shanghai, and Shenzhen. So we are here in Palo Alto, Silicon Valley, and that's what's our lab is. So our lab was called Perception Lab. Is currently based in Palo Alto office and is focusing on 3D computer vision technologies including VSLAM, sensor calibration, and the visual 3D reconstructions. So on the left side, you can see the prototype glasses, AR glasses we published in 2020 and the end of 2020. So it's a stereo camera based 6-DoF AR glasses and with a large display. On the right hand side is recent progress on the AR smartphones. So we're trying to bring this AR VR into the everyday users. So one of the features that people complain about AR, and actually Apple just released the AR Key 6 that focusing on realistic AR effects on the smartphones. So this is ours, and that's recording on the devices, and that's the real product right now. So the first step, for the past 2 and 3 years, for the first step, when we designed this VSLAM, we look at applications, and people know there's a lot of application for SLAM. Of course, there's robotics, there's autonomous driving, and there's also XR, HMD. When I say HMD, it's AR glasses. For the left side, you see there's a Magic Leap, and you see the Oculus Quest, and we also have handheld AR, which is for AR Core and AR Kit. So VSLAM is part of SLAM, but when we call it VSLAM, it's basically because the visual sensor is one of the very important factors to when you design these products. So that's a few examples of using handheld. And you may notice that there's when we design this application of AR on handheld devices, most of the time we're relying on single cameras. So with single cameras, inertial sensor excitation and the visual parallax was used to do these initializations. So if you have tried this on the smartphones, you notice that people have to move around to start this VSLAM. So when you wiring this with the AR glasses or VR glasses, of course you cannot do it. So that's why HMD with stereo camera indoors, we designed these sensors with the applications. You cannot rely on user to moving your head to start. So this larger visual FOV to handle fast rotation and textureless walls, and also if you want to use this HMD with stereo camera outdoors, you need proper triangulation for seeing in the 3 and 5 meter range. So when we say 3 and 5 meter range is most of the time in today's world, there's a limitation of the HMD that you have to have something inside with the texture within 3 and 5 meters. This goes back to the sensor resolution, sensor FOV, and also the computation load. So with that in mind, so Oppo has something really interesting going on. So we all know sensor physical models, which visual sensor model. How does this work in reality, right? So how does it impact? So if you look at this AR glasses on the market today, you notice really interesting is the cameras is visible to the users. So for our team, for Oppo, right? So Oppo say, hey, this industry design is unacceptable for everyday users to adapt to it. It just looks terrible. So so Oppo do have a stereo camera system, but you don't see it. So we basically what we're trying to do is strike a balance between industrial design and technologies. In fact, when you're trying to bring this product to the everyday user, this is something that we have to, from technology side, have to compromise to make this work. So what we did was adding extra layers of protective dark film to make camera module near invisible. It does affect our camera optical characteristics. So what do we do? So this is example. So film added potential distortion in irregularities. So for the normal fisheye, so there's a numerous studies say we have a fisheye model or pinhole model with distortions. It can be perfectly modeled, but once you add this thin film, this optical characteristic completely changed. So you can look at for the left images and right images. When you try to measure distortion irregularities, you can see these reprojection errors going much bigger if you're just using the regular optical sensors models. So that's something we try to solve. This is not solved theoretically, but solved in a practical manner, that we have to work with the materials and work with mechanical engineers to see how to put this film at one time at the same time make it nearly disappear, but at the other time won't affect this camera modeling. As a matter of fact, there's another method. If you can't model this camera, you can do something else, and you can do these lookup tables, basically mapping all incoming light rays. Sometimes you have to differentiate between RGB as well. Instead of doing calibration model, but you're using a mapping models to do this real-time distortion corrections. So another problem with this film is the nice in the nature of fisheye image sensors. So when we talk about fisheye lens, they have a very interesting optical characteristic. We call this lens shading. So if you look at on the left, so this is the gray value, even though it's the same lighting conditions, but you can see on the center, the image is much brighter than the images on the edges. The problem that is this will affect our feature matching, feature tracking algorithms a lot. So if the feature matching heavily relies on luminance levels, so we need heavier lens shading corrections and noise reduction on the edge area of the fisheye images to correct that. So we have the same feature with a dramatic difference in illumination levels on the stereo camera systems. So on the pictures on the right, there's a stereo camera scenarios. So as you might know, with familiar with stereo system, the same features appear at different location of the images, and you can see that if you look at it closely, that the illuminance level is quite different. So more talks on the sensors. So that's the sensor itself. How about the sensor configurations? Sensor configuration is very important as well. So if you look at this different sensor configuration for different products, Oculus Quest, AR glasses, they have this 4 cameras, and sometimes they have 2 cameras. And sometimes these cameras are looking straight forward. And sometimes these cameras are looking sideways. So on the current stereo camera system, when baseline and the resolution limits, the depth limits less than 5 meters. So the configuration is very important to how to place them. So this depends on the FOV and sensors. So one example is if you're trying to wire these glasses indoors, and the indoor environments, they most likely you can see something that within 5 meters. But if you're going outdoors, maybe user may be looking up, then they're looking at the skies, etc. So these sensors, this baseline will lose track So that's why sometimes we'll need to configure these sensors, sometimes looking down. So make sure that something is visible in the correct distance for the VSLAM system to work correctly. So that's why we have these prototypes developed. Other than the stereo camera system looking forward, we have this adjustable FOV and angle with a swappable lens that doing all this kind of experiments to find out what's the best numbers, and that work with our VSLAM algorithms. So this is about the robustness of the VSLAM. So camera looking down, make sure VSLAM sees object from ground, which will be within 5 meter distance. Camera looking straight will lose stereo information if the user go outdoors and looking up. So the second step, once we have the sensors configurable, so the next step is how about the accuracy improvement in the real world? So in the real world, accuracy and latency is of very important factors. If you look at this, we have this typical VSLAM system. We have backend, you have front end, you have map, you have post, and then from the application level, you have rendering and display. So are latency requirements different in different application devices? So for our study, yes. Can we achieve universal real-time performance on all platforms? That's a big question for us. If we try to do in the smartphones, that's something we need to solve. In our study, AR, augmented reality glasses and HMDs has most strict requirements on latencies. This based on studies how user can see it. So, for example, you look at this typical VSLAM end-to-end system latency. Noticeable latency on AR HMD is huge. So we have to reduce this latency as much as possible. But noticeable latency on smartphone is relatively smaller compared to the AR HMD. So in that scenarios, we can tweak your algorithms to make sure that the performance was better. So with that in mind, as latency is so very important, especially image-related algorithm, we find out that the image processing is of the bottleneck and in terms of latency on the smartphones. Real-time performance means less than 60 milliseconds in our scenarios, processing on CPU. Modern embedded CPU frequency won't maintain this high frequency for more than 10 minutes under the most circumstances. So we have to carefully select our algorithm combinations to make sure this does work without sacrifice accuracies in the embedded system. So one of the example is in terms of image matching and tracking, we do NCC is better on optical flow, it's better than the feature descriptor based matching. So in terms of feature corners generations, we found that fast is better than Harris, and it's better than the good features. So also the other things we develop our own OpenCV, it's comparable to OpenCV, but it's much faster and much easier to use and optimized on our Oppo smartphones as well. So it's easy to use, consistent result in multi-platforms, and without copyright problems. And we can also take advantages. If you look down the platforms, we have ARM and DSP and also computer vision processors. There's a lot of computer vision accelerators these days, and also DSP. So another algorithm improvement we've done is faster stereo matching without rectifying whole images. So many people doing this mass, especially on the fisheye images, when they do the stereo matching, sometimes they do the on-distortion. But on-distortion, this is very costly. So instead, we only search only limited areas which satisfy epipolar constraint using lookup table. So with that in mind, with that method, we can achieve less than 3 millisecond processing for 100 points matching on smartphones and on stereo VGA images. That's 400 or more speed gains in stereo matching compared to traditional stereo matching method. Another things about accuracy improvements is about the non-linear problem, solving non-linear problem, which is BA problem, which common as a backend for this VSLAM system today, modern system. So oftentimes require double precision to converge, especially with series or G2O. So we don't use them. We try to use single precision to solve nonlinear problem with our own customized nonlinear solve. So there's a couple benefits in terms of industry. Start from industry standards. One of them is take advantage of faster DSP cores. So if you look at the vision DSPs nowadays available, Qualcomm, MediaTek, Cadence, or SensePro by CEVA, they only support fast single precision processing. So with us, also the second benefit is take half the memory and also the faster convergence speed in solving BA. To get to the single precision, of course, you lose something, but we managed to do it without lose something, but without losing the accuracy of the VSLAM. So we did actual condition when checking Jacobian matrix value problems. We're changing order of a residue value because we can do all this by ourselves without going to the series. We redesigned the cost value termination conditions and choose different linear solver on different conditions to avoid EO condition problems. So with that, so we have 20% speed gain on the smartphones. So algorithm development, the other thing is a loop closure and mapping of a necessary module to maintain this long-term accuracy in terms of for the VSLAM. And the previous talk mentioned that the storage problems, and that indeed is a big problem. So storage remains a big problem. Limitation of common loop closure mapping. There's a lot of research on how to reduce the storage. But in our cases, we have not only the algorithm side, but only looking at the use case scenarios, how to make this storage usage smaller. So map could only, in our case, could only cover a small part of the surrounding environment due to mini-sized memory requirements. That's our requirements. So we introduced special map management, which reduce storage requirements while maintaining important relocalization accuracy for key usage scenarios. So one example you can see here with real-time testing on smartphones. We can remain this relocalization accuracy of 500 meters of trajectory with only 20 megabytes of memory usage on device. So this is all running on device. So we only use 20 megabytes of mapping storage. Okay, so next topic we are going on with the system. So modern day systems you can do on robotics, on smartphones, or HMDs. A lot of times they are not real-time systems. So in reality, these resources always competed among different applications running at the same time on the device. So if you look at the left side, that's 3 different configurations and the hardware types for HMD. first one, one of the example is Magic Leap. So one example is HoloLens from Microsoft. So they don't all do it by itself. So everything, batteries, everything is within one piece. The second one is, the second type is a smart display. So everything computational required is running on a separate computation devices. So the glasses only do the display. The third type is everything real time is running on glasses, including VSLAM, ATW for rendering. Is running on glasses, so it's close to sensor or also close to the display. But application-wise, 3D rendering is on the computation device, on separate devices. So this leads to, when we design this system, we want to this low latency real-time sensor data access, as well as close to the display and rendering. And this involves how to access and arrange different computation cores on the modern day chipset. Another thing about the VSLAM is the calibration. So we all know calibration is an important step before you running any VSLAM. So but calibration consistency is of very difficult problems, especially when you once this device is out in the user's hand. So we have these two things. We have this factory calibration, and we have a online monitoring system. Monitor this device after this device is on user's hand. So once users know something, we monitor something is wrong, we design post-processing. The user can do it by itself. So on the right side, so this is a demo of how user can recalibrate based on the factory calibration result to make sure the stereo system is correct. So lastly is VSLAM. A lot of times is the display. So this 4K AR video feature recently is announced by ARKit 6. So if you're familiar with the VSLAM data requirements, it prefers low resolution. It prefers, it's maybe not no resolution. It needs real time. So most of the time, the sensors nowadays, they do less than VGA. They do prefer the fixed focus cameras and no exposure time images. So while user, when they trying to use this AR, VSLAM enabled AR applications, user prefers high resolutions, sharp, which means autofocus on, clear, and with AE on, and images. So with that, we have using two cameras for the smartphone cases. So one camera only for VSLAM, the other cameras for this rendering. So this involves some timing issues and additional calibration issues to make sure this 4K video resolution AR effect is as realistic as it can be. So if you look at the computators, these two images examples nowadays, if you take the AR pictures, a lot of time the background is blurred. So this happens to a lot of AR core devices. But if you are using our device nowadays, we can ensure that the 3D virtual object as well as the background is as clear as it can be. So with that, I have two examples here. So this is recorded on our smartphones, and it's very realistic. It's not a Photoshop result. It's a real recording result. You can see the background is as clear. Also, the effect is very good. Okay. So next one. So what the demos did here, if you're looking through the pictures, they are very in details. So so we put a virtual room in our office. So these trees are actually fake. So it's a virtual part of virtual environment. So then you see our office, the doors there, and so another SLAM visual system problem is a lot of research has studied how to manage your map. So I just talked about the storage on devices, but how about large scale? How about multiplayer AR and using this map and the persistent map that you can eventually combine virtual world and the physical world. So reducing storage on local is the first step, but eventually you need to store enough mapping all over the world and on all devices. You have to find the global message. So with that, that's our past accomplishments. So looking to the futures, we are looking at the better visual sensors. That's one of the study we've been doing. Maybe higher SNR, maybe higher resolution.
Can you give us a couple of minutes? We are trying to figure out some here.
Okay.
Now it begins to work. I think it's on this side.
I think you should be all right. Asking
Here. Is it something here? It happened?
Yes, sir.
Turn off?
Yes, sir.
Okay. But you can go ahead, I think.
Okay. I hope not. I hope I didn't miss any points that.
Yeah, that is why I have to open the transcript.
Oh, okay. So so looking to the futures, better visual sensors, higher SNR, and maybe higher frame rates, or maybe just get rid of non-important features of the images that is not contributing to VSLAM. So maybe DVS. So we've been looking at this for some time. So more robust sensor configuration study for various use scenarios. To better handle the computation problems, maybe we are doing some customized ASIC for dedicated computing resources. So that can help with our smartphones and also help with the HMD. Also, the other part of the system level is low-level optimized efficient operating system that to make sure that VSLAM has everything it needs with lower latency. Large-scale sparse mapping infrastructure and cross-sorted map generation and merging. That will roll out with because of the 5G. They have the 5G, maybe it's a Wi-Fi 5G. A lot of because these days 5G has more servers compared to 4G towers. So a lot of people are considering using 5G servers as to store this local information. Maybe it's the map. The other part is to learn high-level image feature and semantics for all-day relocalization. So these days, relocalization is still limited by a lot of factors, including time, illuminance, also the feature to describe the same environments, also the moving environment as well. So we are looking at semantics to try to move these relocalization technologies as close as what a human trying to relocalize themselves. The last part is a 3D representation and efficient reconstruction. Actually, we have a collaboration with Tsinghua University, and we have a CVPR this year, Aura. It's called INSCOM. So you're welcome to join the oral sessions there. So with that, that's all the presentation today. Thank you.
Thank you, Fan. I'm sorry that the talk was interrupted with the device problem. But yeah, anyway, the video is recorded, and later you can also review the streamed video and to see the talk. And if you feel you didn't get all of those, any questions from the audience? Fun. Is you mentioned about the library developed by Oppo, and will that library be public, or is already public, or will be public, or you just want to use it in the internal applications?
Right now, everything we develop is proprietary. As we have mentioned that the technology we developed is heavily relies on the hardware configuration that the devices we use. So it's not public yet.
Okay, and right now you are using that for the mobile phone, or for you guys AR devices, AR glasses, or other applications, or you use both?
So we have we support. So let me go back here. You start. So we support both AR glasses and also the smartphones. So but they have different sensor configuration. So we have slightly different tweak the solutions.
Okay, so do we look forward in the near future we can use the Oppo's mobile phone to do quite a lot of AR things in the near future, or is already in the app in Oppo's mobile phone?
So the smartphone solutions right now do have our algorithms supported, but right now we are still trying to find out what's the killer application and the use case. So maybe at the end of this year we can look in. Maybe you can experience some of the applications. It's not AR, but using VSLAM. So VSLAM has a lot of use cases right now. So maybe at the end of the year.
Okay, cool. Yeah, I really enjoyed this kind of talk that is really practical, that gives us how to improve the SLAM efficiency and from the engineering side. And that could be involve quite a lot of research as well. If there is finally any other questions? Okay. If there is any other questions, thank you, Fan, and look forward to see you in the future.
Yep. Thanks. Thanks. Bye.
The next one is the paper presentation from Zipeng Fu. Okay, and he's from CMU, and his collaborators are from other researchers from CMU and UC Berkeley. And his title is Coupling Vision and Proper Reception for Navigation of Legged Robots. Okay, if you are not on Zoom, do you want to are you right now on the work? 然后可以看一下的数据。上来，你先过来，然后你试一试那个 second screen。这个可以的。好像没有。我给你转，我给你弄过去，你可以这边是。嗯。Sorry, he wants to have a adapter. What about we have early break and getting started, change the schedule a little bit while waiting for him getting the adapter. We can get back at 3:40 if that works for you guys. Instead of waiting, right?我给你的时间换了，这样子的话，这样的话不用说是你的时间减少，这样的话3:45这样就是说 coffee break 就是提前告诉你 coffee break， 这样的话你的时间可以多的是10分钟以后讲，现在那个10分钟的 break。然后你可以现在试一试它现在。你现在可以做 presentation， 你那个什么拿这个连上去。不过你这个你需要一次看时间。好，这样进入以后，现在跟这个现在是 different。I want to be better with my the microphone over there. Right now, people can still hear that and from that instead from other ones.
I see.
Sorry for the change of the schedule because of emergency. And then let's get started for the last session in our today's talk. 资鹏 who will give us the talk in his research, which is learning to talk, learning to walk, and navigate by vision and proper reception, and he is collaborating with his team from CMU and UC Berkeley.
Yes, thank you everyone for being here. So I'm Zipan Fu from Carnegie Mellon University. I'm going to give a presentation on learning to walk and navigate by using vision and proprioception. So this is a joint work with Ashish, Kumar, Ananya, and Audrey, and also with Deepak Asa from CMU and knowledge from UC Berkeley. So since it's robotics like paper, so I'm going to go first like on real world robot demos. So as you can see that like all the videos are happening in real time, and the robot is trying to walk is very difficult because the concrete can get stuck underneath pretty easily. But it can get out by using Odometry, and it actually succeeds in traversing the tunnel. This is similarly like a pretty challenging terrain where there's steers cycling. The robot, even though it's very cycling, can still maintain balance, stabilize once it covers the steer. And in addition, robots are very robust to unstable route time, which is pretty challenging. And the speed of the ground are assuming it's static. In this case, it's definitely not static, and the ground is. And yeah, this is another result of slope-free vegetation environment. And even though the robot is kind of sliding, it's still manually moving forward. And we also show different kinds of motion and how it gates, basically lag motion in different speeds. So when we command the robot to move at like very high, around 1.6 meters per second, the robot learns to gallop and bounce with a pretty long flight phase. Basically, all the feet are not in contact with the ground and are all in the air. And in previous demos, the robot used only proprioception, which includes like joint information for contact and IMU information. In this scenario, we activated the vision for the robot mounting an RGB camera on top of the robot. And we can see that the real-time like depth dimension are shown on the bottom right. The map is still incrementally online, which is shown on the top right. So all the computation are done on board, and it can like avoid obstacles and find its way. And yeah, the only information that we provided is like point cloud information, which in this case is like 65 meters away from the starting point. So yeah, for this presentation, I'm going to go through 4 iterations of our robot, like each of which are built on top of a previous version. Eventually, the robot learns to walk and navigate by using vision and proprioception jointly under a large variety of scenarios and environments. So let's first start with how to get the robot to actually do something reasonable in the simulation and do something robust. So we formulate this problem in reinforcement learning setting. And the hard part is trying to ensure that the variety of simulation environments like matches the real world. As you can see, the terrain is full of up and downs. So yeah, let's first solve the problem in simulation. And we want to train a policy that actually can handle a diverse set of environments. And the robots actually takes the current state in a compressed version of ground truth environment parameters and take it into the policy. This kind of environment parameter can be anything that is accessible from simulation, including like the mass of the robot, the center of mass, turning friction, etc. We are not using a generic policy like a domain randomization version policy for all environments, but we are using an adapted one. So the policy knows what it's dealing with through this kind of compressed environment vector, which we call environment intrinsics. So these are pretty standard, like reinforcement learning training in simulation. So how can we actually deploy a policy that we train in simulation in the real world? It's a pretty challenging task because there are two parts. One is the sim-to-real gap, and the second is since the environment in real world is constantly changing. For example, the friction it's not constant. It's like constantly changing. So how can we do this kind of rapid adaptation for our robot? What we actually do is in real world, because the environment parameters are also not inaccessible or hard to estimate accurately. And so how to actually get this kind of environment extrinsics is pretty challenging. For example, imagine that I can measure some about the environment parameters in my living room, but like it will catastrophically fail to work in any other kind of environments that we show in the videos in previous slides. We solve this problem by using rapid motor adaptation, or we call it RMA. So the key insight is we can estimate the extrinsics from onboard sensing, and we collect all the onboard sensings into a sequence, which we call observation history. We need a adaptation module to convert the observation history to actually estimate the environment intrinsics online. And we continue doing this in a rapidly updating fashion. So the training scheme is as follows. We use a supervised learning paradigm because we know both the vector of extrinsics from the simulation and also the state history of the robot in the simulation. So this adaptation module can actually estimate the extrinsics, which we cannot measure directly from onboard sensing, but from observation histories. So this is like a classical supervised training paradigm. At test time, the adaptation module estimates these unknown extrinsics online, and due to limited onboard compute, this module can execute asynchronously. So the key takeaway is that we just train one policy to adapt the robot in different kinds of environments where the underlying environment parameters are drastically different. So this part we show some analysis of the adaptation module, trying to see how we can visualize the predicted environment intrinsics. So the setting is like a oily surface and plastic wraps around the feet so that we can decrease the friction between the feet and the yeah, as you can see, the robot can still manage to move forward. So we plot the first dimension, the fifth dimension of the intrinsic value here to show how the robot adapts according to the environment. And as we can see, as the robot senses the friction that decreased dramatically when the feet get in contact with the plastic sheet that is covered in oil. The extrinsic predicted thermal changes and in that kind of state to notify the policy that it's currently operating under certain conditions that requires it to maintain a stable kind of pulse to move forward with the location. So yeah, so now we have introduced the way to how to deploy adaptive policy on real robots. The next question is like how to get the robot to walk at different kind of velocity without hard coding the gates. So these are the results. So in the bottom row, we plot the foot contact patterns. So basically, like the color is solid, and the subcontact is the ground. And as we can see, at low speed, the robot can learn to do a slow walk, and at medium speed, the robot learns to trot with a diagonal feet asynchronous. And at high speed, the robot learns to gallop, where there's a flex base. All feet are in the air. So classically, these kind of gates are programmed into the controller. So, which is pretty different from our approach, where the gates just emerge from one without any controllers or files. So why do we get different kind of gates at different speeds by using our methods? So one, we borrow some key insight from biomechanics. So one common theory that gate emerge because animals want to choose a gate that save energy at certain speeds. So in this plot, the horse chooses the trotting gait at medium speed because it wants to save its unit oxygen consumption, which is a surrogate measurement of energy consumption. And similarly, the horse chooses to walk at low speed and gallop at high speed. So we formulate this kind of energy consumption penalty in reinforcement setting by adding a term that penalizes the energy consumption. And we get a similar kind of plot by like comparing our robot and the horses. So this kind of validate our assumption that maybe energy that people studied in biomechanics, it's actually a pretty good kind of a cost term for our controller to learn natural gates. Here we show some more results that the robot is kind of robust. In this case, the robot just learned to trot through like grass fringe. And even at very high speed, the robot even like robust to like abrupt human pole. So this is like some slow motion version of the pyramid. So in this video, I just pull the robot to the side, and the robot still can maintain the balance and move forward. Okay, so we have a general like locomotion policy that the robot can adapt to different environments and can operate at different velocities. So velocity, I mean by different speeds and different angular velocity, angular speeds. So now we're gonna focus on how the robot can move with vision, because before this part, the robot learned to move by using only proprioceptions, which means the robot is blind. But like in order to avoid obstacles and reach goals, the robot needs to use vision. So this kind of like topic is like widely studied by the community of navigation. So this is like a point goal navigation task, where people in mobile navigation study this by using real robot, and the robot can get to a goal without colliding with obstacles. So what is missing in the previous prior works? So the first one is the navigation is not actually aware about the capabilities of locomotion system. And we are going to solve this by making sure that the navigation system is aware about the low-level locomotion capabilities. And the second point, I think the prior works are missing to address is there's only vision is used for navigation. And we're going to use both vision and proprioception to navigate our lag robot. This is a work that is going to be presented during CVPR, and yeah, it's a joint work with of Carnegie Mellon University and UC Berkeley. So recall that we already have a lot of condition model, so the prior work is used a joint signal model to teleoperate the robot. In this case, we're gonna operate the robot by actually using a planner that can lead to no lesions of the robot and obstacles and reach some goals. So as we can see, we use two cameras. The first one is Intel RealSense RGBD camera, and the second one is a tracking camera for pulse estimation. And we use both information to construct and update an occupancy map online gradually without any prior information about the map. And then we use the information of the map to construct a cost map by using fast marching method, which gives the command for the robot to follow at next time step. And all computation are done online without ground truth map. But notice that the current version, in the current version, the navigation module and locomotion module are decoupled and operate separately. So in the sense that the navigation module is unaware of the low-level locomotion capability, and locomotion capability cannot give feedback to the planner. So how can we solve this problem by actually couple the navigation and locomotion? We introduce a safety module that can do this job. So the safety module is going to look at the proprioception history of the robot, which includes joint information and foot contact information and IMU information, and use the kind of history of proprioception to give feedback to the visual planner. So the safety module is aware about the walking policy because the input is exactly the history of proprioception. And it allows the visual planner to optimize this plan according to the capabilities of the walking policy. And there's two parts of the safety module. The first part is a fall predictor, which given the proprioception history, it predicts if the command speed is dangerous for the current environment. In the sense that if this predictor predicts a fall is likely, then it overrides a command speed from the visual planner by decreasing the command speed by a certain amount. In this paper, we use 0.2 meter per second. Yeah, this is a safety. This is the fall predictor within the system. So in this experiment, we try to visualize what does the fall predictor actually does. So in the top row, we plot the prediction out of the fall predictor, which predicts the probability of the robot falling. So if the probability is very high, the module will actually override the command from a visual plan by decreasing the command speed. So the robot can decrease the speed and ignore the command from the navigation system and maintain a safety limit without falling. And in the bottom row, plot the raw speed command from Visual Planner, compare with the actual safe speed command that is being overridden by the low-level safety module. And the second part of the safety module is a collision detector, which also given by the same proprioception history, we predict whether the robot is actually in collision with something. But for example, one use case that some obstacles or many obstacles cannot be detected easily by RGB camera, for example, like a mirror or glass windows. So yeah, this is like a collision detector within the system. So we did this kind of experiment where the robot trying to move forward, but like on the way between the goal and the starting point, there's a glass wall, which cannot be easily detected by the RGB camera, and which is actually shown on the right. We plot the online constructed map where we cannot actually see the glass window. But by using this kind of collision detector, the collision is very high. The map will be updated with this kind of locomotion proprioception information. And we do replanning every 0.2 seconds. So the robot learns to move around this window with the updated map. We also have some comparison of our method, which is using vision plus proprioception, compare with the baseline, which uses only vision. So yeah, this is like a similar transparent glass setting. By using vision and proprioception, the robot learns there's some kind of obstacle that cannot be easily detected by vision, and updated its occupancy map accordingly and get around with the obstacle. Another kind of example is that outside of the view of the camera, the robot can learn to update its map by using one. Due to the time limit, I would just skip this version, which the robot can also operate at night, because this proposition does not depend on the light conditions. And yeah, this is kind of like a more performance video where we show both like the safety modules running on board, where the robot can actually detect there's some kind of dangerous environment and increase the speed, and also detect transparent objects on the way and update. So yeah, we also have some simulation comparison, and in real world comparison, we also performs better than the approach that use only vision. So yeah, so this concludes the whole version of our robot, which learns to walk and navigate by using both vision and proprioception. And of course, there are many kind of ways that we can extend our robot. Like, for example, we can actually combine manipulation, locomotion, and power. And the robot arm is trying to maintain the balance of the bonds. And also combine vision with locomotion, where the robot learns to walk. Yeah, so that's for the presentation. And here are some like website links for people to check the exact papers in this presentation. And I'm happy to take any questions.
Thank you. Perhaps I have a question. And I saw you mentioned you train on the simulated environment. Did you transfer that into the real environment, or you just you do?
It's like a zero-shot transfer in the sense that we don't use real-world data, but actually increase the difficulty in simulation is kind of enough for the generalization.
Okay.
Yeah.
Okay. Thank you very much. Now let's welcome the next speaker.
I don't have audio. I don't have audio here.
Audio on my side.
I share the screen in Zoom, right?
Right.
That's the only
Yeah.
thing I do.
Works great. Yeah. Let's see here. Actually.
Great.
Okay. Let's welcome Dr. Costas Danielidis, and Professor Danielidis is Ruth Young Dawn, Professor of Computer and Information Science at University of Pennsylvania, where he has been on the faculty since 1998. He's an active fellow, and he was the director of Graph Lab and from 2008 and to 2013, and associate dean from graduate education from 2012 to 2016, and the faculty director of online learning since 2016. He was also the associate editor of Army Journal, and he was also the co-chair of Attribute 3D PVT in 2006, and he was also the program chair of ECC 2010. He received the Best Conference Paper Award and from ICRA in 2017. His research has methodology fluency research on visual odometry, omnidirectional vision, 3D pose estimation, 3D registration, and eye calibration, structure promotion, image matching, and actually this is also reflected by quite a lot of people have listened to his public online lecture, and at least I watched quite a lot of his lecture. And his main interest today is on geometric deep learning, state association, event-based camera, and vision-based manipulation and navigation. And today he will give us a talk on the topic of from semantic SLAM to semantic navigation. Welcome.
Thank you very, very much for the kind introduction. And it's really amazing to be back at CVPR. My first CVPR was in 1993, to give you a perspective here about how long the conference has been. And in 1993, I gave a talk about structural motion. Today, I'm going to give a talk about SLAM and semantics. So, we did a lot of research for many years on visual odometry and visual inertial odometry. And in 2017, we said, what about introduce semantics in the problem of both localization and mapping, and study the hypothesis whether semantics help in localization, and of course whether we can build a map which is not only metric in terms of an occupancy, but also with enriched with objects, because we need the semantics for both. All the maps that we use are not just CAD models, they have labels, and we need it also for human-robot interaction. And this kind of semantic SLAM we have used has been used also for reactive navigation by the group of Dan Kodicek, where a robot has to like navigate by abstracting the objects using their geometric models. So in the classic SLAM task, we focus a lot on localization for the purpose of augmented reality or VR, or in general for GPS-denied localization. And whenever we do the mapping, we usually run the mapping exhaustively in order to build the map of the whole environment. In the best case, running a frontier-based exploration. And the result of this, we use it either for metrology, really to see how to measure things, and also for planning. But in order to do any other downstream task, like going from A to B or following directions, we really need first to create the whole map. And the whole map, it has to, as I said, it cannot be just occupancy. It has to also be enriched with semantics so that we can give much easier directions. So the main theme of this talk, in addition to semantics, is that how can we navigate in an environment where we take observations from the robot, like from an egocentric point of view, and without access on a map. So how do we do that in a completely unseen environment? And I will just show two slides on a still metric task, which is going from A to B, when somebody gives you the coordinates of B with respect to your current location A. And this is called the point nav. Both point nav and what I present object nav have been created from computer vision people at FAIR. And in the point nav, you are just you're dropped in a novel environment, and you have to just follow something that says go 5 meters north, 3 meters west right at the start, or a bearing at a distance. And this is how it looks like in a scene where you are given both, you're given a depth map and an RGB, and you want to go to the goal. And obviously, you can do the whole mapping, and then it will be very easy to apply just any planner in order to do that. But this would be really the most inefficient way to do that. So what we really want to do is to predict what obstacles we're going to encounter on the way from A to B. And in order to do that, we really need to hallucinate how the environment will be. So we need a kind of prediction about how environments look like in general in the task of point nav, just in terms of occupancy, and in the main task I'm going to present here in terms both of occupancy and semantics. So in the task of semantic navigation, we which exists as a challenge, the object nav challenge. You're starting again from a random position in an unseen environment, and you want to find an object of a specific class. For example, find a stool. And I'm going to present here our approach, which has been published at ICLR 2022. So we assume that we are given an RGBD sensor, and also that our odometry is given by an oracle. And we are working on how to do that with combining it with an odometry, given odometry from a different like algorithm. Just for your information, for the task of point lab, there is a paper by Alexander Swink on how to combine both odometry and the point lab task. So the environment is the Matterport 3D. Many of you might have seen it. It is a simulation environment, but made from the constructions from real environments. And these are environments with a very high visual complexity, with a large layout variation. And with these are not big halls like convention center. You have very limited visibility. So you observe only always a very small part of the environment. And in order to navigate efficiently, we cannot really do that with an exhaustive search in the environment. This would take forever. So in this goal of semantic navigation, you are given egocentric observation, and you want to take the actions that will get you to the semantic goal. And in order to do that, you have to predict where this goal will be. And this first part, how to predict where the goal will be, we argue that you need to build a map to learn how to predict maps, so even for the invisible parts. And for the second one, after you have predicted where your semantic goal will be, you can still solve it with an A to B solution for the point goal navigation problem. So we predict that this is, for example, 2 meters at 30 degrees to the left. After we do the prediction, we can run a metric navigation task. So in the related work from Shaplot and others, also from the FAIR group, usually you're detecting objects with off-the-shelf detectors, and you try to predict where the object you are looking for is, and then you are applying a policy in order to find it. So in our approach, we have an active approach for mapping, first on how to learn how to predict, and then again an active approach on how to select the goal. So just to describe you, you're given an RGB and the depth. Then you do a semantic segmentation of the scene. You back project it on 2D. So everything I'm showing today is only 2D. You have an occupancy map here, M. Then you register them over time of the previous one, and you try to predict first where your goal will be, for example, the sofa, by using an associated uncertainty map. And so the first thing is really that you predict beyond what is your line of sight, the semantic beyond your visible parts. And after we predict where is the goal, then we apply a policy in order to reach this goal using confidence bounds. So how do we learn how to predict this map? We are using a depth reprojection, as I said. semantic segmentation. Both of them are projected. And then we are predicting what we see beyond the visible by using in a grid, by using again a unit structure. Now, how do we do that efficiently, even during the training approach? So during training, we want really to not exhaustively again explore the whole environment, but we want to take steps towards places which give you the highest information gain. And we define the highest information gain the way it is defined in Bayesian active learning as the place where it has, if we visit the place which has the highest model uncertainty. So there have been several approaches, and there are many good results, for example, from Gary Gall and Alex Kendall on how to model this uncertainty. We have experimental, I will show you an experiment about these different measures of information gain. But at the end, we decided to follow the ensemble approach as proposed by Lakshminarayan and later also applied by Deepak Pathak, the senior author of the previous paper. And this consists on computing the variance of the outputs of our semantic segmentation. And this is the way it works, is that we use several actually networks, an ensemble of networks. We take the mean of the softmaxes at the end, the expectation, and this gives us the probability, a marginalized probability over the weights of the network. And then we take the variance of the softmaxes as an estimate of the model uncertainty of the network. And we choose to go while we are learning, while we're training, we choose to go to directions where this variance is the highest. So to give you an idea how this works, you have here on the right the ground truth map of the environment. And you see, for example, there is a high variance in this location where the cushion is, all right? Or here you see that there is quite a variance on predicting what is around the bed. Again, with much enlarged cushion, or even mispredictions of where the table can be. And these are locations where we are uncertain. Not only first, let me repeat, these are not just on our line of sight. These are not just semantic segmentation of the image. These are also how certain we are about the prior distribution of such environments. And these are results on how we just predict semantic maps before even solving the semantic navigation goal. And we show that our active learning to map approach yields of a 68% accuracy in the occupancy and a 33% accuracy in the semantic prediction. So this, you see that this is still quite low, and this we might have seen this also in other semantic mapping approaches, which really predict by the environment. So this is how we chose to use the variance. The first is what we call offline, is just taking random samples during training. The second is just the predictive entropy itself. The third is the mutual information. The fourth is the variance in the ensemble. And we see in both the IOU and the F1 score that the variance gives the best results. And this has been found also by Lakshminarayan and others. So we see also quite a variation on the based on the actual things that are predicted. And what we found is that our active strategy achieves a more equal performance across the semantic classes. So these are some qualitative map predictions, again with the ground truth here, and here is the semantic prediction. But let me switch to the object goal navigation. What happens after we learn how to predict what is in front of us and what is behind the walls? And in order to select our object goal, we use both the mean of the output of the ensemble as well as the variance. And both of them have a different meaning. So the combination, for example, when your confidence is low and the variance is low, it means that we are fairly certain that the target is not at that location. And using a combination of the confidence and the variance, we can follow two paths, two kind of policies, either to safely go to the goal by taking the lower bound, or to explore by taking the upper bound. These are ideas that are coming from the bandits literature. And skip this. These are like the object goal navigation results. I repeat that this is how to find a specific object, find the sofa or find a stool in an unseen environment. And so this is our approach with active learning, and the upper bound policy for goal selection achieves 34%. ANS, what we call here oracle stop, I will explain it. It really means that there's somebody who stops you even if you don't know it when you achieve your goal. And the ANS is from Saplots et al. And the SEME-EXP is again from the same group, but from a more recent paper. So this is like qualitative results of finding from the task of finding the table. And you see here that this is the semantic map that we are building. And here is the uncertainty while you're building this map. Both are during the inference task in the unknown environment. And here is the projected observations, like just what you see every time. And this is what you predict always from the negocentric point of view. We did also an ablation analysis that shows the importance of the maps and how good the maps are, and how good is the selection of the goal selection. So this is when we use our semantic mapping approach plus the ground truth path to the goal. So after we select the goal, how we can do the shortest path. And we see, and the oracle stop is again when somebody tells you that you are in the right position. So we see actually that we are not doing in the full system here, the top. We're not doing that well by detecting whether we are at the actual place. Probably we need a monitoring there in order to increase the performance. So I talked about a lot about the motivation for semantics, which is the vision, language, the interaction with the robots. And I'm gonna very shortly present a few slides from our poster next, then paper here at CVPR next Thursday. So the visual language navigation is that again that you are dropped in an unknown environment, and you are given an instruction like the one you read here on the bottom, and the goal is to follow this instruction. This is a very challenging task. It really reflects the foundational problem of grounding language into what we see, and also building a spatial representation. And what we argue here is that maps is pretty much all you need in order to solve this task. That if you are able to build good maps, then that you can quite well follow the instruction. We further argue that when we learn semantic maps, that it would be beneficial to do it by following the language instruction in order to predict the path, and that this learning of the map, which we do with a cross-modal map attention, this cross-modal attention between the map and the language can really create also better maps than just using vision. And so this is the whole model here, which on the top really is pretty much what I presented with the language to map. But here there is an cross-attention model with the language, and then a second cross-attention model which produces the input to a path prediction that is then trained using examples of paths. So this is a qualitative result. In the middle, it is our predicted path. What we do is we predict 10 waypoints, and then we always choose the closest, and then we repredict. And the ground truth is here on the right. And if you read actually the instruction, you see we go and get indeed here past the table, and we go between the kitchen counters and walk straight, and we finish between the two shelves. This is an example of a successful actually following of the instructions. Here is another one: exit the bedroom into the hallway, turn right, which we do well, and into the doorway on the left, stop in the middle of the bathroom next to the bathroom sink. And we do that by using, as I said, our learning to map approach, plus a cross attention with the language. So this is presented, this is the poster 209B, Thursday afternoon. And this is a collaboration with the group of Dan Roth-Penn and Georgios Georgakis over there is the first author. So just to finish with a take-home message. So in order to solve navigation tasks, even the metric one, you need to learn the distribution of environments. There's no way that you can solve it anymore with a frontier-based exploration. So we have shown that the best way to learn this distribution is by using active learning, by following directions of the highest epistemic uncertainty. Then during the actual goal selection, we choose a strategy which tries to best balance the trade-off between exploitation and exploration. And last, semantics maps, if we are really good at producing them, predicting them in an unseen environment, then we show that this is they really suffice in order to follow instructions. And these are all my collaborators in both projects, the learning to map and the vision language navigation. How am I doing regarding time? Good. Thank you very much.
Any questions?
So I'm working also with the data of market. I have said usually you have a drop in performance between the seen and the unseen environment. So my question is that in your test, you also notice that what is the difference in performance of the test with method and in the seen environment with respect to some environment that we haven't stored?
Yeah. So we are. This is really a prediction task, and as always, the closer the environment is to the initial distribution of the 2000 scenes that are used for training, the better. It's really as any other prediction task in machine learning. There is both the semantic mapping, as long as it is about in the same distribution, we can do quite well. But if you see the numbers, these tasks I really urge you to work on these tasks. If you see the numbers are still quite low. I mean, it is unseen. Everything here is in unseen environments. Everything. All the numbers that I showed is in unseen environments for the semantic maps themselves, for the goal navigation, and for the language for the VLM. I think I think if you have seen an environment, at the end you don't even need prediction. I mean, you might have just a database of things. I mean, the idea is really to work on it somewhere where you have not been before.
Another questions? I have a couple of questions. So for predicting the invisible goals, I saw you have input of both depth and RGB image.
Yes.
And for the depth, you also how critical is here the depth is playing the role in predicting, or whether it's only by the RGB image would work, more or less.
I think it's very critical because it really gives you. We use the occupancy versus not occupancy in order to also predict where we are going. So we never go through the walls.
But the depth image is also coming from RGB image, or is separate input?
Separated. Okay. Yeah. We don't do. That's a very good question. Yeah, we could have used the virtual depth or any of the current approaches. We have not done this. So that's another future direction. Using a monocular or stereo. In addition to unknown odometry. Odometry is known as well.
Yeah, another question is, I'm just curious whether from the language itself it can build the map or go to the goal without image input, just from the language input.
Yeah, it's a good problem to
I guess it will the accuracy will be low, but I want to know whether you have done experiment to see how low it is, and just using the language.
We've done experiments with just putting random stuff on the semantic map, but we haven't trained on that. We have done only the inference. What is the if we do random stuff on the semantics? What is the drop?
It depends how much you change at the input itself. So
Can you go to that one? Can you go to the speaker?
Yeah.
So the online people can hear that as well.
So it really depends how much you change the input for the language and the top. So there's no like direct answer to that, but I thought the question was more about how much does the language actually help the map prediction itself?
Well, that is part of the question, and also I want to know whether the language is sufficient to build a job.
Just the language. Yeah. So preliminary experiments on that have not been successful. So there is around 20-25% drop in the actual prediction of the path itself, depending how accurate you actually predict the path corresponding to interaction, if you only use the language.
Yep.
But I think that matters also. What matters a lot is how detailed your instructions are as well. So the instructions here in the particular data set are not very detailed. So I think it's very difficult to actually predict the path from vague instructions.
Exactly. That is something like if you give a wrong instruction, the map is also absolutely wrong as well. So that also depends on the details like you mentioned.
What we found matters a lot is actually anchoring the words that correspond to objects on semantic objects on the map. So we think that's what actually guiding most of the path prediction itself. So if you remove the semantic objects from the map, then you basically have no easy way to anchor into the environment.
Okay, that makes sense. Cool. Thank you.
Thank you,
please go ahead. Yeah, sure. Yeah.
So I have a question. It's about the semantic app, in the sense that it's related to how you understand the environment. And there's different levels of abstraction that we can use to understand an environment. So in this case, for navigation, what is that level of abstraction? Is it structural and objects? I mean, what is
Yes, that's a very good open. It's actually a very good open question. We use really the lowest level, which are grid points associated with a label. We don't use any, like, for example, graph of objects, like many people have done before in semantic SLAM. We don't use any hierarchy. This is like Ben Kaiser argued long ago for spatial hierarchy. The semantics, no, we use just the grid, the same way you would say occupancy, non-occupancy. We just give an additional labels for other. Sudipta.
So I was thinking that you and many people robotics have worked on active recognition, right? Where the robot trying to look for something and how it positions itself, how it's doing the sensing. So this is not yet doing that, right? Like active recognition. And the first one.
Yes. So this would mean that locally. Locally here, we would move around in order to make the semantic segmentation better.
Yes. What we are looking for may not be visible. Now, trying to predict.
But because we do it halfway, because when we predict, we don't differentiate between visible and invisible. If let's say you are in an environment where it is only visible, we're going to follow what we follow is principally an active recognition study, because we were going to go to new places where our semantics are uncertain, and this will correspond to, because it is modulo the 3D. This really corresponds to what uncertainty is in the image. So we don't differentiate between visible and invisible as far as information gain is concerned. So if there is a very ambiguous object and we still see it, there is a high uncertainty there, and we still go there.
And what I was thinking is that in real world, not in the simulator, making like type the recognition model to the fact that you put something at different scales and trying to bring the active recognition component to the finding of the target object will also be very interesting, right?
That's true. I mean, having incorporating a scale or like a hierarchical model there, definitely we could have narrowed down the goals. Yeah.
Thank you. Thank you.
I have a question. And if there's no further question, let's thank to Dr. Kostas Danielidis again. And one more thing is, actually, Dr. Danielidis just actually yesterday was his birthday, and right after his birthday, he tried to catch up our workshop. He takes the earliest flight to come here to give us the talk in person. And for that, I would like to say happy birthday to Dr. Fernandez again, and thank you again.
Thank you.
Javier, are you here? Javier, are you here? Oh, you are here. Can you hear me? I couldn't hear you. I can see you are here, but
Okay, can you hear me now?
I can hear you now. Can you hear me?
Okay, yeah, perfectly. Yeah, good.
Yeah. Can you try to share your slide and we can test? We can see whether it's
definitely good. Yeah. So I should be sharing now my screen.
Yeah, you share your screen.
Yeah. I just shared it. Can you see it?
Let me try again and let me stop sharing and sharing again. Yeah, right now it works. Let me switch the screen to the other one.
Okay, good. Okay, so all good then. You can hear me. You see my screen. Nice.
It seems all right for me.
Okay, perfect.
Okay, then let me introduce our next speaker, Professor Javier Silva, and he is currently associate professor at the University of Zaragoza in Spain, where he teaches courses in machine learning, computer vision, SLAM. His research is in computer vision, in particular in the use of machine learning and multi-view geometry for localization, scene reconstruction, and understanding, with applications to robotics, wearable technologies, augmented and virtual reality. He has co-authored more than 60 research papers on those topics. And he has also served on the associate editor for Acra errors and attribute transactions on TASE and attribute transactions on robotics. And he is also currently a senior editor on the attribute robotics application letters. Several of his work has quite a lot of influence, like the 1-point ransack for common filter, and he also, some of his work like on inverse steps parameterization for mono-SLAM has also quite a lot of applications. So Javier, thank you very much for coming to our workshop to give a talk, and you can get started.
Okay, thank you very much for the introduction. I hope I could be there. Actually, I am very jealous of you. I will join later in the week, but today it was impossible for me. So yeah, actually, you mentioned some of my early works. So I wanted actually to start with one of my very early works back in 2008, 15 years ago. And yeah, this is a SLAM system, AKF, based on the EKF. And you will see here, in addition to this crappy codec I used, you will see that in this video, for the camera pose and for the features, they will not be represented by points, but by some ellipses that are actually representing the uncertainty of each estimated state. Okay, so you see here the uncertainty ellipse for the camera position and the uncertainties for the features. So all of this was there in when I started my thesis in localization in SLAM. And yeah, the thing is that of course we needed these covariances, these uncertainties for the state estimation, the sequential state estimation of the EKF to perform. But yeah, uncertainties had also a relevance, or we gave them a relevance in robotics, because of course robots need to know the certainty with which they are observing the environment. So these uncertainties, they went missing for a while in localization and SLAM. You can see here a map from OrtoSLAM 2, but this is the same for many systems. So with nonlinear optimization, you do not need these covariances anymore to perform the optimization. It is expensive extracting them. And actually, there are applications that are not as critical as robotics, like augmented reality, in which, well, uncertainties are not really needed. If something is uncertain, maybe the user experience is a bit worse, but you can go on and nothing happens. Okay. So in a sense, in this talk, I would like to advocate this use of uncertainty modeling in several, in 3 actually cases for localization and mapping. Okay, this uncertainty is nowadays again, in my view, getting up and gaining relevance. So in that sense, it is yeah, some works that join this line or giving back the relevance to uncertainty that once had. So this is my collaborators in these 3 works that I did. I was lucky enough to collaborate with people from DTU in Denmark, from the University of Oxford, from DLR in Germany, and colleagues from the University of Zaragoza. So the first of the works I would like to share with you, it refers to place recognition. So place recognition casted as an image retrieval problem, where we have one image, one query image. We have a database of geo-registered images. So all these images are registered in the 3D world. And then the goal of this place recognition system is retrieve the image that is most similar to the query one, okay? And in this case, by similarity, we mean close in space, okay? So addressing this problem, this image retrieval problem like this, what it is usually done is learning an embedding function which transforms each of these images into a low dimensional code, so that images that content-wise they are similar, then they are metrically close in this low dimensional embedding. And then all you have to do is just retrieve the images looking for the nearest neighbor in this embedding space, okay? So, of course, this is nowadays done with neural networks, this learning of these embedding functions. Here, there are the two of the most typical architectures, NetBLAD, that actually mimics the vector of locally aggregated descriptors that was used before the deep learning era. And this generalized mean layer, which is actually very similar to a global pooling. This generalized mean layer is just a layer added at the top of a convolutional backbone. And then this is just a pooling where this P norm is learned. So in a sense, it is a generalization of max pooling, average pooling. If this P is infinity, I think this is max pooling. If this P is 1, this is actually average pooling, okay? So how can we train this network architecture, these deep models, for them to be able to encode these image descriptors that will allow us to say, okay, this image here is the same as this image here, but during the night, and this image here is very different from this bottom image here. So this is trained using something called the triplet loss. Okay, so in this triplet loss, we start by having 3 data samples. One that we will call the anchor, one that we will call the positive, and this is what we want our network to retrieve as a close image, and one negative sample that it is one image that we want that our network doesn't retrieve as a close sample. Okay, so the triplet loss is specifically this one, where we try to minimize the maximum between 0 and this expression here. In this expression here, we have a parameter called the margin, then the distance from the anchor to the positive sample, and then minus the distance from the anchor to the negative sample. So you can see in this formula here, to minimize this loss, you have to minimize the distance between the anchor and the positive samples. So these images have to get close together in the embedding space. And you have to maximize the distance between the anchor and the negative. So you get these 2 images, the anchor and the negative, far away in the embedding space. And when the distance from the anchor to the negative, it is greater than the distance from the anchor to the positive plus certain margin, then this expression here, it is negative, and then the maximum between 0 and something negative is 0, and the loss is flat for this particular negative sample. That means when a negative sample is far away, it doesn't matter how much far away it is. It is already far away. It won't be retrieved as an image close to the other one. So this is one data set that we did in 2020. which is a quite large data set of several places, showing very challenging image changes, appearance changes, okay? Here from day to night, from these are weather or seasonal changes. These are dynamic objects that appear and disappear and change in a scenes. And even rural environments, which even for a human, they are super difficult to match. It is very difficult to match that these images here, these pairs correspond to the same place. So, but all in all, GEM architectures, generalized mean layer architectures, or NetBLAT architectures are able to have more or less 50% recall in this dataset, which is quite high, but still there is room for improvement. So what about uncertainty in all of these image retrieval, place recognition setup? So even if an image is very similar in appearance to another one, that might not mean that they are come from the same place. And in this sense, I love this example taken from a seminal paper in this probabilistic appearance-based matching, which is FabMap. And in this brick wall, you can see here that the probability of being the same place is very low. And this is not because the appearance is different, because the appearance is actually very similar between these two brick walls, but it is due to the fact that brick walls are everywhere. Actually, these guys were from Oxford. So actually they have brick walls are quite common there. Then, of course, if you have these two places with vegetation, they receive a very low probability of being the same place, again, because vegetation is everywhere and it looks pretty similar. And then in these image pairs here, they receive a higher probability of being the same place because they have distinctive features, features that are not that common, and that in combination you can associate with the same place. Okay. So in these deep networks, deep models that I was explaining, what we are going to do is, well, what the state of the art was doing previously is learn for each image one embedding, one descriptor. What we are going to do is transform each image into a probability distribution in the embedding space. Okay. So in this manner, what we will be able to have is for very distinctive images, we will have very peaky probability distributions. But in very like cluttered images or difficult images, the probability distribution will be more flat. Okay. So when we evaluate the expectance of the squared distance between images, it will grow with the trace of the covariance of the respective with the trace of the respective covariances, which in turns it depends on the covariances of the features. Okay, so we will have the covariance into account just for measuring the closest neighbor. So how can we learn these probability distributions? So what we are going to do is to translate this triplet constraint, the fact that the distance between the anchor and the positive has to be smaller than the distance between the anchor and the negative minus the margin. Okay, we are going to transform that into a probabilistic equivalent, saying we are interested in the probability of the anchor minus the positive being smaller, the anchor minus the negative minus the margin. Okay, and we are going to resort to variational approximations. So what we are going to do is assuming first Gaussian embeddings, and actually Gaussian and isotropic Gaussian embeddings. Then this probability here with the triplet constraints, we are going to rearrange it, and we are going to call this difference of distances as a new variable tau, which is actually this one. If these embeddings are isotropic Gaussians, this tau is a non-central a non-central scaled chi-squared, which actually, if the dimension of the descriptor is high enough, let's say 100, it is quite similar to a Gaussian distribution again. Then we will assume also a Gaussian prior for the embeddings, and we will use an approximate posterior, also Gaussian or von Mises Fischer. And with all of this, with variational inference, what we can do is compute this approximate posterior and have this probabilistic formulation of our image embeddings. Resorting to variational approximations actually is very nice because for all the computations that we need to do, there are closed form expressions, and then the training is not significantly different from the standard triplet loss. So we have uncertainty almost for free. So yeah, before going to the place recognition results, we tried in many in several image retrieval datasets. This is one of birds, and yeah, it is just to illustrate how nice it is the uncertainty that we are able to estimate, to predict. So in these two first rows, these are highly uncertain. Our network got highly uncertain embeddings for these images, and you can see why, because the bird appears very small or partially occluded or blended with the surroundings, with the environment. And in these ones here, these are highly certain embeddings, and you can see again why, because the birds appear very big in the images, and they have quite nice patterns to be spotted and recognized. And this is finally results for place recognition. So here in this table, the Bayesian triplet loss that I just explained, it is the last row. Compared to the standard triplet loss, we lose a little bit of predictive power, but we attribute that to the fact that we used a very similar network. So the capacity of the network for predicting the embedding decreases because it has now to predict also the uncertainty. But compared to other baselines that do other types of uncertainty estimation, we get quite nicely calibrated uncertainties. And here in place recognition, you can see the type of uncertainties you can get. So all of these are positive pairs that were found at the same place by our network. But in these ones here, they were given a low confidence. In this one here, because you have this sun here almost whitening or your image. Then you have tunnels that do not have nice features for recognition. Here, the features are just the road and vegetation, which are everywhere. And the ones that are given high confidence is because they have clear landmarks. So, and in particular, landmark buildings. Okay, so with all of this, what we can see is that the uncertainty we can get for this is quite decent, and we can use it for example, for loop closure, okay, for considering differently the loop closures depending on the uncertainty that the network told us that they have. Okay, so with this, I will switch to the second work that I wanted to show you. Here, this is a multi-view odometry SLAM system. And here what we try to do is to get rid of this standard assumption over the image matches or the multi-view residuals, that is 1 pixel isotropic constant variance for feature matching, or just a constant quantity for photometric residuals. Okay, so we tried to make this variant, and actually depending on the viewpoint. Okay, so the two concepts that we deal with here is perspective deformation. So whenever you take an image, for example, this I0 here of something in the world, then if you get closer, if you get farther away, if you move, this pattern in the image gets distorted, gets deformed. Okay, and we call that perspective deformation. And how does this affect the SLAM? Well, our hypothesis is that when you have patches that are undergoing quite a lot of deformation, these are likely to have larger noise. Okay, larger multi-view noise, both photometric or image reprojection noise. Okay, and we color in red here the ones that have higher deformation for the patch. So what we try to do is to derive a formulation for the deformation of the points in an image here, and then make the answer, the noise, the variance of the noise of the points depend on this deformation that they undergo in the image. So here is the formulation that we found for perspective deformation. So we start by the projection function, taking one point in one view, then projecting it back to the scene, and then projecting it again in another view. Then we made the first order approximation, and this derivative here, this is what it is called in the continuum mechanics literature, the deformation gradient tensor. So this is a tensor that encodes the deformation that undergoes an infinitesimal patch around a point from one view to the other. And it depends, of course, on all the parameters of the projection functions. Then we again exploited the continuum mechanics literature, and we computed the Cauchy green deformation tensor, which actually the nice thing that it has is that it gets rid of the deformation due to, it gets rid of the contribution of the rigid rotation between two views. So if we use the Cauchy green deformation tensor, all we have in this tensor is deformation. We get rid of rotations that are that come from rigid motion. And then finally, if we want to compute the deformation in a particular direction nu, we make this computation and we end up here with a deformation. So the nice thing about this feature, this formulation exploiting all this continuum mechanics literature, is that it is general for every surface. So we can deal with any type of surface in the real world. However, due to the difficulty of parametrizing general surfaces in the real world, we made a planar approximation in the paper and our experiments, but the formulation is in principle general. And then having a general formulation for the deformation between multiple views of a patch, what we did is compute empirically or extract empirically the relation of such deformation with the variance of the, in this case, of the photometric noise. So what we observed, this is the results of a simulation in the ICL new in dataset, but we also did that in other dataset and in other datasets, and in general it holds that there is a clear, very nice relation between this deformation in the image and the variance in the photometric error or the feature matching error. So with this, we can we can have an estimation of the image noise that one point is going to have in bundle adjustment, and we can use that for many things. One of them is, of course, using this better covariances in the bundle adjustment. So what we did here, the experiment we did is taking OrbSlam as it is, running it in the Freiburg, in the TUM RGBD dataset, and these are the absolute trajectory errors, and then plugging in our bundle adjustment, actually not our bundle adjustment, but the bundle adjustment of OrbSlam with our covariances. And the result is a 10% reduction of the absolute trajectory error. And you can see that in a quite consistent manner. It improves over all sequences. And here we did the same with photometric bundle adjustment, in this case with our in-home photometric bundle adjustment, because it was easier for us to plug these uncertainties. And again, the reduction is quite bigger in this case. Of course, we attribute this because of the higher maturity of feature-based bundle adjustment. You know that it is super hard to improve something in feature-based bundle adjustment. Photometric bundle adjustment is less explored, and consequently, you can improve a little bit more with anything you do. So this is a significant, reduction, and actually this is also pretty quick. These computations here are super cheap, and the additional overhead for using our method is around 3% of the total cost of bundle adjustment. So for 3% extra computation, you have 10% error reduction in the absolute trajectory error. What we can do also is use these better covariances for computing better information metrics. Actually, what we observed is that these information metrics gives, in some cases, they give absurd results, totally nonsense results if we use constant isotropic Gaussian error. For example, in this circular trajectory, if you assume that points has constant isotropic error and you compute the information that you gain by observing, by adding a second view in all of these positions, you have that the information is the same. And you know that this is not true, right? When the more you skew your second camera, the worse is your accuracy. And actually, when you are at a 90 degree, if the patch is planar, most likely your estimation is already quite corrupted. So using our covariance model, this is actually very nicely reflected. When you start turning the camera, the information drops, and farther than 90 degrees, the information drops quite heavily, and you can do nothing as it corresponds to reality. Okay, this is a similar case with a camera moving forwards and backwards, and again, our formulation allows to compute nice metrics for information. And actually, what you can do with this information is doing informative point selection. So what we did actually in a previous work is using informative point selection to run a visual odometry with a very low number of tracks. So in this case, with only 24 tracks, 24 point matches per frame, we are able to achieve an accuracy that is very similar to state-of-the-art systems. This is DBO SLAM, this is OrbSlam 2, this is CAN-EBO. But as I said, these three baselines here, they are running as out of the box, and we are running with only 24 tracks per frame. You can see here a video of this system. Here in purple, there is the estimated trajectory. In white, it is the ground truth trajectory. You can see that it is almost overlapping. And you can see here the small number of tracks that we do, as I said, just 24 of them. This is a photometric odometry. This is why these points jump from place to place, because actually we can use every high gradient point we want, and at every frame we compute the 24 that are most informative. This also is running in real time. So yeah, finally, just to finish, I wanted to comment on a third work, actually in an application that it is as safety critical as robotics, or even more, which is medical application. Okay, so in this case, our goal is to model the uncertainty of single view depth predicted by a neural network in a colonoscopy image. So as the motivation for this work, we want to reconstruct human cavities just to help medical staff to take better informed decisions. Okay, so this is an example of what we do. And actually, our motivation for using single view depth learning instead of multi-view reconstructions with feature matching, the more classical approach, is that feature matching is quite challenging in this environment. And what we found is that if you use if single view depth that you learn in this data, and you just do a dense photometric tracking using this predicted depth from single views, things work quite nicely. You can do quite nice reconstructions of these human cavities. Then, of course, as I said, the medical domain is quite safety critical, so it would be nice to have uncertainties. And then a usual challenge in this data, in addition to the other ones, is that usually there are no ground truth available. So in order to learn this depth and its associated uncertainty, you have to rely either on self-supervision from multiple views or in transfer learning from synthetic data. So this is what we did, evaluating these alternatives: self-supervised learning, or learning in a supervised setting in simulation, and then transferring this learning to the real scene. So what we found there is that the best was actually transferring the learning from a synthetic dataset. Of course, you have to rely on a nice synthetic dataset. You have to make it, render it with care, just to be quite similar to the real environment. But they are nice datasets now, and we could do it. So I suppose this holds in the future. And in this paper, it just got accepted at NICAI. What we do is in this in this teacher-student approach, we have a network that is the teacher. This is the one that is learning in the synthetic domain. And then this teacher is the one that it is doing predictions in the real domain, and this is serving as a supervisory signal for the student network. And a critical thing there is to consider that the teacher is not an oracle. The teacher also has an uncertainty. So in this loss here for the student, it is important to incorporate the uncertainty of the teacher to get the best metrics, which are the ones that we get here. And these are better than the other approaches, just using networks that just learn in the synthetic domain, and using networks that just learn in the target domain, in the real images, but with self-supervision from multiple views. So this is these are some results where you can see that this is the depth from multi-view stereo. This is the depth predicted from our single view networks, the uncertainties and the error. So if I stop in any of the frames, in this one here, for example, what you see is that usually this approach has the smallest error. You can see here bright is big error. This one here has less brighter areas, more dark areas. So it has a smaller error, and it also has a better representation of the uncertainty. These uncertainties here are smaller than these ones, and actually these ones are better calibrated. So this, this is what I wanted to explain to you. These three works using uncertainty related to localization and mapping in three different applications. So just to sum up, as I told you at the beginning, we derived in 2021 a Bayesian triplet loss that allows to quantify the uncertainty of appearance-based place recognition. And as I told you, almost for free, as the overhead introduced by the variational formulation is very, very low. Then we also modeled the dependence of the multi-view residuals, both photometric and feature-based, with the viewpoint, and what we observed is that it improves the bundle adjustment accuracy by around 10%, and it boosts information-driven localization. So we can select informative points better, and then we can do visual odometry or SLAM with a very small number of points. And then in the colonoscopic domain, what we did is to characterize the uncertainty of single view depths, and in particular with a teacher-student approach, taking into account the uncertainties of both the teacher and the student. And that's all from my side. Thank you very much again. And if you have any question, please let me know.
Hi, thank you. I have two questions if you don't mind. The first one regards the triplet loss formulation, and can you go back to that slide? Can you hear me?
So sorry, the sound is very bad. So if you can get closer, I heard very clearly the previous speakers.
Yeah, let me change your mic. So
okay.
I have two questions, if you don't mind. The first one regards the triplet loss function formulation. Can you go back to that slide?
Yeah, here.
Basically, my question is when you model the distance between anchor to positive and anchor to negative, is that L2 distance, or should it be normalized by the uncertainty of the, let's say, the lag uncertainty?
Is that, sorry, what distance you say? Is that
your distance, your formulation, loss function formulation, is that L2 norm, or it should be normalized by the embedding descriptor covariance itself?
Yeah, so what you actually do in this variational formulation is maximizing some quantity called the elbow, and then this is what guarantees this is what guarantees that these two approximate posteriors here are actually very close to the true posteriors that are intractable. So the losses are a bit different from the standard ones, if I understood the question correctly.
What I'm trying to say is that, for example, the loss function you model a minus n square and the a minus p square, that's L2 distance square, right?
So you mean, yeah, that's it. Each of these, so the distance, I mean, each of these two AD, PD, ND, the three of them actually, they are Gaussian. So the square difference of a Gaussian, this is a scale non-central chi-square. And this is the distribution that for high D, actually not so high D. We did some experiments, and I think for more than 50, 70 dimensions, this is actually quite similar to a Gaussian. Yeah.
Okay. Can I have a second question regarding the feature detection uncertainty modeling? Can you go to the, yeah. That's not necessarily a question because I don't remember wrong, you formulate the gradient tension, right? Tensor.
Yeah.
But my question is, why it has to be gradient? Because it just occurred to me the classic difference of Gaussian pyramid, it has this spatial and scale naturally forms 3D space with this cubic surface where you can extract the feature and also naturally derive the derive the uncertainty of the feature. Right? So it's a similar idea, I believe, but why it has to be gradient tensor?
Yeah, this is a very, very interesting question, actually. If I understood you correctly, what you say is that when you extract certain features in an image, you can already extract its uncertainty. So the thing is, you are right. When you compute features, there is an uncertainty associated to the extraction, but this is another uncertainty. This should be added on top of the extraction uncertainty, because when you extract features, you have some uncertainty, but if the viewpoint grows, this uncertainty grows even more. So you are right. Yeah, there is uncertainty in the extraction, and there is uncertainty when you have very different viewpoints.
Okay. All right. Thank you.
I have a question.
Yeah. Thank you.
Javier, I have a question. And in triplet for the place recognition, you have somehow used the triplet to recognize images, which I see can overcome the daytime and the nighttime, those kind of illumination invariance. I have seen something like in the same trend is trying to use triplet loss, trying to train the feature detection and feature matching descriptors, and which using the triplet to train the feature matching. And so I can see there's quite a lot of similarities in here. But for place recognition and using the triplet to train the place recognition, and another one is to train the feature matching, and which do you think is can have better performance?
Yeah, so definitely, yeah. Here in this paper, our contribution is only on formulating probabilistically the triplet loss and this place recognition, but with a single image descriptor, not feature matching. But you are right. These approaches usually, as a second stage, they add feature matching and they improve. So possibly a follow-up of this work could be to incorporate all the uncertainties together, the one from the triplet loss and the ones from the feature matching. It would be a nice follow-up, but we didn't do that, not in this work, or we didn't continue in this direction. Yeah.
Another small question that is not absolutely a question. Is something like in the teacher uncertainty part, teacher and student part, and for the teacher to train the teacher, instead, in addition to the uncertainty, do you have some other laws used when you train, no matter if supervised and unsupervised?
Yeah, that's it. So what you can do to train these networks where you do not have ground truth, these are images, you do not have the depth. So what you can do is self-supervise, saying, okay, I want to learn the depth so that when I back project a point to a certain depth and then projecting another image, the color is the same. And these are the self-supervised approaches, but actually, if you see here, in this domain, they don't work that well, possibly because of reflections, deformations. Actually, these cavities deform. And these self-supervised approaches, monodepth 2 is the one that we used. they don't consider deformations. So possibly this is why they work the worst. Then if you train in synthetic data is quite nice. So then the network learns better. And this is why this supervised GT is a network that learns on synthetic data, and the metrics are better. Then if you do teacher-student, you learn in synthetic data, and you use this network that learns in synthetic data. It makes predictions on the real sequences, and then these predictions on the real sequences, it is the supervisory signal for another network that we call the student. And this works, even better, because of course we are using more data, and actually data from the real domain. And then finally, what we do is also taking into account that the teacher is not an oracle and it is uncertain. So if you incorporate this teacher uncertainty, you improve even more. Yeah. So this is more or less a summary of the 4 approaches.
Thank you. Any other questions? Go ahead.
Thank you. So very good talk. I'm just curious since there's no ground truth for such uncertainty, and when you design such uncertainty modeling, I wonder how you quantify the goodness of such certainty. Because recently there's also some learning-based methods that tends to learn some uncertainty for the measurements, and they seem to have quite different behavior than like handcrafted uncertainty. So just wonder how do you think that we can quantify the goodness to measuring the goodness of the uncertainty?
Yeah, this is actually a very good question. Yeah, this a very good question. These metrics here in green, these are metrics for the error. And what we did is we computed a multi-view stereo reconstruction, and we use this to compute the errors, taking into account that it might not be very good. So we filtered some problematic points and etc., etc. But you are right, for the uncertainty, we do not have ground truth. So usually the metrics are based on the consistency of the errors and the predicted uncertainties. For example, if you take all points for which the predicted uncertainty is 10 centimeters, the errors should be within this range of 10 centimeters. So this is more or less what it is used to measure this consistency of the uncertainty. Uncertainties should be consistent with the errors. So if you take the 10% of the points, for example, that have smaller predicted uncertainties, it should be the points with the 10% of the points with the smallest errors. Okay, and with this you can do graphs and compute the differences between predicted uncertainties, and real errors. Then this is one of these metrics, uncertainty under the calibration errors. And I don't know if this is clear.
Yeah, it's clear. Thank you.
Thank you.
Thank you for such a wonderful talk. So I wanted to ask, like, regarding this table, like you are saying that like the M deepest ensembles, which is used to compute like the bottom row. So is it fair to compare with other models which do not have like ensembles? Because the primary reason we switch to a monocular depth kind of model is like a fast index.
Yeah, good question. Sorry, here I didn't explain this detail. All of the models are deep ensembles. So what we did in this work is following, as Costas said in the previous talk, following this Kendall work, we computed the aleatoric uncertainty and the epistemic uncertainty. So the aleatoric uncertainty, we are computing it, minimizing these Laplacian laws. And then in these laws, the uncertainty is here in the laws, so we can learn it. But this is the uncertainty due to the data. and then we need the uncertainty that is in the model. And for that, in this case, we did an ensemble of a few networks. I think only 10 networks. Yeah. So in all.
Yeah.
Sorry.
Yeah, it is actually 5 or 10 in that paper. Yes.
Yeah. That's it. And actually, the 4 methods here, they all have epistemic and aleatoric uncertainty. And for the epistemic, they all have an ensemble with the same number of networks. So all have ensembles. Yeah.
Okay. And just following up on the Bayesian triplet stuff, because you are using a negative log of the Laplacian likelihood here, whereas in the Bayesian triplet ones, you are using the Gaussian one. So I feel like Laplacian likelihood will be more like robust to outliers. So why didn't you use a Laplacian likelihood for the Bayesian triplet stuff, but you use it here? So I believe that's a normal random, like a multivariate normal. Yeah.
Yeah. Yeah. Good question. I cannot remember if we tried it or not, but yeah, it would be a nice thing to try. I agree with you. Yeah. The Laplacian is usually more robust to outliers, so probably it would be a nice thing to try. And I cannot remember now if we tried it or not. Yeah. Sorry.
Okay. Okay. Yeah. Thank you.
Thank you. Thank you for the questions.
Okay. Thank you, Javier. I think it's the time for you to have sleep. Actually, it's already more than 12 in the midnight. Okay.
Yeah. But thank you in any case. Yeah, it was a pleasure.
Yeah. Okay. Thank you, Javier. Let's move to the next paper presentation from Gawen Liu, and her presentation is on the topic of parallel generative adversarial network for third-person to first-person image generation.
Hello, everyone. I'm Gawen Liu from Cisco Research. Today, I'm going to introduce our parallel generative adversarial network for third-person to first-person image generation. Cisco is known as a networking company, but actually, we are working on different research domains like AI, ML, edge computing, computer vision, quantum, cyber security, security in edge computing, healthcare, supply chain, natural language understanding, ethics in AI, and future work. I'm going to introduce our work following this outline. This work is about third-person to first-person image generation. Third-person is also known as exocentric view. Third-person view. The data are usually collected from third-person camera. First-person view is also called egocentric view. The data is usually collected from wearable camera. In this work, we mainly generate egocentric view from side view images and top view image. This is our framework. This framework consists of 2 parallel generation tasks. 是的，是 mute。
是这样的。因为你如果是那个这个话，这个是
This is our framework. This framework consists of two pipelines, two parallel generation tasks. One task is to generate egocentric view image from exocentric view, and the other task is in the opposite direction, which is generate exocentric view from egocentric view. We have two generators and two discriminators. For the generator, we have we are using UNets. Inspired by the UNet, we designed a cross-cycle loss, which is we take one exocentric view image as input and go through the first encoder of the first generator and then output to the decoder of the second generator and generate the fake exocentric view image. The other one is we import the exocentric view image and go through the encoder of the second generator and then go to the decoder of the first generator and generate the fake egocentric view image. Here we have fake egocentric and exocentric images output by the two generators, and we use L1 loss to compute the difference between the fake image and the real image. And we also designed a novel contextual loss, which is extracted by VGGNet. VGGNet is friction on ImageNet. The optimization objective function consists of 4 parts. The first part is the contextual loss, which is described in the red area. We extract the features, contextual high-level features of the image and compute the similarity between the two images. And then we normalize the similarity as the contextual loss. And second, we compute the cross-cycle loss across the two generators. This is the standard adversarial loss, which incorporates both the discriminator and the generator. The reconstruction loss is using L1 loss, which is to compute the reconstruction error. The data set we are using is the side to echo subdata set and the top to echo subdata set. So we have around 26, more than 26,000 pairs of images for training and more than 13,000 pairs for testing for the side to echo data set. And for total ego data sets, we have around 28,000 image pairs for training and 14,000 pairs for testing. This is our results, experimental results. We compare the results with the classic single view image generation algorithm like text-to-text scan and cycle scan. And our performance is better than text-to-text and cycle scan. And we also compare with cross-view image generation algorithms like XFork, XSequence, and selection gun. This is the qualitative results. Compare with the single view generation methods, other single view generation methods, and the cross view generation methods. Our performance looks better. The objects are in the right position compared with the ground truth image. This is the results on site to ego data sets. In our work, we propose the P-GAN framework to learn share the information between different fields simultaneously via a novel cross-cycle loss. And we designed a novel contextual loss to capture the context information. And our experimental results showed our performance is better than other classical algorithm. Thank you.
Any questions? So a quick question on your model is using two parallel ones, and the model will grow double size, or is still not really that much that big? Or in the usage you just use one part, or you use those two parallel at the same time?
Yes, it's running at the same time and the training at the same time. It's one pipeline.
Okay. In testing it's the same, right? Testing is also in parallel.
Yeah.
Okay. Thank you. No questions. Yeah, please. Okay.
So this task seems very similar to geolocalization, where you want to select aerial photos to kind of a street view photo. Have you considered trying to train some of that and seeing if that helps performance? Is that a thing that you guys have started looking at?
Yes, that's a great suggestion. We are considering using multiple sensors to add some more information like locations or multiple data and multiple information. But it's an ongoing project. We haven't added that, but it's in our future plan. Thank you.
Thank you. It's the time for the last contribution. You're using my computer, right? Yeah, using mine. Yeah, using my computer, right? Yeah, true. Thank you. Share the screen. The first and then I share the screen. Okay.
Thank you. Hello, everyone.
My name is Antianta Bangun Harjana, and I will be presenting one of the works that we are doing in our lab with my advisors, Suhyun Kim and Kyung-Soo Kim. And we are from MSc Lab in the Department of Mechanical Engineering at KAIS. The title of our work this time is Revisiting the Receptive Field of Conv GRU in Droid SLAM. And as the title suggests, our work is building on the amazing Droid SLAM work that was presented last year in NeurIPS 2021. And we are trying to improve the Conv GRU updates that are being used to refine the Droid SLAM framework. So I will first talk about what is Droid SLAM and how it works so that we can be on the same page, and then talk about why we want to improve the Conv GRU in the Droid SLAM, and then present what we did and the results of our experiments. So as we've seen in a lot of today's talks, visual SLAM has had a long history in the research community. And the classical approach to SLAM, or rather the conventional approach, has a very strong physical or geometric foundation to the modeling of the algorithm. But even with the strong physical or geometric foundation, there are a lot of challenges in the real environment or real scenarios that are hard to model, such as scenarios with textureless regions, motion blurs, like when we move quickly or there are objects that move quickly, dynamic lights, and also inaccurate camera calibration. And that's why in recent years, many studies are starting to try to integrate deep learning, which can use data to learn all these challenges in the modeling to improve the SLAM algorithms. And as it turns out, learning SLAM can be difficult, and especially in generalizing from the training set to the unseen data set. So what a lot of recent studies find out is that the hybrid between deep learning and conventional method is what seems to be the future. And Droid SLAM is also a hybrid, and in their case, sorry, I'm trying to get the laser pointer. Okay, and in their case, they perform this iterative refinements, and at the end of each refinement, update refinement steps, they perform the conventional geometric bundle adjustments to compute the depth and relative forces. So let's take a closer look at what Droid SLAM did. And the key ingredients in Droid SLAM is actually the all-pair matching correlation that was introduced in the Raft optical flow approach. And in this approach, as in the case of Droid SLAM, we actually have multiple sets of pairs of images in a set of adjacent frames. And we'll take a look at one of the pair as our interest. So let's say we have the target frame, and the all-pair matching correlation will compute the correlation between this pixel of interest and all the pairs in the other source image. And this will give us the correlation pyramid that contains the correlation values between each pixels in the target image and all the pixels in the source image. And that can give you the long-range motion information between the query image and the key image. And this is used as one of the inputs. And so at the end of each bundle adjustment step, when you have the depth and relative forces computed, you sample from this correlation pyramid, which is in the inputs, and use it to update the hidden states in the conv GRU update. So if this is just the so if we see just this part of the update step, just one update step, so we have the correlation pyramid from before, And we want to update these hidden states using conv.gru, and we sample from the depth and relative force the correlation values from the correlation pyramid and perform conv.gru. And that's basically the key ingredient in the DroidSlam. And they showed that they outperformed a lot of state-of-the-art models on the challenging Tartan L datasets. And in case you're not familiar with this dataset, it is a synthetic data with fast motion, light and weather effects, and a lot of dynamic objects. So it slightly models the real world data. And so our questions would be, the DroidSlam uses the data-driven approach to model some of the difficulty in the challenge, like the challenges that I mentioned before, like the textureless regions, motion blurs, occlusion, etc., etc. But as we saw in this conv.gru, although we actually perform this all-pair matching correlation that gives us a long-range motion information, when we perform the conv.gru, what we are looking at is actually just the local window, since we are just using this small 3x3 convolutions. So we ask a simple question: will a larger receptive field for the conv.gru updates be beneficial? And so that's the experiments that we did in this paper. And the first modification to the conv.gru update that we did was to perform spatial pyramid pooling. And a spatial pyramid pooling was, maybe you are familiar with the deep lab work, and this was popularized in the deep lab work, that you can basically, if you compare the original conv.gru and then now we perform spatial pyramid pooling, what we do is just downsample, perform the 3x3, and then concatenate with all the other computed hidden states. So by doing that, we can have a larger receptive field, and we can have some sort of semi-global information and extract context information from a larger receptive field. And this might give more information when we have the challenges like the textureless regions, motion blurs, and things like that. And the second modification that we are we also experimented with the Atlas version of the spatial pyramid pooling, which have the dilated convolutions instead of downsampling. And the second modifications that we did is by doing self-attention. And what we hope to achieve by doing self-attention is that we can get the global context information from the image. And if you've seen the transformer works, we are just doing the similar steps by basically, if we have this point of interest, we compute the query and key and compute the attention value, or attention between this point of interest and all the other points, and then we perform the updates using that. So now we have the updates by aggregating from the whole image, and we are hoping that that will improve the performance even further. But as we know, when we perform deep learning, and then especially in this case, we are performing iterative refinements. So the memory has to be stored in every operations. And when we are doing backpropagation through time, the training memory becomes extremely large. And that was a challenge that we were facing. So in the original DroidSlam paper, we did experiment with the original DroidSlam. And what we found was that with the baseline, we already consumed 24 gigabytes of VRAM with a single batch. So if we perform all these modifications, then the memory will be too much, and we didn't have the resources for that. So what we did was perform slided convolutions before each of these operations. So instead of doing it in the full resolution, we downsample it first and then perform these operations. And then we upsample it again. So this was the experimental setup. For every modifications, we just perform slided convolution. And additionally, we also perform experiments with just doing the slided convolution to see what happens. And this is the results. And on the top is the table that I showed in the early slides. And on the bottom is our own experiments. And compared to the original, we actually made some changes in the experimental setup due to some limitations in our resources. We changed the batch size from 4 to 2 and the number of iterations from 250,000 to only 100,000. But we reach similar level of accuracy to the original Droid SLAM. And this is the absolute trajectory error on the Tartan Air test set. And if we look here in the average, the slided convolution implementation that we did actually outperform the original implementation of Droid SLAM. And we think that it's because by doing slided convolution, we are actually already increasing the receptive field. But when we add the SPP and ASPP, because we already did the slided convolution, this didn't really make much difference. And in fact, we found that it reduces the performance. And the other interesting thing that we found is doing self-attention gives us a more stable performance, and the accuracy is improved a lot compared to the original Droid implementation. So these are just the visualization of our results. And this is on the EuroC MFE dataset, and we just visualize, and you can see that it looks quite nice. And this is also the visualization of the plotted point cloud. And so now we ask the question, what's next? Because we found that the largest issue that we found was that this implementation requires a huge memory consumption. And we are actually inspired by one of the work that is going to be presented in the CVPR called DEQ Flow. And I highly suggest you to check it out in the poster session, I think. And in that work, deep equilibrium model is implemented to reduce the memory consumption of fixed point iteration. And in our case, the fixed point would be the hidden states and also the optical flow and the depth and the pose. And this is actually not part of our paper currently, but I just wanted to share what we think would be the next step in improving this. But yeah, I'll just briefly talk about this. So by using deep equilibrium implementation of the SLAM, we found that we can reduce the memory consumption during slaining from 24 GB to 17 GB. So it's a large 30% reduction. And hopefully we can perform more experiments with more flexible model designs by doing this modification. And hopefully we can get an even more improved results. That will be the end of my presentation. Thank you. Oh, that's. Do you mean this one? Yeah. It's the trajectory error. So. And
you show the map building is better.
Yes.
It looks good, and we have the quantitative result that is showing how much improvement, whether the mapping, generated mapping is more accurate or not.
Yes. Unfortunately, we didn't perform evaluation on the depth maps, but I think we'll look towards doing that to evaluate it properly. Yes.
Thank you. Thank you very much for staying here until this long. And it's really the end of the talk, and really appreciate all of you staying here until the last minute. Okay, thank you.
Yes, thank you.
Thank you very much for organizing.
So curious about the current GRU, when was the first piece of published?
So current GRU is actually based on GRU, which was published in 2012.
Okay, yeah, that's very old.
Yes, and this was actually done in the last optical flow paper. I believe that was in 2009. And this generic SLAM one was from last year in Munich.
And so in GRU, you have a training set and the GRU model, even states are changing, right, as the sequence gets processed. Yes. So all the train parameters of the GRU or similar thing would be like LSTF and GRU or all that signal, right? They have gates, right? So it means that the values in the gates change over time as you process the sequence. Yes. And when you add the self retention, it still has all the gates of the GRU. You will be modifying it's not replacing the gates in the GRU. All of that is still there. Yeah. But the self retention is just changing how the correlation volume information is being processed.
Yes. So in the original GRU, it's actually processing the 1D sequence, but in current GRU, it becomes the P by P convolution. And in the self-retention, what we did was just changing that into the self-retention.
So the pairwise interaction where between patches is the same.
Yes,
overlapping.
Yes. Okay. So that's actually one of the part where we are hoping it will improve the performance because the correlation parameter is acting as a cross attention, and we're hoping this one will act as a self attention. So we have both cross and self.
Why is it called voice?
It stands for deep equivalent optimization.
There's a void or high speed or low power computer.
Yeah,
void is basically
not like
So we talked about papers of localization. So this feature we have localization units now. So it's very different to so to remember faster to recent recipe things. We have to put papers on national points objects. So with the problem goes to problem, we have not applied this for scenes. So we're defining scene forms based on the process that we have here. Then basically try to basically look into the most basic network. So we do not want to add that. But where is the geometry regression or so one of the key parts was that when you with objects, either for face or hand or equal distribution is basically that in a world with business. I don't know when you big use of so many people. But that's work with them or it's worse or not.
so the prevention command part, like now you will separate process. I mean, not so much for the people doing that to get into everywhere and trying to just be better than all the others, but it's not better than any of the method that's stored in the map. I think how
Here's the art flows for the rest of everybody to start looking for these things. Thank you very much. And then we don't have any election from the contract.
well, we do have a